Hello and welcome everyone. Very happy that we are all together again. In this very fast tutorial, we will take a quick tour on the solar system energy as a whole to anchor some basics that we need to learn during this course. So fasten your pill and let's get started. Our aim of this lecture is to know what is the basic concept behind the solar energy and its use. Since we are at the very beginning, we need to start from scratch, and during this course we will go in depth step by step. And the second step is to know what is the different type of the solar energy technologies, what are the different topologies available to use in the solar system world. That's good. Now, very basically, the solar system energy is a system that takes the energy produced from the sunlight and convert it to an electrical energy that we can use and take the most benefit of it in our daily use. So the solar energy take an input and it produce an output. The input is the sun energy and the output is the electricity or the electrical energy. Alright. But we need now to know what exactly the sun energy consists of to take the most use of it. So the sun energy consists of two parts. The light produced from it to make our beautiful day too bright, and the second part of the sun energy is the heat produced from it. And this heat gives us the required energy that we use mostly in our life. And by a little thinking, you can estimate that each of those two types of energy is used in the solar electrical energy production in different way. So we have two main types of the solar energy production depends on the type of energy used. The first type, which depends on the light, is called the solar photovoltaic technology. Therefore, at this type we have some solar panels as you see here, and this solar panel absorbs the light that is radiated from the sun. Then, by some means of technology that we will illustrate later in details, the light is converted to an electrical energy. Now, the second type of the solar energy is the solar thermal technology, and at this topology there are some means of mirrors that attracts the sun energy on it and it concentrates it. Then the concentrated sun rays are reflected from the mirror and falls onto some tubes like this one here. And those tubes absorbs the heat from the sun rays. Then this heat is used to produce electricity by converting it from the thermal energy to the electrical energy by some means that we will illustrate also later. So at conclusion, these two different systems used to produce electrical energy from the solar energy, the photovoltaic and the thermal type. Now let's talk about the first type and the most important type, which is the photovoltaic system. Here, the photovoltaic solar system consists of two main types. The first one is the off-grid system, and the second one is the on-grid system. So let's differentiate between them. Here, the off-grid system, and from its name, it's disconnected from the electrical power supply or the electrical utility. So it's not connected to the company that provides you with the electrical energy. Therefore, you can say that it's a local system because the power flow of the electrical power generated is going through some local devices to supply them, and it doesn't go through the utility. And the components of the off-grid solar systems are the solar panels that receives the sunlight, then it converts it to a direct electrical current, and this direct current or DC current is going through some charger controller. And the job of the charger controller is to control the flow of the DC electrical power from the solar panel, and the power gets out of the charger to enter the batteries. And we use the batteries to store the electrical energy so we can use it later or at any time we need. This is because the sunlight comes only during the day. But suppose that we need to use the electricity in the night, so we use some kinds of batteries to use it at any time we need, or to use the electricity stored at any time we need. But the problem now is that the stored electrical energy is a DC current, but the most electric devices or the most electrical appliances we use works on an AC power or an alternating current. So we need to convert this DC current to an AC power. And for this reason, we use an inverter, which is the powered electronic device that converts the DC power to an AC power. And finally, this electricity is ready to be used for our electrical photovoltaic solar system, and for this reason it's an off-grid, as you see, because it's not connected to the electric main power supply or the main utility. So the flow of electrical energy is a local one, only to supply your devices. And now the second type, which is the on-grid solar system, and you can guess from its name, it's the inverse of the off-grid solar system, as the output power of this system is going directly to the electric utility or the electrical grid. So its construction is more simpler than the off-grid system. Here the DC current comes out of the solar panel, is converted by the inverter from DC to an AC power, and then this AC power is injected directly through the grid. So this is the basic difference between the off-grid solar system and the on-grid solar system, and for this reason the on-grid solar system produces a global flow of electricity as it's injected directly into the global grid. And the final thing that we have now is the hybrid system, as the hybrid system is a combination of the on-grid and the off-grid solar systems, as the electrical energy goes through the utility, through the inverter, and the other part is continue pathing from the charger to the batteries, then the inverter. Finally, it feeds our electrical appliances and devices. So those are the different photovoltaic solar systems, the off-grid, the on-grid, and the hybrid system, which is a mix or a combination between the off-grid and the on-grid. And at this point, we are finished. And those are the links for the photos that we use in this lecture for preparation. Hope that's clear right now. Thank you for watching and see you next lectures. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will start asking why the solar systems. So we need to know what are the benefits or the advantages of the solar systems that will motivate us to work on this field and start our investment in the solar system design. Now fasten your belt and let's get started. The aim of this lecture is to discuss an on-grid solar system from the economic point of view. So the first benefit of the solar system implementation is its economical part, as the electrical power produced from it will be sold and it will provide an income for you as an investment owner. Therefore, in this tutorial we will focus on the economic advantages of the on-grid solar system by an example. Now our on-grid case study says that suppose you are an owner of a textile factory and the monthly electrical bill that you pay for is large and it annoys you. So you need to solve this problem to reduce the electric bill and gain more money from the factory by making your system more economic. So you have decided to construct an on-grid photovoltaic solar system farm beside your factory to produce electrical energy that will reduce the electrical bill that your factory consumes. So the photovoltaic solar system farm will produce the energy that feeds your electrical machines inside your factory. Is that right? No, it's a trap for you. This is wrong since the on-grid photovoltaic solar system produces electrical power that feeds the utility and it has no relation with the electrical loads. So as we mentioned before, the on-grid inject power through the electrical grid while the off-grid inject the power through your local devices. Now we need to know how the factory owner gets the benefit from this on-grid solar system farm. Easily we say that there are two blocks of money in that case study. The first one is the monthly electric bill that this factory owner pay each month because this factory consumes energy from the utility. So the factory will pay an amount of money for the utility each month. And suppose that this amount of money is, for example, $4,000, and the negative sign here because the owner will lose this amount of money or it will leave his pocket. Also, the second amount of money is the money that the factory owner will gain from the utility, as his solar farm has produced a specific amount of electric energy that was injected through the utility. So suppose that the money produced from the solar farm due to its electricity generation is, for example, $2,000, and here it will be with positive sign because it's an income that enters the owner pocket of money. Now to calculate the net income that the owner will receive, here it will be positive $2,000 minus $4,000, which means that the owner will pay $2,000 each month to the utility. And at the first glance you may think that the owner is losing money as he's still paying money. But in fact, the owner has reduced his factory electric bill from $4,000 to only $2,000, and this indeed is a good gain. But suppose now that this farm is producing $7,000 instead of $2,000, and at the same time the factory consumes $5,000 instead of $4,000. So at that moment the net revenue that the owner will take is $7,000 minus $5,000, which is $2,000. And at this time the owner will be gaining money from the farm, not only paying for the factory bill. But you know, this is not a complete picture till now. So let's take a complete simple example to know exactly how the owner will gain money. Here the solar farm has total cost of $200,000, and this cost is the cost of the photovoltaic solar panels and the inverters and any other attachments related to the construction of the solar farm. And also it includes the expected maintenance charges. This is because after a specific period of time there may be some damages in some panels or, for example, in the inverters, so I don't need till now to go in depth on those details as it will be illustrated in details later. So the $200,000 is the total cost. Now the yearly income that this solar farm produces is $60,000, which means that the income per month will be 60 over 12, which is $5,000 per month. Now let's return to the factory to know what are the charges required. Here suppose that the factory bill per year equals to $48,000, which means that the monthly bill is equal to $4,000. That's good. We need now to know when the owner will get the money that he has spent back, as he has spent total $200,000. So the required years for the owner to get his money back is the total cost over the yearly income. So he needs 150 over 60, which is 3.3 years to get this money back. And during this period he will also be paying the factory electric bill because the income is busy now to compensate the total cost. But after those 3 years the owner will have on his pocket the $200,000, which are the costs that he have spent before. So the owner after 3 years is ready to receive money. And because the income is $60,000 and the spent money is $48,000, so the net income will be 60 minus 48, which is $12,000. So the monthly net revenue will be $12,000 over 12 months, which is $1,000. So, at conclusion, the photovoltaic solar farm has enabled the factory owner to pay for his bill for free and also to get an additional revenue of $1,000 monthly. But this is after 3 years of constructing the farm. So that was about the on-grid economic case study, and that's why the solar energy is important from the economic point of view. And on the next tutorial we will see why the solar energy is important but from another point of view. And at this point we are finished. And those are the websites for the photos that we have used. Thank you for watching and see you next tutorial. Hello and welcome everyone. Very happy that we are all together again. In this lecture we will continue asking why the solar systems so fast in your bill, and let's get started. Now, the aim of this tutorial is to know why it's recommended to use the solar system technologies, but from another point of view. As in the previous tutorial, we discussed why the solar systems is recommended according to the economical aspect, but in this tutorial we will see why the solar systems according to the energy aspect by comparing it to other energy sources. So let's go ahead. As we know, the fossil fuels are the most widely used energies in producing electricity, so we will compare the solar system with the fossil fuel to see how the solar system can compete with this popular energy source. But firstly, and for everyone who don't know what is the fossil energy, it's the energy that's produced from a group of fuels that are formed in the earth from dead planets and animals. So fossil energies are similar in that they are extracted from the ground, and it represents the backbone of the energy's consumption, and it's very important till now that it represents about 80% of the energy consumption in 2007, and the other 20% are all of the other energy sources. And because the fossil fuels are extracted from the ground, so it consists of the coal and the gas that is used in the petroleum stations and the natural gas that is used inside our homes. So after this quick introduction to the fossil fuels, let's start comparing it with the solar energy. The first point of comparison is the continuity of each type of them, and we mean by the continuity that which of those types of energy will last us more, or which of them has the sufficient reserve to continue and not run out. And we find that because the fossil fuel is not renewable, or it's not a renewable energy, so it has a fixed storage that will run out after a specific period. And it's clear here from this curve. Here is the relation between the date on years from 1900 to 2100 on the x-axis, and on the y-axis is the consumption of different type of fossil fuels. Here it's clear that the consumption is increasing gradually, which means that there is a great demand on the fossil fuels until it reaches the peak value in 2020. But after the peak, the fossil energy consumption will decay by the time, and the reason is that the fossil energy storage will decrease, so its consumption will decrease until it's about to vanish or run out. On the other hand, and because the solar energy is a renewable one which depends on the sun, so it will not run out, and for this it will be the trend by the time, and its consumption will increase by the passing time in conjunction with the leakage of the fossil energy. So the solar is a renewable while the fossil fuel vanishes by the time. Now the second point of comparison is the environmental effects on each type of them. Here we find that the fossil fuels has many disadvantages or many environmental disadvantages, and one of them is the land degradation. And this is because the fossil fuel is extracted from the ground by making deep holes under the Earth's surface to reach those fuels like petroleum and natural gas. So this drilling in the ground harms it badly and makes some deformations in the Earth's surface like what you see here. On the other hand, the solar energy doesn't have those effects because it's a clean energy and it doesn't harm the environment. Alright. Also, another point is that the fossil fuels may have some leakages in the oil during the extracting operation from the underground or under the sea surface. And this leakage may spoil the seawater and kill the marine life, so the water population is a popular case that the fossil fuel causes, while the solar energy doesn't suffer from any of these disadvantages. And also another defect is that the fossil energy has harmful gases emissions. So those emissions of carbon dioxide gases makes us as humans and other organisms to breathe non-clean air, which produces many diseases and affects the human life. And those emissions of carbon dioxide leads us to another environmental disadvantage, which is the global warming. So the global warming appears as a reason of the accumulation of the populating carbon dioxide gases on the atmosphere of the Earth, So those gases produce something like a layer or a belt of exhausts. And this harmful layer of carbon dioxide gases makes the sun rays to enter the surface of the atmosphere, then reaches the Earth's surface, but those gases prevents the sun rays to go back and reflect from the Earth's surface back to the atmosphere. So as a result, there will be a large amount of heat on the Earth's surface because the rays are not reflected from the Earth's surface and it goes back to the Earth. So the temperature of the Earth will increase unnaturally, and this increase in temperature is called the global warming. But this phenomenon has some bad effects on our world, and it makes some significant changes in the climate nature, and it makes also the temperature get more higher. And when the temperature increases, this will lead to melting the ice on the north and south pole of the Earth, which causes an increase in the water level, and this may cause some floods in some cases. And also the global warming affects the crops cultivation due to the climate changes. So those are some environmental effects of the fossil fuel consumption that doesn't exist in the solar systems because it's a clean energy production. And now the final point of the comparison between the solar and the fossil fuels is the electricity production cost to see which of them is more economic. So the fossil fuels is considered to be more expensive in the electricity production, as the cost per kilowatt hour of electricity generated from the fossil fuels is about 5 cents per kilowatt hour, while the cost of production of the solar energy is about only 3 cents per kilowatt hour. So the fossil fuels are more expensive in production. And this is because the fossil fuel price is growing by the time, as you see here, from 1990 until 2015, the fossil fuel prices increasing gradually. On the other hand, the cost of the solar energy production decreases gradually by the time. So the future will be for the solar energy, and this is because the solar energy is not an energy that has a specific reserve, but it's a technology that is modified and developed by the time, so it becomes less expensive by the time as a result of new development and more popularity that it takes, and more companies that investing in the solar system technologies modifications. So for this, the solar energy becomes less expensive. On the other hand, the fossil is not a technology, but it's a kind of energy that has a specific reserve that will run out by the time. So the less amount of solar energy remains, the more expensive it will be due to its scarcity. So that's good and enough until now, and at this point we have finished. And those are the links for the photos that we have used in this tutorial. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In this tutorial we will start from scratch to design our photovoltaic solar system. But the first step of this design is to understand and detect some angles that we need mainly to make our design. Therefore, we will talk now about some important solar system angles. So fasten your belt and let's get started. The aim of this tutorial is to learn about the declination angle and its design and how to get it. Also, we will learn and understand what is the elevation angle and how to get it. And then we will learn about the tilt angle and its design. So let's go ahead. The first angle is called the declination angle, and easily the declination angle is the angle that lays between the universe axis and the Earth axis. So we suppose that the universe has an axis, but this is just an imaginary fixed axis we suppose related to the other parts in the universe, and also the Earth has an axis. So while the Earth is moving, it tilts with an angle, which is the angle between the Earth's axis and the universe axis. But this angle is not a constant one, as while the Earth is moving around the Sun, its declination angle changes, as the Earth tilts with an angle during its motion, while the universe axis is constant, so the angle between the two axes changes during the time. So let's see what's happening in more details. As we know, the Earth is moving around the Sun in a circular path to complete one cycle each year, so the Earth lasts 1 year to have a complete cycle around the Sun. Therefore, we suppose that this is the Earth's path. It starts moving to make a quarter cycle, then a half cycle, then a three-quarter cycle, and finally a complete cycle to returns to its original position. But during the moving of the Earth around the Sun, it has another type of the movement, which is the tilt or the decline around its center. So at the first position, the Earth is exactly aligned with the universe center, which means that its tilt angle equals to 0, and this occurs exactly at 21 of March. So this is the position of the Earth to have a declination angle of 0, and its positional relation with the Sun causes the climate on the Earth to be at the spring season. And at this condition, the day hours equals to the night hours. Now, while the Earth moves again anti-clockwise around the Sun, its declination angle increases step by step from 0 until it reaches its maximum value, which is 23.5 at 21 July. So during this half quarter, the Earth tilts to the right and its declination angle increases. So this means that the declination angle has a margin to change at it, which is from 0 to 23.5. And for this reason, the summer season comes because of those conditions of having a larger declination angle with respect to the Sun in front of it. And also for this reason, the day at the summer season is larger than the night. So it has a higher number of days hours than the night because the Earth declines with a larger angle that makes the area of the Earth's surface that is exposed to the Sun is larger than the area on the other side or the shadow area. Or in other words, the sun hour increases during the day due to the increased declination angle, then increasing the applied area to the Sun. Now when the Earth moves to another quarter, its declination angle starts to decrease again until it reaches 0 exactly at 21 September, and that causes the weather to be at the autumn season. And it becomes the day equals the night again. So when the Earth is aligned with the universe axis, the declination angle equals 0, and then the area of the Earth that comes in front of the Sun will equal to the other area that is dark or that has the night at the same time. So they will be equal at the same time, and this is also the reason to have a different weather to be in the autumn season. Now when the Earth starts moving again to make a new quarter, it declines again, but now with a negative angle to be declined left, not right, until it reaches the same maximum declination angle at 23.5, but now with a negative sign. So it's minus 23.5 that the Earth reaches exactly at 21 December. And at this condition, the area of the Earth's surface that is applied to the sun rays will be smaller than the area that has the shadow or that is the dark. And for this reason, at this quarter, we are on the winter season because the sun has a smaller effect of its rays on the Earth. So the Earth starts to be cold in the winter season, and this also causes the night to be higher than the day, as the larger area is the dark area. And finally, the Earth moves again to make the last quarter or to make a complete cycle on the Sun. And at this quarter, it declines again, but to right now, not to left. And this makes its declination angle to reach 0 again at 21 March. And at this condition, it will be on the spring season again, and so on. So what we wanted to say is that while the Earth is moving around the Sun, it declines around its center with a declination angle in the margin of minus 23.5 to positive 23.5, passing through 0, and that causes the variation in the seasons and also the day and the night hours variation. But you may ask now, what is the link between this declination angle and our required photovoltaic solar design? So there is a direct relation because when designing the photovoltaic solar system, we need to know what are the number of hours that we will have a solar radiation at them, as the electrical power calculations depends mainly on the number of hours at which the sun rays falls on the solar panels, but those number of hours depends on the declination angle, as we just mentioned. When the declination angle equals 23.5, this will give us the largest number of days hour, then the largest solar radiation, then the largest electrical output power from the solar panels. while on 21 December the declination angle will be minus 23.5, then the number of day hours will be the least during the year, and when the number of solar radiation hours is the least, then we have the lowest output electrical power from the solar station. Alright, now we can ask how to get the declination angle or how it's determined, or how can we detect the Earth declination angle at any day of the year. So we can calculate it easily by this formula. Here it's equal to 23.5 times sine 360 over 365 times d plus 284. Here the only variable in this equation is d, which is the number of days in the year. This is because there is a numbering system for the year days, and it's detected easily by a standard table, and this is a sample of it. For example, at 1 January, the day number will be 1, and at 1 February, the day number will be 1 plus the number of days on January, which is 31 plus 1, which is 32. And now suppose we need to get the declination angle, for example, at 10 February. Here its day number is 41. So we will substitute with 41 in this equation, which will give us a declination angle of minus 14.9 degrees. That's great. Now another angle that is very important to us is the elevation angle, and easily it's equal to the angle between the horizontal plane on the Earth and the sun rays. And to get the horizontal plane, we get the latitude that passes through that point, as the latitude is the horizontal line on the Earth. So suppose that we need to get the elevation angle on that point on the Earth here, for example. So we detect the latitude that this point lays on and plot its line like this one. Then we plot the line from the sun to that point, and this line is the line that represents the sun rays that falls on that point. Then the angle between those two lines, the rays and the latitude, is the elevation angle. But for the same point on the Earth, the elevation angle is not constant. This is because the Earth is moving around its center during the day, so the sun rays changes during the day, and for this reason the elevation angle ranges from 0 to 90 degrees. This is because at the moment of the sunrise, the sun ray will be parallel to the latitude of that point, so the elevation angle at this moment will be 0. And when the sun is vertical over the detected point, the rays will be perpendicular to the latitude, so the elevation angle at this moment will be 90. And also we use the elevation angle in the solar system as the location that we install the solar panel at, which is considered to be a point on the Earth. So we need to know what is the angle of the sun rays that will fall on those panels, as the angle of the rays will affect the total amount of solar radiation on the panels, then affect the total output electrical power on the panels. Now the equation by which we can get the elevation angle is 90 minus the latitude plus the declination angle. So the elevation angle is a function of the latitude and the declination angle. Therefore, in our design, we must detect the latitude of the installing location and its declination angle. That's good. Now the final angle that we will talk about in this tutorial is the tilt angle theta. Here the tilt angle is the angle between the solar panel and the horizontal plane or the ground. And we designed this angle to make it with a value that gives the most benefit of the sunlight. And this will be achieved, or the most benefit will got, when the solar rays are exactly perpendicular to the surface of the panels. For example, if the solar panels are installed at the equator, the tilt angle will equal to 0 because the sun rays are perpendicular to the equator. So we need no angle for the panels, but we need it to be flat with the equator. So it will be parallel to the equator. But when going far away towards the north and the south poles, the angle will increase to compensate the angle that the sun rays makes with respect to the Earth's surface. And for this, the rule we are following in designing the tilt angle is that the solar panels must be in the direction of the equator, or it must face the Earth's equator with its surface. And in this case, we will get the most benefit of the sun, as the sun is perpendicular to the equator. Also, the used formula to calculate the tilt angle is theta. Here theta equals to 90 minus alpha, where alpha is the elevation angle. But you know, In the practical life, we have some standard values for the angle theta to install the panel at which, and those are 15, 20, 25, 30, 45 degree, and 60 degree. So those are some standard values that are popular in the practical life. So if we calculated theta from our design and it becomes 13, for example, from our calculation, we approximate it to P15, which is the nearest standard value. So that was about some important angles that we will use very much in our calculations. And at this point, we have finished. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this very interesting tutorial, we will talk about a very exciting topic, which is the solar radiation and some concepts related to it, which will be very essential to us in our design. So fasten your belt and let's get started. The aim of this tutorial is to know what is the difference between the solar radiation and the solar irradiation, and we will learn also what are the different types of the solar irradiation, and finally we will learn how to calculate the solar irradiation on the solar panels to know exactly what is the most benefit that our solar system can get from the solar energy. So let's go ahead. The first thing which we have is the solar radiation, and the solar radiation is the power that the sun can supply to a specific area on the earth. But this power from the sun is in the form of electromagnetic radiation. So the sun radiation is a kind of the power, and as we know, the power is the available benefit from the sun. So when I say that the power that I get from the generator is 500 kilowatt, so this means that this generator is capable of giving a power or a benefit of 500 kilowatt. And this is regardless to what is exactly the consumed energy. So this is the generator or the sun ability to give me per unit area. And now to understand this concept well, we can compare it with the solar irradiation. Here the solar irradiation is the integration of the solar radiation, or in other words, it's the solar power consumed per a specific period of time. So the solar irradiation is related mainly to the time, as we need to know exactly the amount of power that we have consumed. While in the solar radiation, we were talking about the solar power that it can give us regardless to the consumed power or the real output power. And we must differentiate between the power radiation and the power irradiation, because not all the time in the day we are getting the benefit from the solar radiation. This is because there are some weather conditions during the day that makes it not available to get the most benefit from the solar radiation at all the hours. For example, in a day we will have a maximum solar radiation of 5 hours. Also, there will be another 4 hours of heavy clouds that will prevent that area from receiving the solar radiation. Also, for another 10 hours, the area that will have a night because the earth is rotating, so there will be no solar radiation in the night. So what we wanted to say is that the solar irradiation is the multiplication of the solar radiation with the time, because not all the 24 hours of the day we have a solar radiation. And this is the same idea of the generator when I say that the load that this generator feeds is working for 5 hours per day. So this means that the total energy consumed is 500 kilowatt hour per day. As you see, although the generator power is 100 kilowatt, but the power is not consumed all the day, and it's consumed according to the load. So at conclusion, the difference between the radiation and the irradiation is the same difference between the energy and the power. Now let's see what is the behavior of the solar radiation and the irradiation during the day. Here on the x-axis we have the time, and on the y-axis we have the irradiation from the sun. Now before 6 a.m. there is no sun as we are on the night, so the solar radiation at this condition is 0. And starting from 6 a.m. to 12 a.m., the solar radiation will increase gradually to reach its maximum value at 12 a.m. And the maximum value is good at this time because the sun will be exactly perpendicular to the earth, or it will be perpendicular to your location at this time. And when the sun rays are perpendicular to the earth, this gives us the highest radiation. Now, after the peak value, the solar radiation will start to decrease gradually as the sun rays starts to decline step by step until the sun rays are parallel to the earth. Then the sun will disappear to get in the night, at which there is no sun, so there is no solar radiation. Now this is the difference between the radiation and the irradiation gradually, as the solar radiation is this orange curve here, while the solar irradiation is the area under the curve or the integration of the solar radiation during the time. So not all the day the sun is shining, or in other words, the irradiation has a specific period of time to have the radiation at which. But do you know, the solar irradiation itself hasn't only one type, as it consists of 4 types. The first one is called the direct horizontal irradiation, and at this type the irradiation is the irradiation that goes directly from the sun to the earth with no losses. So the solar irradiation faces no obstacle that prevents it from going to the earth directly, and it doesn't absorb it by any object. It just goes perpendicularly with an angle of 90 degrees and directly to the earth. Now the second type of the irradiation is the diffusion horizontal irradiation. And at this type the solar rays faces some obstacle through its way, like the clouds for example, or the atmosphere, so those obstacles absorb some of the solar rays energy and it reflects some other rays. So if the rays from the sun comes projected perpendicularly to the earth, when it faces some obstacle like the cloud, it will be scattered or it will fall on the earth with a declined or a tilt angle. So those types of the irradiation is caused when the rays faces, for example, some clouds or rains or mountains that reflects the sun rays. Now the third type of the irradiation is called the global horizontal irradiation, or its simple as S sub H, and it's nothing but the collection of the direct and the diffusion horizontal irradiation. So its name is global irradiation that contains 2 types of the irradiation. For example, some rays are falling directly to the earth and some other rays are scattered as they faces the cloud through their path. So the collection of those irradiation to the earth is the global horizontal irradiation. And this S sub H is very important type of the irradiation as we made our design according to it. So the global horizontal irradiation is a fixed value for each place on the earth, and we get its value each month from some standard tables. And it's logically to make our design on the global irradiation because not only the direct rays that falls on the solar panels, but also the diffused rays participate in falling on the solar panels. So those horizontal irradiation are supposed to fall directly on the earth with an angle of 90 degrees. And this will happen on the peak time of the place only, while the rest of the day the solar rays will fall on a specific area of the earth with a smaller angle of 90 degrees. Which means that there will be a smaller effect from the sun rays on the earth, as the effect is maximized for the perpendicular rays only. And as we mentioned on the previous tutorial, the equator of the earth is a special case as it's perpendicular to the sun rays at any time because its latitude is 0, while when going up and down the latitude angle increase until we reach 90 degrees at the north and the south poles. So for this reason the solar rays are not perpendicular to the earth's surface except the equator line. So at conclusion, at the equator we will get the most benefit of the solar rays, while when going up and down the solar rays starts to deviate or decline due to the deviated nature of the earth. So this is about the solar rays, and on the next tutorial we will illustrate the final type of the solar irradiation, which is the most important type as it's related to the design of the solar panels itself. Now I think that's enough for this tutorial. Hope that's it right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial we started talking about the solar irradiation types and the difference between the irradiation and the irradiation. And in this tutorial we will continue this exciting topic. So fasten your belt and let's get started. Now in this tutorial we will continue talking about the irradiation types, as we illustrated the first three types, which was the direct horizontal irradiation, the diffusion horizontal, and the global horizontal irradiation. And now this is the time for the last type, which is the global tilted irradiation. And the global tilted irradiation is similar to the horizontal irradiation in that both of them are a global type, which means that they consist of a direct and the diffusion irradiation. But the difference in that in the global horizontal, the falling rays are supposed to fall on the horizontal surface of the Earth, while at this time the global tilted rays are falling on a tilted or a declined surface, not a horizontal one. And we suppose of this tilted surface to be the solar panel itself. And it's logically to have this type of the irradiation because the solar panels are installed with a tilting angle theta, as we mentioned before. So we must analyze the irradiation that falls on the solar panel, as we must know what will be the amount of irradiation that our panel will receive. And here it's simple as S sub m, which is the irradiation for the module. But you may ask now, why we need to install the panels with a specific tilting angle theta? So this is because we need the solar rays to fall on the panels vertically with an angle of 90 degrees, because we get the most benefit when the rays are perpendicular to the panel. But the problem now is that the Earth's surface takes a sphere shape like this one here. So the solar rays will be vertical to the Earth only at the equator of the Earth. And for this reason we install the panel on the equator to be flat to the Earth's surface, which means that the tilt angle at this condition will be 0. And this means also at the equator S sub m will equal S sub h, so that the tilted irradiation equal the global horizontal irradiation. But when going up and down, we start to decline, or the Earth starts to decline gradually to have an angle according to its latitude from 0 to 90 degrees. And for this reason, the solar panels must be installed with the same angle, but in the opposite direction to compensate the declination angle. So the solar panels will be installed with an angle theta that makes S sub m at the point not equal S sub h, as S sub h is perpendicular to the Earth's surface, while S sub m is perpendicular to the panel's surface. Now let's see how to calculate those global tilted irradiation S sub m to make our design according to them. Here we suppose that this is the solar panel and this is the horizontal plane on the Earth. Now the panels is installed with an angle theta, which is the tilted angle. Now suppose that this is the falling solar rays on the ground, which is called S incident. So as we learned before, the angle alpha is that angle between the ground level and the incident rays. Now suppose also that S sub m, or the module irradiation, is this one, and it must be perpendicular to the solar panels, as by definition S sub m is the solar rays that are perpendicular to the solar panels itself. Also suppose that this is the horizontal irradiation S sub h, and by definition also it's the rays that falls perpendicular to the Earth's surface. Now we need to get the value of S sub m, as its value is very important for us, now. So we need to make a relation between the horizontal irradiation and the tilted irradiation. As the horizontal irradiation is a known value for each place on the Earth, so it's a known value. That's good. Now from the trigonometric laws we can say that this angle is equal to this angle alpha, as those two green dashed lines are two parallel lines that have the same intersecting line, which is the incident ray. Also this angle will be the same, or will have the same angle theta, as those are two parallel lines having the same intersecting line with the panel itself. Now let's focus on this triangle here, as it's a right triangle which has a 90-degree angle. So the horizontal radiation S sub h is this line that is in front of the angle alpha. So it's equal to the incident radiation times sine alpha. Now let's focus on another triangle, which is this triangle here. So at this condition, the module irradiation lines is in front of the angle alpha plus beta. So it's equal to the incident line times sine the front angle, which is alpha plus beta. Now when substituting from the first equation and the second equation, pi the incident irradiation to P the global horizontal irradiation over sine alpha, so the module irradiation or the global tilted radiation finally equals the global horizontal irradiation times sine alpha plus beta over sine alpha. That's good. But you may now need to know what is exactly the S sub m means for us, or what is the type of the quantity that we will handle during the solar design. So what is the S sub m? As all what we said about S sub m is that it's the irradiation from the sun, or it's the energy consumed through a specific period of time. Or it's the solar radiation at a specific period of time. But the problem now is that we are talking about the solar radiation in general for the place, as we are handling with the solar system that consists of a number of panels, and according to the panel's capacity or the panel's number, there will be a solar radiation. So the more the number of panels, the more the radiation from the sun. And this means for us that the radiation is a property determined by the existing case of the solar design. So the radiation is not a general parameter for us to specify the energy coming from the sun. And for this, to have a general parameter to describe the energy coming from the sun, we use only the number of hours at which we have the radiation at it. So starting from now, we will describe S sub m by the number of radiating hours from the sun. Therefore, we can say that S sub m is the number of hours at which we have a net radiation from the sun on the panels. And for this, we can exclude from the 20 hours in the day, the night hours and the cloud hours and the rain hours. But we take only the number of hours for the radiation or for the net radiation from the sun. And as we know previously, the radiation from the sun varies greatly during the day, so the net number of radiation hour has a variation in the solar radiation due to the changing angle of the solar rays on the panels. And for this reason, we have a curve like this one with a peak value at 12 p.m. and it decays before and after 12 p.m. So this means we cannot talk about a specific number of hours that have a specific radiation, as the radiation changes during the time as you see in this curve. So for this reason we come up with another definition for the S sub m, which is the peak sun hours. But you may wonder now, how S sub m to be the peak hours although we have a peak value of the radiation only at the maximum point? So that comes easily by making a small trick here to replace those two blue areas lays down here by those two areas up here. So we replace this curved blue area by those orange areas. And then we can have this triangle area that represents the solar irradiation. And by this solution, we can convert the radiation from a variable function with the time to be a fixed function with the time that has a fixed peak value during the day. And physically, this means that we have only a radiation from 9 p.m. to 3 a.m. But this radiation is the maximum radiation, as it has a fixed peak value as you see. Now the last thing we have is to know how to get the most benefit from the solar radiation. So we know well that the best radiation is got when the falling rays on the panels are perpendicular to it. But we have just known that the actual falling rays are the incident, while the perpendicular falling rays are the S module. So if we manage to make the incident rays equals to the module rays, at this condition all the falling rays on the module will be perpendicular to it. So to represent this mathematically, S module equal S incident. But we have known that the S module equal the S incident times sine alpha plus beta. So when substituting, we will have S module equal S module times sine alpha plus beta. So S module will be cancelled with S module, which means that sine alpha plus beta equals to 1. And this means also alpha plus beta equals to 90 degrees. So at this condition, beta now equals 90 minus alpha. So physically, this means that if we need the falling solar rays on the solar panel to be perpendicular to the panel surface, we must install the panels with an angle on the ground level that equals 90 minus the elevation angle. And this is the tilted angle equation that we talked about before. So this is about the peaks and hours, or the S sub M, and its design. Now I think that's enough for this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In this tutorial we will start arranging all the steps that we have illustrated before and some steps to make any solar system design. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to understand some general steps you must follow to make your solar system design, and we will represent those steps in some forms of a practical example. So let's go ahead. The first step we have in the design is to detect the coordination of the place we are making the solar design at which. So those coordinations are represented by the place latitude and longitude. And for example, we suppose we are making a design in New York. So to get the coordinations of New York or of any location in the world, there is some beautiful online websites that you can use for this purpose. Now one of them is called the latlong.net. So this is its hyperlink and here we can check it. As you see, this is the website, and all what we need to do is to type the location name in this bar. Then its coordination will appear to you. So let's type, for example, New York, and press enter. Here it appears that its coordination is 40 for the latitude and minus 74 for the longitude. So let's go back. That's good. After getting the latitude and the longitude, the next step is to get the tilt angle theta, that is the installing angle of the panels on the ground. And as we learned before, theta equals 90 minus the elevation angle, but the elevation angle is still unknown now. So for alpha, it's equal 90 minus the latitude plus the declination angle. So we just have calculated the latitude, but we need to calculate the declination angle itself. So this is the declination angle formula, and we knew that it depends mainly on the day number on the year that we need to detect the Earth declination at which. Now we need to select the day that has the worst solar radiation in the year. And this is because we must make our design on the worst case, because if we made the design on the worst case, the design at this condition will be able to cope any other cases. But if we made the design on the best case, at this condition when the solar radiation becomes fewer at any day, this will give us a smaller output electrical power that will not be sufficient to feed the electrical loads. So by selecting the worst case, we can increase the number of solar panels to get the required output power. But we know also that the worst radiation in the year is coming at 21 of December. So when searching the days table, we will find that this is 21 December. And here this is the intersection that gives us a day number of 355. Now when substituting by this 355 to get the declination angle, it will be minus 23.5. So this is the worst declination angle in the world that gives the worst solar radiation. So when substituting back in the elevation angle, it will be 26.5, and then when substituting back in the theta, it will be 63.5. But as we said before, the tilt angle has some standard values according to the manufacturing standards, so the nearest standard to it is 60 degrees. So this is the second step required, which is the installing angle of the panels. Now the third step is to get the S sub M, or the peaks and hours, and to get it we must firstly calculate it for each single month separately. As we know, the solar radiation differs from one month to the other, so we will firstly calculate it each month. So S sub M depends on the global horizontal radiation, so we must calculate S sub H each month. And this value, S sub H, is a given value that some scientific organizations are collecting. So the S sub H is detected at each point on the Earth. So we will get it from the NASA database, as NASA provides us with a global horizontal irradiation values for each coordination on the Earth. So what we just need to know is the location, latitude, and the longitude that we just have got, and then enter the NASA database, then get the value of S of H each month. Now this value for each month is the average of the month's day, as the average of the month day is. As we know, each day of the month has a different value of S of H. So this value that we will get is the average value for each month. Now the second thing we need for getting the S of M is the tilt angle theta. But as it's a constant value, so we will use it to be a fixed angle that we got. Also, we will get the declination angle at 21 December, and then we need to get the elevation angle that depends on the declination angle, and we got it at 21 December. Now, after getting S of H, theta, and alpha, we are ready to get SM. But you know, this is an approximate assumption to get alpha at only one day in the month, which is 21 December. And the most accurate solution is to get alpha each day in the month. Then we get the peaks and hours each day, and after that we get the average of all days in the month to get each month peaks and hours. But for now we will try this assumption, as it's more simpler in the calculations. And later we can try the accurate solution by getting S of M each day in the month. Now we need to get S of M each month, so we must calculate it 12 times, but for the illustration purpose, we will take two examples for January and February. So those are the global horizontal irradiation for New York each month, and here is a screenshot from the values that we need. Here for January, the S of H equals 1.97 hours, then theta equals 60, and the declination at 21 of January, so the day number is 21, then it will be minus 20.1 degree. Now the elevation angle of 21 January is 90 minus the latitude, which is 40, plus the declination angle, which is minus 20.1, so alpha equals 29.9 degree. And finally, we get the S of M to be S of H times sine alpha plus beta over sine alpha. So it's equal 3.95 hours. Now let's repeat those steps fast for February. Here S of H equals 2.86 hours, then theta equals 60, and the declination angle for 21 February equal minus 11.2, then alpha equals 38.3 degree. So the global tilted irradiation at this condition equals 4.5 hours. That's great. Now we will do the same thing for the rest of the 12 months, and for this we have prepared all the required values for the 12 months. So those are the required parameters at each month. Here we have S of H given from the database of NASA, then theta is a fixed value at all of the design, then the declination angle is determined at 21 of each month, and alpha is determined each month also according to the declination. Then S of M is determined each month according to the above data. And finally, we get the average value of all of the months of S of M. But you can ask, will we take the average value of the S of M to be the global tilted irradiation or the final value of the global tilted irradiation? So this depends mainly on something. Here, the difference between the maximum value we got for S of M and the minimum value is greater than 2 hours. So if the difference is greater than 2 hours, we will choose S of M to be the minimum. And if the difference between them is less than 2 hours, we will choose it to be the average value of all of the months. And here for our case, the minimum value is 3.86 and the maximum value is 5.38. So the difference between them is 1.5 hours, which is less than 2 hours. And for this condition, we will choose the average value, which is the summation of all the months' value over 12. So it will be 4.6 hour, which is the final value of the global tilted irradiation hours. So by this way, we can get the final value of the net hours at which we will get a maximum radiation from the solar panels, then the maximum electrical power that we need to feed our loads with it. So at this point, we have finished. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. This is a very special tutorial at which we will learn how to make an Excel program that can make all the required solar design calculations automatically. So when you make your own solar Excel program, this will shorten many tiring manual steps and calculations, as all things will be done automatically. Only you just need to enter the new data for the new design case and the program will make all the required steps. Now let's create a new Excel file. Here right click and new, then Excel file, and let's rename it to the solar design. Now let's open it. Here we have this blank Excel sheet, and now let's start with the columns, as we need a column for each month. So we will make our calculation each month like what we just did on the previous tutorial with the month staple, but here we have some little changes in our design. So let's type here Now let's select all of those cells by pressing on the first one of them, then press Shift, and then press the right arrow here, the right arrow on your keyboard, so you can select all of them. And after this, we can press on this border tab here, and then we need to make borders for all of those cells. So we will press on this all border. Also, we can choose the fill color tab for each cell. So to fill all of those cells, we can select them again, and then press on this tab here. And then let's make the color to be this one, for example, and it will be more pretty to change the font to be white, for example. So let's press on this font and let's make it to PY, and also we can change the font style, for example. So let's make it to be, for example, Century Gothic. Here that one is more pretty, and it will be more pretty and clear also to increase the font size to be, for example, 26. Then we can increase each cell width. That's good. Now let's move to the rows. So let's make a cell and call it parameters. Here let's select it and make it to be parameters, and quickly we can give it the same format for those months format. So let's press on this cell, for example, and this press on format painter, and then press on this cell. So the cell has taken the same format. Let's increase its width, and also we can decrease its size here by Control A and make it 24, for example, and we can distinguish between this cell and the month cells, so we can fill it with another color. Here let's make it to be this color, for example. Now the first parameter we have is the same as what we did in the previous tutorial. Here it's the peaks an hour, or S sub H. So let's make it to be S sub H, and let's give it the same format of the parameter cell, so format painter, and then give it the same format. Now we can make this H to be subscripted, and also let's center the content of this cell, so that's good. Also we can distinguish between this cell and the parameter cell by filling it with another color, so this green color may be more better. And also we need to copy the peaks and hours for each month from the nested database. So let's open the text file for the nested database. Here this is the text file that contains all the peaks and hour values for all points or locations in the world. Here the latitude and the longitude and the corresponding values for each month, January, February, and so on. So those are the peaks and hour values corresponding to each point in the world. And for us now, we can work on the same example of the previous tutorial, which is the New York. As New York has a latitude of 40 and a longitude of -74, so we can search in this text file as it's very large. And here press Ctrl and F, then type 40 and -74, then press enter. So this is -40 and -74, but what we need is 40 and -74, so we can press enter again, and here we go. This is the value that we need. Here we find that this is 40 and -74, and those are the corresponding values for the peaks an hour for each month of them. Now we can copy them by a right click and copy, And let's jump back to the Excel file, and here we can select all of those 12 cells here from January to December, and then press Ctrl and V. So press OK, and now let's press and Ctrl, use text import weathered, and press next, and finish. So those are the values of the peaks and hours for each month. Now let's format those cells again. Here let's select them, and let's make them in the font 14 and pull them, and then let's make them to be Century Gothic also. Now let's move to the second parameter, which is the latitude. So we can type latitude on the next cell here, and then we can give this cell the same format of the upper one. So format painter, and let's make it here, so that's good. And as the latitude we are using is 40, so let's type here 40 on this cell, but here we need to enter it as an equation. So any equation in Excel must start with the equal sign. So here we type equal 40 and then enter. Now let's give it the same format of this cell. Now we need all the other cells here from February to December to have the same value of the first cell, which is January. So we need to refer all the other cells to the first cell. And to do so, we need to refer first here this second cell to be equal this first cell here. So let's select this cell, and here in the upper left we will find that its address is G7. So let's select this second cell and type equal and G7 and press enter. So by this way we have made this second cell to be equal to this first cell. Now to make all the other cells equals to the first cell, we can access each one of them and type the address of the first one here, which was G7. But you know, this is a very tiring operation to access each one of them manually. And we have a very easier way to assign all the other cells to the first cell. Here we can select this cell and go to the bottom of it, so you can note that we have a plus sign here, and then we can press a left click, then drag with the mouse to select all of the other cells. So we press a left click and then drag. And by this way we have made it, so you can see that it's automatically all the other cells is assigned to the second cell, but the second cell itself is assigned to the first cell. So we can say that all the other cells is assigned to the first cell. And the benefit of this method is that if we change the first cell value, all the other cells will be changed. So we don't need to change each cell separately if we are working on another design or for another location. Here let's try by typing, for example, instead of 40, let's type 50 and press enter. So you can note that all the other values has been changed. So we are making this design compatible for any design. So if you are working on any location, you just need only to type here its latitude and all the other values will be changed. So that's what we need. Now let's make it back to P40 and press enter, and let's format the rest of those cells to P with the same value of this first cells. So we select this cell, then format painter, then let's drag by left click, then move with the mouse. So we have formatted them to P with the same format. Now let's repeat those cells exactly with no change for the longitude, and then let's give it the same format of this one here, format painter, and that's good. Now our latitude is -74, so we type equal -74 and press enter. Then we select it and we find that its address is G8. We can go to this cell and press equal and G8, then press enter. Now we can select this cell and drag to all the other cells. That's good. Let's give it the same format. Now the next parameter is the day number, and we will make the design for each month on the World Solar Radiation Day, which is 21 of each month. So let's type here day number. So we have copied each day number for a short time. So let's select those 12 cells and press Ctrl V. Here 21 of January is 21, 21 for February is 52, 21 for March is 80, and so on. So that's good and enough for this tutorial, and on the next tutorials we will continue our Excel program. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. And this tutorial will continue constructing our solar system program on the Excel sheet that we have just started on the previous tutorial. So on the previous tutorial we designed the rows of the peaks and hours, of the latitude and the longitude and the day numbers at 21 December of each month. And now let's continue with the next row, which is the declination angle at 21 of each month. And for this we type here the declination. Now each cell of those 12 cells will be assigned to the declination angle equation. So let's zoom firstly, and then let's get our cell. And here we can type equal 23.5 times sine, and then two parentheses, and 360 over 365, and then times, and here another parentheses, and 284 plus. So we will assign now the day number automatically by the day number address, as we are calculating it for January. So it's 21 January. So let's access this cell to see its address. So the cell address is G9. Here it's assigned automatically, and then close the parentheses. So this is the equation of the declination angle. But there is a note here. The Excel equations handle any angle like the angle inside the sine here to P in the radian. So we need to convert it from the radian system to the degree system. And for this we multiply this angle with pi, which is 3.14 or 22 over 7. Then over 180. So we type here 22 over 7 and then over 180. Now let's close this parentheses and let's press enter. That's good. Now after assigning the declination angle of January, we need to assign it for the rest of the months. And as we did in the previous tutorial, we will drag from the first cell here to the last cell. But at first let's zoom out. And now let's drag here, go to the bottom of the cell, and then drag by the left click and go with the mouse. So those are all of the values, and now we can give them the same format of this cell here, format painter. And let's take from this one to this one. That's good. Here this job was done automatically, so this is the benefit of the Excel, that we enter the equation only one time, and for the repeated calculation it will be done automatically. Now let's move to the elevation angle for each of the months. Here we type elevation and then enter. Then its equation is 90 minus the latitude plus the declination angle. Here we type equal 90 minus G7 plus G10 and press OK. Also we do the same thing for the rest of the months by drag only and then format them. So format painter, and for this one also let's drag all of those. So those are the elevation angles of each month according to the declination angle at each month. Also we need to find the installation angle of the panels on the ground, which is beta. So let's type here beta and enter. And if you remember, beta was equal 90 minus the elevation angle alpha. But don't forget that we are not calculating beta each month. This is because beta has a fixed installation angle all the year. So we calculate it only at one time or only at one case, which is the worst case in the year. And as we know, the worst solar radiation day is at 21 December, so we must calculate beta just at 21 December, which means that we must take the elevation angle at 21 December, as beta depends on the elevation angle. So here this is the cell at which we calculated the elevation angle at 21 December, and its address is R11. And for this we type here equal 90 minus R11 and enter. So that's the calculated value of the beta. Now for the rest of the cells, we will not drag from the first one to the final one, as the drag will make the rest of the cells to have the same pattern of the first cell or the same equation, but changing the variable into it. So the variable R11 will be changed if we drag from the first one to the last one. Here let's try that. we can find that at the next cell we have here S11, and here we will have T11, and here we will have U11, and so on. So this is the wrong way. Let's make Control Z. Now for the rest of the cells, we must make it to take the same value of the first value of beta here. This is as we said before, because beta is constant. So we apply the same idea as we just made in the previous tutorial in the latitude and the longitude cells. Here we can assign the second cell to P the first cell, or to P equal the first cell. So let's type equal and the first cell here. So when we access H, we will find that the next cell at February will have the same value. Now press enter. That's good. The second cell have taken the value of the first cell. Now we can drag the rest of the cells. So let's drag the rest of them. And here we can see that the rest of the cells has taken the same value of the first cell. So let's format them also. Now we need to see what is the actual and installation angle beta, as this angle beta is the calculation value or the calculated value. So let's type here beta calculations and then increase the cell width. But now we need to detect the standard angle of the beta, which we will pi the solar panel stand according to it. Here we say that it will be 60, as it's the nearest standard value to the value which we have got here, 63. So the nearest value of 63 is 60. And this is totally true. But you know, we don't need each time to detect the standard value of the beta and assign it to the table. Here we are making a full automated design, and we just need to enter the data and get all the results automatically. So we need the program to detect the standard value of beta automatically, and for this we will use an if condition in the program. So if the beta calculated we have got is in a specific range, we will put it with a specific standard value. And if it lays in another range, we will put it to another standard value, and so on. Therefore, if you remember, the standard installation values of beta were 15, 30, 45, and 60. And for this, we will type here beta, but now it's not the calculation, it's the design. So design. So this is the designing value of the beta that we will enter now. Now let's zoom in. Here, this is our cell. Let's type equal. Then we use an if condition in the Excel software. So we can type here if G12 smaller than 7.5 and then a comma and then 0. So what's typed before the comma here is the condition, and what's typed after the comma is the order that we will apply if the condition is right. So this comma means that if the beta designed is less than 7.5 degree, we put it to P0, as here we assign it to P0, which means that we are installing the panels to be parallel to the Earth's surface. And this what will happen in the countries that lay on the Earth quarter or near to it. Now we type another comma, then the comment that will be after the comma will be applied if the condition is false. So if the calculated beta is larger than 7.5, the next order will be applied. Now let's type here another if, and then a parenthesis, and then and a parenthesis, and G12 is larger than 7.5, and then comma, and then G12 is less than 22, and then close the parentheses, and then another comma, and then 15. So this if and means that if the two conditions are true at the same time, so if the calculated beta is larger than 7.5 and at the same time it's less than 22 degree, at this condition we will apply the order after the comma, which is to put the value of beta or assign it to P15. So in other words, this means that to put the value of beta with a standard value of 15 if the design value ranges from 7.5 to 22 degree. But if this condition also is not true or it's false, what will be applied as the next condition after the comma. So after the comma here, let's make another comma, and then let's copy this F and let's paste it here. Then we can change this 7.5 to P22, and let's change this 22 to P37. So this means if beta designed ranges from 22 degree to 37 degree, we install the panels with a standard value of 30 degree. Also, we can repeat the same thing if this condition which we have just typed is false. So if this condition is false, we can have another condition after the comma. So let's paste the same format here. And let's change this 7.5 and put it to P37, and then change this 22 and put it with 52, and then change this 15 and make it with 45. So this means if the calculated value of beta is nearer to the 45, or if it's in a range that is nearer to the 45, which is from 37 to 52, we will put it, or we will assign it to a standard value, which we will pipe the solar stands with it to P45. Now the final condition is that if beta calculated is larger than 52, so it will be nearer to the 60 degree, so we put it with 60 degree. And for this we can type another comma and then another F and a parenthesis, and G12 is larger than 52, and then another comma and 60, and then we need to have a 5 parentheses, 1, 2, 3, 4, and 5, and then press enter. Great! It appears here with 60 as the calculated value in our case is larger than 52. So the if condition works well. Now let's apply that on the other cell by assigning the second cell value to the first cell. Here we can type equal and then access this cell, so we make it to P equal G13 and press enter. Then we can drag the rest of the cells, so let's zoom out and then drag those cells. So the other cells have taken the value of the second cell, but the second cell exactly takes the value of the first cell. But we need to check that if all of the conditions inside beta are working well. So let's change the value here to force it to P, for example, with 5 degree and press enter. That's good. It appears here with 0 because 5 is less than 7.5. Also, we can make it to P10, for example. Here, let's make it to P10. And here it appears with 15 as 10 is larger than 7.5. Also, we can try 25. So it appears with 30 as 25 is larger than 22 in this condition. Let's try 47. So it appears with 45 and so on. Now I think that's enough for this tutorial till now, and on the next tutorial we will continue constructing the Excel design with the last step to finish our program. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will continue our solar Excel program to finish it. As in the last couple of tutorials, we learned how to get the peaks and hours, the latitude and the longitude. Also we got the day number at 21 of each month, and we learned how to enter the equations of the declination, the elevation angles, and finally the tilted angle beta. So we got beta calculations and we learned how to get the beta designed. And now this is the time to get the value of the peaks and hours. As this is our main target of the design, is to get the number of hours that we will get the most benefit from the design at which. Now we will start with the peaks and hours at each month, and we know that it depends on the elevation angle, which varies from one month to the other, and also it depends on the tilted angle, which is fixed through the year. And if you remember also, the peaks and hour equation equal the SH times sine alpha plus beta over sine alpha. So let's start getting it. Here we type SM and enter and access this cell, but firstly let's give it the format of this cell, so format painter, and this cell here, that's good. Now we can type equal and select S sub H for January, and then times sine, and select the elevation, and after that plus, and then select the declination design, and a parentheses, and then times 3.14 over 180, and a parentheses, and then over sine, and select the elevation times 3.14 over 180 and close the parentheses and then press enter. So this is the peaks an hour value for January, and what we did here is that we access G6 above here, which is the S sub H for January, and we multiply it by sine G11, which is the elevation angle, plus G13, which is the peta design, and also we multiply the angle by 3.14, which is pi over 180, so this term pi over 180 for converting the angle from the radian system to the degree system. And then we divided this term pi sine alpha, here G11 is alpha or the elevation angle, so by this way we can get the peaks an hour value, which is S sub m. That's good. Here as you see it's a 3.9, and it's actually the number of hours that we get the most solar radiation from these cells at which in January. Now we can apply the same formula on the other cells for all other methods just by dragging the cell until the December cell. That's good, it's done well now. You can compare those values of the peaks and hours of each month to the values that we just got on the previous manual tutorial, so you will find that they are approximately the same. But now we need to know what is the value that we will work on for the peaks an hour, as we have got 12 values. So which of those values that we will work on? And as we learned on the manual example, we must apply the condition that says if the difference between the peaks and hours of the lowest and the largest months is less than 2 hours, we assume at this condition that the final value of Sm to be the medium of all of the values of the 12 months. So we get the medium in case of the difference between the largest and the lowest is less than 2 hours. But in case of we have the difference between the largest and the lowest value of Sm is larger than 2 hours, so we will use the lowest value to be the peaks an hour at this condition. So those are the two conditions that we have, and to apply that job on the Excel, we need firstly to detect the minimum and the maximum values of the peaks and hours, and for this we will type Sm many and press enter, then access this cell, and we can select all of those cells, so we need to merge them as we will make this cell to take the area of all of those cells. So we will press merge and center, and also let's change its font to P, for example 14, and its font style to P Century Gothic, and we can pull it also. Now that's good. Now we will type equal and then many and in parentheses. Now what we will do is to drag from this cell here to the last cell and then another parentheses and press enter. So what we did here is that we use a function embedded in the Excel which is called the many, that can detect the cell that has the minimum value from a range of cells. So we range it from January to December, and it detected the minimum value as you see here to be 3.87, which has the peaks and hours of the December cell. So this is the peaks and hour of the December as you see here. Now after detecting the minimum value, we need to detect the maximum value. So for this we type here Sm and then max and press enter. Then we can select this cell and format painter and give those cells the same format. That's good. Now we can type equal max and in parentheses and start from this cell and drag to this last cell and then another parentheses and press enter. So by this way we can detect the maximum value. As you see, we got the maximum value of September, which is 5.39 hours. So 5.39 is actually the value of September, which is the maximum value of those 12 months. So what we did is only to replace the minimum function with the maximum function. Here we have selected the minimum function, and here we have selected the maximum function. So it's very easy. Alright. Now after getting the minimum and the maximum peaks and hours, we need to get the final value that we will use in our design. And for this we will type here, let's type peak sun hours and press enter. Then let's merge those cells. Here, merge in center. And also we can give it the size of 36, for example, and we can fill it to P red, and let's make the font color to P with white, and we can use Century Gothic. That's good. Then we can type here if and a double parentheses and G16 minus G15 in a parentheses, and then lower than 2 hours, and then a comma, and then average, and then select also and press enter. So that's good. So this comment means that the difference between the maximum SM, which is G16, and the minimum SM, which is G15, is less than 2 hours. So this is the comment of less than 2 hours. At this condition, we will set the peak sun hour value to be the average value of the 12 months. So this is the average from G14 to R14. Here this is G14 and this is R14. We will select the average between them. But if this condition is true, which is G16 minus G15 is not less than 2 hours, so it's greater than 2 hours, at this condition we will set the peak sun hour value to be G15 itself, which is the S minimum. And those here are the three parameters or the three parts of the if condition. The first one is the part that before the comma, which is the condition itself that we need to check, and the second part is the one after the comma, which we will apply if the condition is achieved or it's true, and the third part is this one after the second comma, which will be achieved if the condition is false. So by this way we managed to make an Excel program that is able to make any required calculation for any solar system design automatically without the need of those tiring calculations. For example, if we change the latitude here, let's make it to P50 instead of 40. So you will see that all the other calculations or the rest of the calculations has been changed. Here the peak sun hour has changed, the S minimum, the S maximum, and so on. So by changing only the input of the program, the output will be changed automatically without the need to recalculate your design or to retry the calculation from the first step till the last step. Here it's done automatically. Now let's make Ctrl Z, so the value has changed back to its original condition, which is 4.6 value of the peak sun hour. And you can notice that 4.6 is the average value between all of those 12 values. This is because the difference between 5.3 and 3.8 is less than 2 hours. So as it's less than 2 hours, the program has changed the average value to be the peak sun hour that we will use. So our if condition now works well. Now I think that's enough for this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. Today we will take a tour on the different solar system technologies. So fasten your pull and let's get started. The aim of this tutorial is to take an overview on the solar system technologies which are used to convert the solar energy into electricity. So let's go ahead. There are three main types of the solar energy technologies. The first one is the photovoltaic, which is known as the PV, and the second one is the concentrated photovoltaic, which is called as the CPV, and the third one is the concentrated solar power, which has an abbreviation of CSP. So let's start to talk about each of them in more details. Here we have the first part, which has the PV or the photovoltaic. So the photovoltaic is a process of converting the sunlight directly to an electrical energy by using the solar panels. As we know, when the sun shines into the solar panels, some photons from the sunlight are absorbed by the cells or the solar panels, which creates an electric field across the layers and causes the electricity to follow, as we explained on the previous tutorial. But note that this technology depends on the amount of sunlight, not the heat. And this means when the solar radiation that falls on the panels increases, the number of free electrons will increase and the production of electricity will increase. But when the solar radiation is weak, the number of free electrons will decrease and the production of electricity will decrease also. On the other hand, when the temperature increases, the panel's efficiency decreases and the produced electricity will decrease. And that's against a lot of people think, as a lot of people think that when the temperature increases, the solar panels will be able to produce more electricity. But this is wrong, because the increasing of the temperature has a negative effect on the solar panels. And you know, this is the reason that makes some very cold countries to have a huge electricity production of the solar energy. And we will know the reason of that in more details in the next tutorials. Now the main components of the PV solar systems are that the solar panels, which converts the sunlight to a direct current, and in this tutorial we will explain the solar panels in more details and know its types. Also, we have the charger controller, which regulates the current and the voltage that the PV modules feeds into the batteries to avoid overcharging the batteries, and it can measure how much the battery is charged to be able to charge the battery when we need and stop charging it when the batteries are fully charged. Then we have the batteries that are used to store the energy generated by the solar panels to be used at the night or when the sun disappeared, because almost we need the electricity at every time. After that we have the inverters, and we know that the solar panels generate a direct current or a DC electricity, not an AC one, but our home appliances are working on the AC devices, so the inverters is used to convert the DC electricity into the AC electricity that are used in our home. So that's about the PV system. Now for the CPV, it's a photovoltaic technology also, but it has a different way for its working operation, as the CPV uses some lenses or some curved mirrors to focus the sunlight into some small and highly efficient solar cells. And the CPV systems often uses a solar tracker and sometimes a cooling system to further increase their efficiency. So the system is more efficient than the PV one. And it also requires a less area and a less solar panels to produce the same amount of electricity than if we are using the traditional PV system. But you know, the lenses used in the CPV are very expensive, so this technology is very expensive, or it costs us higher money than the PV system. Now the final technology we have is the CPS, or the concentrated solar power, and this technology converts the sunlight into some forms of heat to produce the electricity. But at this technology we are using some mirrors to reflect the concentrated sunlight into the receivers that heats a high temperature fluid, which is used to spin a turbine or a power engine that drives the generator. And finally we produce the electricity. And this type is used primarily in the very large power plants, and it's not appropriate for a residential use. So persons can't establish a CPS stations alone because it's very complicated and expensive, and it requires a larger area. In addition to that, some solar trackers are used in the CPS to get the most benefit from the sunlight during the day. And if we need to talk about the types of the CPS, we will find that it has 4 types. And the first one is that when the mirrors have some parabolic shape, so it's called the parabolic truss, and this is the first type. And the second type is the linear mirrors, and the third type is the tower, and finally we have the dish or the parabolic dish. Then we have this figure to show us the different types: the tower, the linear mirror, the parabolic truss, and the dish. And in case of the parabolic station, there is a tube receiver for every group of mirrors which collects the sunlight, and in this tube there is a fluid with a high temperature. But in case of the linear mirror stations, there is one tube receiver for a huge number of linear mirrors. So those are the tubes for the parabolic station, and this is only one tube for the linear mirror stations. And at the third type, when the station is of the tower type, there is a huge tower in the center of the station, and all the mirrors reflect the sunlight on the top of the tower where the receiver exists. So there is a receiver here at the top of the tower, and all the mirrors are installed with an angle that reflects the sunlight to the top of this tower here. And finally, at the parabolic dish, in that case, there is a huge parabolic dish that can collect the sunlight on a small receiver at the center of it. So those all stations can be called as steam stations because they are the same like the steam stations that uses the gas or the coal or the nuclear to heat the water to produce an amount of steam which is used to spin the turbine that drives the generator to produce the electricity. But the only difference between them is that the concentrated solar power stations uses the sunlight for heating the fluid to produce the steam from the water, but the other stations use the petrol or the gas or even the nuclear energy to get the required heat. So by this way we have illustrated the different technologies of the solar systems. Basically right now, thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. Today we will talk about the different solar systems in more details. We have talked about the on-grid and the off-grid before in the overview tutorial, and now let's know more information about the off-grid and the on-grid. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to know the difference between the on-grid system and the off-grid. So let's go ahead. Here, the on-grid system is the system that is known as the on-grid or the grid-tie solar system, and it means that your solar system is tied to the electrical grid or the electrical utility that provides us with the electricity, and your loads is fed by this grid. So the on-grid only generates the power when the utility power grid is available, and when the grid is cut off, the on-grid solar system has to stop generating the electricity. But why that? Here assume that the electrical company cuts the service because the grid requires some maintenance, for example, so the electrical engineers and some electricians will go to the place of the grid that requires the maintenance, so the service must be cut off. As if the on-grid system continue to generate electricity, all the people who implement maintenance will be choked and maybe die of the electricity. So the on-grid system has to stop generating power when the grid is cut off. And this system must be synchronized also with the utility. That means the on-grid system must have the same frequency and the same voltage and the same phase sequence of the power of the grid. So the electricity that is supplied from our on-grid solar system must have those same parameters, frequency, phase shift, and the same voltage level of the voltage that the utility or the grid is producing. As when we need to connect any two power sources together, some qualifications must occur like that they must have the same frequency, the same voltage, and the same phase shift. And although this system is very simple and cheaper than the off-grid system, but it doesn't provide the power feeding during the grid outage. And the main components of that system is that the solar panels that converts the sunlight to DC electricity, and then the inverter that is different from the off-grid inverter, so the inverter converts from the DC power to the AC power. And finally we have the last component, which is the net meter that is connected to the inverter from one side, and the other side is connected to the utility. So the input of the net meter is our on-grid solar system, and the output of it is connected to the terminals of the grid or the utility. But we need to know what's actually the net metering and why we don't use the traditional meter. Here the net metering is the technology at which we can measure the energy in two directions. So we measure how much energy you consume from the grid and how much excess energy you export to the grid. So the net meter is very important in the on-grid system to determine if you will give money to the utility company or you will take money from it, as the net meter is capable of determining your net consumption, as if you consume more than that your solar system produces, so you have some appliances that consumes from the grid more than what your on-grid solar system can produce. At this condition you will pay a money to the grid, as your consumption is larger than your generation. But in the other case, when your consumption is lower than your generation, at this point you will get money from the electrical company. Alright, now let's move to the second system, as the second system is the off-grid solar system, also known as the standalone solar system. And at this system you are not connected to the electrical grid, but you are off the grid, so you provide an electricity to your loads directly, not to the grid. And in this system, to ensure an access of the electricity at all time, so the off-grid solar system require a battery storage and a backup generator, as in case of there is any troubleshooting in your solar system or your off-grid solar system, you need the generator to feed your loads, and we use that case, or we use the generator for the critical loads that must be supplied to electricity at all the times. Alright. Now the main components of the off-grid solar systems are the solar panels, and then we have the charger controller that's used to regulate the charge process of the batteries and disconnect the batteries when it's fully charged to avoid the overcharging. And then we have the batteries which store the electricity at the day to use it at the night or at any time. And finally we have the inverter, which converts the DC power to the AC power. And we can say that the most expensive component of the off-grid system is the batteries, and it means that the off-grid system are much more expensive than the on-grid system, but this off-grid system is the best choice in the remote areas that's far from the electrical grid, because if people at remote areas doesn't use the solar systems, they must use the diesel generators, and the cost of it is much more expensive than the off-grid system. That's good. Now after that we can make a comparison between the on-grid system and the off-grid system. Now we will find that the on-grid system is more cheaper and simpler than the off-grid system that is more expensive and more complex. Also, the on-grid system depends on the grid. That means when the grid goes out, the on-grid system cannot produce any electricity. However, the off-grid system doesn't depend on the grid, so it can produce electricity at all times to feed our loads. And when the grid goes out, the on-grid system cannot be a backup source, so it doesn't provide your load with the electricity, but the off-grid can do that. Also, we can say that the on-grid system must be synchronized with the grid to connect them together. However, the off-grid system requires a backup generator. So that's all about the off-grid and the on-grid. And now there is a third system that is called the hybrid system, and this system collects the two systems together, so it provides the grid with the electricity, and also it has some batteries to provide the load in case of the utility cuts out. So the hybrid system combines the best of the off-grid and the on-grid together. And with the hybrid system, the solar batteries are used as a backup in case of the grid goes down. And from this we can estimate that the components of the hybrid systems are the solar panels, then we have the charger controller, and also we have some batteries, and after that the inverter, and also we have the net meter which connect between the utility and the load. So as we said, the net meter job is to connect between the electrical grid and the load to see what your loads consume and what you can give to the grid. So we can summarize all what we said in those words. Here the on-grid system is the cheapest option, but it leaves you with the mercy of the electrical company. And also if the grid substation goes down, you will be without power like everyone else. But the off-grid system is much more expensive, and it requires addition of both of the solar batteries and the backup generator to be on for all of the time when the solar power is less available, but it's the best choice when you are far away from the utility. And finally, the hybrid system provides the best of both, as it allows you to both sell power to the electric company and rely on some batteries as a backup in the event of the electrical grid goes out. So the hybrid system saves you the cost of the backup generator. So that's about our tutorial today about the difference between the on-grid, the off-grid, and the hybrid system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this interesting tutorial we will talk about how the solar system operates. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to take an overview on the different electrical engineering materials, the conductors, the semiconductors, and the insulators. Then we will move to the next step, which is to know the difference between the N-type and the P-type semiconductors, and after that we will know what exactly the P-N junction is, and finally we will know how the solar cell works. So let's go ahead. First of all, the electrical engineering materials are divided into three materials, or we have three main categories. The first one is the conductor, then the semiconductor, and finally we have the insulators. And the crucial difference between the conductor, the semiconductor, and the insulator rely on their level of electrical conductivity, as the conductivity of the material is based on the number of free electrons available in the material. As we know, the electricity is a flow of some free electrons. So we can say that the conductors are materials that have a higher value of conductivity, so the number of free electrons are very high in the conductor at the room temperature, which is the basic reason of the high conductivity for the conductor. And an example of the conductor is the copper and the metal and the bronze. So the bronze is an element, the copper and the metal are some substances that we are using in our daily life. After that we have the semiconductor. So the semiconductors are some materials which have the conductivity between the conductors and the insulators. So we can say that it has a medium level of conductivity. And at the normal temperature, the conductivity of the semiconductor is very low, and by increasing the temperature, the conductivity of the semiconductor increases exponentially. And the popular example of the semiconductors is the silicon material. Now for the insulating materials, it's the material that has a conductivity of a very low value. So the insulators are materials that prevents the flow of the charge through them, as the insulators have no free charge carriers. And an example of that is the phosphorus or the plastic or the wood. So the plastic and the wood are some materials that are used in our daily life, and the phosphorus is an element that is insulator. Alright. Now all of us knows that the atom is the smallest object that retains the properties of an element, and the atoms are composed of the electrons and the nucleus. And the nucleus contains the protons and neutrons. And the electrons are arranged. But the electrons are arranged around the nucleus and the energy levels or the shells. And the electrons at the outermost shells are known to be the valence electrons. And the first energy level has 2 electrons, but the other energy levels has 8 electrons. So we can identify the type of the material by knowing the number of the valence electrons. Here, when the valence electrons is less than 4, the element is conductor. But when the valence electrons equals exactly 4 electrons, the element at this condition is a semiconductor, while when having a valence electrons more than 4, the element is an insulator. That's good. And this is because any material tends to be a staple, and the stability comes when the outer shell has 8 electrons. So conductors prefer to get their valence electrons to another materials to reach the stability, because the conductors have a valence electrons less than 4 electrons, so it's easier to lose them. But when a material has a valence electrons more than 4, it tends to earn some electrons from another material to reach the stability. And it reaches the stability, as we said, to get 8 electrons in the outer shell. And we will see now the atom structure of 3 elements. The boron, that is conductor, and it has 2 electrons in the first shell and 3 electrons in the most outer shell, so it tends to lose those 3 electrons to be a stable one. And then the silicon, which has 2 electrons in the first shell and 8 electrons in the second shell and 4 electrons in the most outer shell, so it's a semiconductor. And finally, the phosphorus is the insulator, and it has 2 electrons in the first shell, 8 electrons in the second shell, and 5 electrons in the most outer shell. So it's called an insulator as it prefers to earn 3 electrons to reach the stability. But you know, we will focus now on the semiconductors because the semiconductors are the materials which is used in the solar system, and we know that the development of the semiconductor is the main reason of our technology today. Hence, you find semiconductors in all devices you have, like the smartphones, the laptops, and all other the electronic devices. And now we are going to talk about the process that is called the doping of the semiconductor. So the doping is a process of adding impurities in the semiconductor, and the aim of that is to increase the conductivity of the material. As we know that the conductivity of the semiconductor is low, so we add some impurities in the semiconductor to increase the number of free electrons to increase the conductivity. But this depends upon the type of the impurity added. So depending on the type of the impurity, we can have the p-type or the n-type. Here the silicon can be doped with 2 of the most important materials, the boron or the phosphorus. And in the case of boron, we have 3 valence electrons, and at this time the p-type is formed. But for the phosphorus case, we will have 5 valence electrons, and at this case the n-type is formed. So the p-type semiconductor is formed when the semiconductor is doped with a conductor, but the n-type is the semiconductor material doped with an insulator. That's good. Now let's see the n-type doping in some details. Here we find that the phosphorus atom has an outer electron more than the silicon atoms. So we find that 4 outer electrons combine with every 1 silicon atom, while the 5th electron is free to move and service as a charge carrier. And that occurred for thousands of times, so there are thousands of free electrons, and therefore the conductivity is increased. But on the other hand, for the p-type doping, we will find that the boron atom has an outer electron less than the silicon atom. So 3 outer electrons combines with every 1 silicon atom, so there is 1 hole more in the material, and those holes, like free electrons, increases the conductivity of the semiconductor. Alright. Now the next thing is to combine them to get the p-n junction. So the p-n junction is the main basic component of the solar cell, as it looks like the brick in our wall. So when an n-type material is fused with the p-type material, the p-n junction is formed. And when the p-n junction is formed, some electrons from the n-type material diffuses to the p side, and some holes from the p-type material diffuses to the n-type. And those charge carriers or the electrons combines and create a region called the depletion region. So there are 3 regions, the N crystal, the P crystal, and the depletion region. And according to that, we find that the p-n junction has 3 different characteristics. The first one is the equilibrium, the second one is the forward bias, and the third one is the reverse bias. So at the thermal equilibrium, there is no external voltage that is applied to the p-n junction, and in that case, there is no flow of the electric current. And that's what applied in this figure here. But when an external voltage is applied to the p-n junction, there are 2 cases, the forward and the reverse bias. So if the n-type crystal is applied to a negative voltage and the p crystal to a positive voltage, the depletion region at this condition will decrease and the current will flow in the circuit, and that's what's called the forward bias. However, if the n-type crystal is applied to a positive voltage and the p-type is applied to a negative voltage, the depletion region increases at this condition and no charge carriers can pass through the depletion region, so there is no current flow, and that's what's called the reverse bias. Let's see how the solar cell produces electricity. At first, we know that the solar cell is a device that directly converts the sunlight into electricity, so the solar cell is made up of a p-n junction. But the p-n junction here produces volt and current when the sunlight falls into it. Here, when the sunlight shines on the cell, the photons hits the solar cell, and the absorption of the photons creates the electron-hole pairs, and then the electrons flow through the external circuit, creating the current. And we can see an animation here that shows us what's happening when the photons of the sunlight hits the solar cell. A pair of electrons and holes are produced, then the electrons pass through the external circuit, and ultimately after passing through the load, the electrons meets up with a hole and completes the circuit. That's good. Alright, now the last thing we have in this tutorial is the solar module, as the solar cell is the smallest component of the module as you see here, and many cells makes a module, or it's called the panel. So the accumulation or the integration of the cells produces a panel, and many panels make the array, and many arrays make the solar system at whole. So that's good and enough for this tutorial, at which we have learned what is the basic idea behind the solar cells and the integration of the solar cells. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. Today we will talk about the first component of the PV solar system, which is the solar panels. So fasten your pull and let's get started. The aim of this tutorial is to understand the different characteristics of the solar panels, because when we understand the characteristic of this device, we can get the most benefit of it and we can handle with it correctly. And also we will know the tests which are applied on the solar panels, and those tests occurs by the manufacturers, and then we will know what are the factors that affects the solar panel performance to reach the peak performance. And finally, we will know the different types of the solar panels and we will compare between them. Now let's understand the panel's characteristic by studying the voltage current curve or the IV curve and also the power voltage curve. So by those curves we will find 5 important parameters of any solar panel. The first curve is the IV curve. It represents the relation between the current and the voltage at the existing condition of the irradiation and the temperature. So when the irradiation and the temperature change, this curve will change. So this is not a fixed curve that has some fixed values, but the values changes according to the parameters like the panel itself and the solar condition that it's exposed to it. Now the first thing is the short circuit current or ISC, and the second thing is the open circuit voltage. So let's illustrate them. Here the short circuit current means the maximum current that is provided by the panel when the voltage across the panel is 0 or when the panel is short circuited. And the open circuit voltage is the maximum voltage that the panel provides when the terminals are not connected to the load or when the panel is open circuit. So this is about the first curve here, this red curve. This is the I short circuit current and this is the open circuit voltage. And now the second curve determines the PMP or the maximum power point. And at this point the panel can provide the maximum power available. And then the next parameter is the maximum power voltage or VMP, and it represents the voltage value at the maximum power value. Here this is the maximum power value. When going down we will find that this is the voltage at the maximum power. And finally we have the maximum power current or IMP, and it represents the current value at the maximum power. Also at this point when going vertically we will find that this is the current at the maximum power point. So if we draw a line from the maximum power point to the IV curve, we will get the maximum power voltage and the maximum power current. And as shown here, the short circuit current is greater than the maximum power current, and also the short circuit voltage is greater than the maximum power voltage. So the short circuit values are related to the end of the curve. Here this is the end of the curve at which we have the short circuit, and this is the end of the curve at which we have the short circuit current. While the maximum power point voltage and current doesn't relate to the end of the curve, but it's related to the point at which we have a maximum power. That's great. Now when the solar panels are manufactured from the factories, some tests are applied to them. And the aim of those tests is to check the solar panel's performance. And here the first test is called the standard test conditions or the STC. So the STC is an industry widely used standard to indicate the performance of the PV module. So standard test conditions are the industry standard for the conditions under which the solar panels are tested. And by using set of conditions, all solar panels can be accurately compared and rated against each other. So that's the STC. And the 3 conditions of this test are the temperature of the cell, which is 25 degrees Celsius, and the solar irradiation, which is about 1000 watt per meter square, and the mass of the air, which is about 1.5 air mass. And with this test, the maximum power of the solar panel can be determined. Now the second test is the nominal operating cell temperature or the NOCT. So the NOCT is defined as the solar panel temperature based on three standard test conditions. The first one is the irradiation on the panel, which is about 800 watt per meter square, and the second one is the air temperature, which is about 20 or for example 25 degrees Celsius, and finally the air mass also, which is about 1.5. So the normal operating cell temperature provides a measure of how the PV cell temperature varies with the ambient temperature and the solar irradiation. So the ambient temperature is the temperature of the surrounding or the temperature at the place we are installing the solar panel. And we need now to know what will be the internal solar cell temperature with respect to the surrounding temperature and the solar irradiation. So those tests determines the efficiency losses due to the increase of the panel temperature. Now we want to know the factors that affects the performance of the solar panel itself. Here the first factor is called the solar radiation or the solar irradiation. As we shown, the IV curve represents a different irradiation. So at an irradiation from the sun of 1000 watt per meter square, we have a voltage level or we have a voltage current curve, and at 800 we have another voltage level, and at 600 we have another voltage level. So we can see that when the solar irradiation decreases, the voltage current curve decreases, so the power will decrease. Here the maximum power point is about 100 watt, and the maximum power point at 800 watt per meter square is about 18 watt, and at 600 watt per meter square we have a maximum power point of about 60 watt, and so on. So when the irradiation increases, the current will increase, and then the power will increase, as the power equals the voltage times the current. And also the efficiency will increase, as we will have a larger output power from the panels. Now the second factor is the temperature, as shown in the IV curve. Those are two curves with different temperature of each one. So when the temperature increases, the current will increase slightly, but the voltage will decrease greatly, so the output power will decrease. Therefore, the output power of the panel is inversely proportional to the temperature. So when the temperature increases, the voltage will decrease, and then the output power will decrease, and the efficiency will decrease. So we can conclude that at every degree of the panel temperature change or increase about the 25 degrees Celsius, this will cause a decrease on the efficiency of about 0.5% approximately. Now the last thing we have in this tutorial is the solar panel types. So there are three major types. So the first one is the monocrystalline silicon panel, and the second one is the polycrystalline, and the third one is the thin film panels. So as you see, this is the mono, this is the poly, and this is the thin film. And from its physical shape you can note them, as the monocrystalline panels are usually very dark blue or black in color, but the polycrystalline panels are often blue in its appearance, and the thin film are usually homogeneous of the dark blue. Also, for all of the panels we have an average of the lifetime of about 20 years or 25 years. So most of the solar panels are manufactured to have a lifetime of about 20 years. And for the ranges of the power available for the solar panels, we have some standard ranges like the 100 watt, 150, 250, 255, 260, up to 300 and 320. So there are some ranges between those also, but those are the most common ranges. But you can ask now, which of those solar panels is the best? So we can compare between them now. Here, this is the monocrystalline, the polycrystalline, and the thin film. And the first part of the comparison is the area. So this is according to the area of the solar panel itself. And for the same power range, we can find that the monocrystalline panel has the smaller area, while the polycrystalline has a medium area, and the thin film has the largest area. Then the second part of the comparison is the weight. So we will find that the monocrystalline is the most light, and the polycrystalline is medium in weight, and the thin film is the most heaviest, related to the first two ones. Then the next part of the comparison is the efficiency. So we will find that the monocrystalline is the most efficient, that has an efficiency from 15 to 20% for example, and the polycrystalline has an efficiency of a medium one, ranges from 13 to 16, and finally the thin film has the lowest efficiency from 7 to 13%. So the monocrystalline is the most efficient and the thin film is the lowest in the efficiency. Now for the cost, we will find that the monocrystalline is the most expensive. This is because it has a higher efficiency and a lightweight and smaller area, so those are some benefits that makes its cost to be the highest. And then the polycrystalline has a medium cost, or its cost is smaller than the monocrystalline. And finally, the thin film is the cheapest one due to its lower efficiency and its heavy weight and its larger area. Now the last part of the comparison is the shadow effect. So we need to know which of those panels will be affected greatly by the shadow effect, or which of them will have the lowest output power when it have a shadow in it. So the monocrystalline has the highest output power when it has a shadow in it, and the polycrystalline also will have a high output power, but the thin film will be affected greatly. So when there is a shadow on the thin film panels, its output power will be the lowest. And now you can ask, which of those panels we can choose in our project? So in case that the space is not the issue, so you have a largest space that you can spread your solar panels into it, the thin film panels can make sense. But when the area is the crucial factor, or when you have a smaller area to spread your panels on, the mono panels will be the best choice. So you can select your panel according to some different factors that is related to your requirement or your current case. So that's about this tutorial today, at which we have illustrated some important concepts related to the solar panels. So basically right now, thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial, we explained that the solar modules is fixed with a certain angle called the tilt angle, and we knew how to choose the optimum tilt angle to get the highest performance of our solar system. Now in this tutorial, we will understand another solar system, which is called the tracking solar system. And in this system, our solar system isn't fixed, but it tracks the sun movement to get the most benefit from the angle. Are you ready? Fasten your pull and let's get started. The aim of this tutorial is to discuss the difference between the fixed solar system and the tracking solar system, and which of them is the better. And also we will know the different types of the tracking solar systems. Now we wanted to know the difference between the two systems, the fixed and the tracking system. So in the fixed system case, the solar panels are placed at a fixed angle, which is usually the optimum tilt. And in that case, we design our solar system with a fixed angle, and we try to collect the sunlight as much as possible. And absolutely, we all know that the sun moves through the sky from the east to the west through the day. So we have to calculate the optimal tilt angle as we learned on the previous lectures. So if we wanted to obtain the maximum efficiency from the solar panels, they needed to be pointed in the direction that captures the most sun. But our new system today is mostly different from the fixed one. Here the solar tracking is the technology of orienting the sun panels towards the sun. Because the sun moves through the sky every day, so solar trackers are used to keep the solar panels oriented directly towards the sun to increase the energy output from the solar panels. And in that case, the solar panels can capture the sunlight at all time in the day, except if the sun disappears because of the clouds, for example. And although this system will increase the efficiency of our solar system, but it has some disadvantages also. And now we wanted to know which of them is better, the tracking or the fixed system. So we can know that by studying the difference between them. Here the tracking system generates more electricity than the fixed, so the tracking system has more efficiency. But the tracking system also is more expensive than the fixed system because it requires more devices to track the sun every time. And also we can say that the tracking system requires more maintenance because it uses actuators and sensors and other devices to track the sun panels towards the sun at all time. And most of the time the huge solar systems are created outside the cities and the deserts, for example, as there are a lot of sands and winds there in the deserts or those harsh weather conditions. So we need to maintain the tracking regularly. Also, we can say that the trackers are more complex systems than the fixed system because the way to track the sun is very complicated and require very complicated sensors, and the connections between the sensors and the actuators is very difficult also. And finally, we can say that the fixed system maintains the harder environmental conditions than the tracking systems. So the fixed system can withstand the winds and the sands and the desert environment. So it can cope with the harsh environmental conditions. And from all of that, we can estimate that the tracking systems need more cost, so it's more expensive. For example, if there is a huge solar station and the small increase of the efficiency will affect greatly the electrical production, in that case the tracking system is the best option. But if we are handling a smaller solar system, for example the solar system above your house roof, at this condition the fixed solar system will be the best condition. That's great. Now the tracking system is in only one type, as there are some types of it. The first one is called the single axis tracking, and the second one is called the dual axis tracking. And here this figure illustrates the case at which we have 3 axes, 2 horizontal and 1 vertical. So this is a horizontal movement of our panel, and this is a vertical one, and this is another vertical one. So we can say that the single fixed tracking can have either a horizontal or a vertical axis. However, the dual axis tracking has a horizontal and a vertical axis at the same time. So it can track the sun apparent motion at any location. So the dual axis tracking is more efficient but more expensive also. And it's a common trade if you want more efficiency and more comfortable, but you will pay more. And also we can say that the single tracking system has 2 types. So the single tracking system itself is divided into 2 types. The horizontal type axis, and in that case the rotating axis is this one here at this part, so it moves up and down at those directions. And now the second case is the tilt single axis, and in that case the panel moves right and left as you see here. But the question now is that how the solar panels determines the position of the sun. So we can say that in the single axis tracking we have an open loop controller tracker, and that open loop controller hasn't the sensors, but it has a microprocessor inside it, and it uses the mathematical formulas to predict the sun position. So it depends on the geographical location and start time situation of the system. Although the open loop controller tracker is more simple, but also it's less efficient. That's good. Now the second type is the dual axis tracker, and at this condition, as we said, the axis tracking can rotate in the horizontal or the vertical axis at the same time as you see in the figure. So it can rotate right and left, also up and down, and it can move at any direction. And in that case, the closed loop controller tracker are used to detect the sun position. And this system uses the information of the electro-optic sensors for estimating the location of the sun. So it also doesn't depend on the geographical location, and it starts at time situation of the system. So this system is more efficient than the previous one, but it's more complicated and expensive. Now that's all about the tracking system and their types. But as we said, the tracking system is a more complex system, and it requires a lot of maintenance, and it can't maintain the difficult environmental condition, but the benefit of it is that it increases the efficiency of our system. And now we need a solution to get the benefit of the fixed and the tracking system together at the same time. So we need to collect the advantages of the 2 systems together. So we can create a simple tracking system collects the advantage of the fixed and the tracking system. And this system has 3 different tilt angles, depends on the season. So let's know that. Here the tilt angle beta has 3 different values of 3 different seasons. So in the spring and the autumn it will equal the latitude, so we will get the beta to be the latitude at the spring and autumn. So if the latitude is 30 degrees, the tilt angle will be 30 degrees. And in the summer the tilt angle will equal the latitude minus 15, because decreasing the tilt angle can increase the energy production in the summer. But at the winter, the tilt angle will equal the latitude plus 15, because increasing the tilt angle will increase the energy production in winter. And that's because the S module equals the horizontal irradiation, or the global horizontal irradiation, times sine alpha plus beta over sine alpha. So from this relation we can say that the module irradiation or the global tilted irradiation is directly proportional to beta. But in the summer, the sunlight is stronger and we don't need to increase the global tilted radiation, so in the summer the tilt angle theta equals the latitude minus 15. But at the winter, the tilt angle theta equals the latitude plus 15. And also we have the same standard values for the tracking angle, 15, 20, 30, 45, 50, and 60. So those are some common values when choosing the tilt angle for the tracking standards. So this is about the different technologies, the fixed system and the tracking system, and the different type of the tracking system, and how can we solve the problem of the tracking system by making a semi-fixed system or a system that can vary during the seasons of the year. So this is about this tutorial. So basically right now, thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial we will take a tour on the batteries that are used in the solar system. As in the previous tutorial we talked about the first component, which is the solar panels. And now we will talk about the second component of the off-grid solar system, which are the batteries. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to take a general overview on the batteries, and then we will talk about the different types of the batteries. So let's go ahead. As we know before, the solar system is a system that converts the solar energy into electricity. So when the sun disappears, the solar system doesn't produce any electricity. And of course, as we know, the sun rises at the day only, but at the night the sun sets. And also sometimes during the day, there will be some clouds or some rains that decreases the solar radiation or make it to P0. So there will be a zero produced electricity from the solar system. And we need to use the electricity at our homes in the day and at the night and at any time. So we need the device to store the electricity in the day when the sun gives us the light to use the electricity at any time during the absence of the sun. And this device is called the batteries. So for this reason, the off-grid solar system consists of some batteries. So we can say that the battery is a device that stores the electricity energy in a form of chemical energy and then converts it again to electricity. Therefore, it takes the electrical energy as a DC input or a direct current, and it stores it as a chemical energy, and then it converts it back to an electrical energy for us to use it at any time. And the batteries has only one type, as there are many types of the batteries. So let's know now the types or the different types of the batteries. Here the batteries are divided into two main categories, the primary and the secondary. And for the primary batteries, it's the one-way process, as the chemical energy is converted to electrical energy, but the process isn't reversible, or the electricity cannot be converted back to a chemical energy again. So we can say that the primary battery is a non-rechargeable battery, so it can be used only one time. And an example of it is the alkaline battery that is used in the flashlights. But in the secondary batteries, the conversion process between the electrical and the chemical energy is reversible, so the chemical energy is converted to the electricity and the electricity energy is converted back to a chemical energy. And for this it's called a rechargeable battery, and we can use it many times. And an example of it is the lithium and the lead acid batteries. And here you can see this is the alkaline batteries that we are using widely in our daily life, and this is the lithium battery, or this is the other battery that is rechargeable. But for the photovoltaic solar systems, all the batteries must be rechargeable, so it must be of the secondary type. And the secondary batteries have many types, but we will focus on the types that are used in the solar system. And there are two common secondary batteries used in the solar system, the lead acid batteries and the lithium batteries. So the lead acid is more common in the solar system due to its lower cost, but the lithium is better in the other factors, as we will see now. Here this is a comparison between the two types to know who wins and who is better. So the lead acid wins only in the cost, but the lithium wins in the efficiency, its lifespan and its maintenance. So let's describe the difference between them in more details. As we said, the lead acid has a lower cost, but the lithium is very expensive. So the cost of the lithium almost about 7 times greater than the lead acid. but the lithium batteries on the other hand are more efficient, and this means that more of the solar power is stored and used. So the lithium batteries are more than 90% efficient, higher than the lead acid batteries, and that means if we have a 100 ampere hour from the solar radiation coming into our batteries, for the lead acid there will be only about 80% available after the charging and the discharging operation. However, at the lithium we have about 90% ampere hour available. So the lithium batteries can store more power than the lead acid. Then for the life cycle or the lifespan of the batteries is measured with the cycles, not the years. But what does this mean? So when the battery is discharged and recharged again, this is called the cycle. So the cycle means how many times the battery will be charged or discharged. So we can say that the lithium batteries can be charged or discharged many times than the lead acid. That's great. Now the next part of the comparison is the maintenance. So the lead acid batteries require regular maintenance to keep them running properly, but the lithium batteries don't need that. Alright. Now after this comparison, we decided that the lithium batteries are better. However, many systems use the lead acid batteries due to its lower cost. Now let's mention more details about the lead acid batteries. The lead acid batteries consists of a positive and a negative lead plate of different composition suspended in a sulfuric acid solution called the electrolyte. And when the battery discharges, the sulfur molecules from the electrodes bonds with the lead plate and release electrons. And when the battery recharges, an excess number of electrons goes back to the electrolyte and the battery develops a voltage from this chemical reaction. So this is about its chemical working operation. But you know, the lead acid type itself has many types or many subtypes under it. And there are two main types: the starting batteries or the crank battery and the deep cycle battery. So you can see that this is a type of the starting batteries or the cranking batteries, and this is another one of the deep cycle battery. So the starting batteries are designed to provide a large amount of power at a short time, and this is the type that is used in your car for starting the car engine. But on the other hand, the deep cycle batteries are designed to get a lower amount of energy or a lower amount of current, but for a large time. So it doesn't give us a spark or a very large amount of energy at a lower time, but a medium amount of energy for a large time. That's good. But the important thing to know is that the deep cycle batteries are the batteries that we are using in the solar system, not the starting batteries. And for this we will focus on the deep cycle batteries now, as this is the type that we are handling. So the deep cycle batteries falls mainly on two distinct categories. The first one is the regulated lead acid, and the second one is the flooded lead acid. And the regulated lead acid also has two subcategories. The first one is the gel, and the second one is the absorbed glass mat. So the AGM and the gel are usually used because the flooded type requires a regular maintenance to work normally, and also the flooded type produces a harmful vapor during the chemical reaction. And for those reasons we prefer the gel and the AGM types of the lead acid batteries. That's good. Here we can see the different types of the batteries. You can see this is the flooded type, and this is an image for the gel type, and this is another one for the AGM or the absorbed glass mat. So by this way we have discussed the different types of the batteries and an overview at which. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial we will continue talking about the batteries used in the solar system. So fasten your pull and let's get started. The aim of this tutorial is to know the different properties of the batteries used in the solar system. So let's go ahead. Assume that you need to buy a battery for your solar system, so you should know some characteristics to choose the optimum battery. So there are some certain specifications or characteristics you should use when evaluating the solar battery option. And the main specifications are the battery capacity, the depth of discharge or the DOD, and the state of a charge or the SOC, and finally the life cycle of the battery. Now we will understand those specifications in more details. The first characteristic is the battery capacity. So the battery capacity is the total amount of electricity energy that the solar battery can store, or it represents the maximum amount of energy that can be extracted from the battery under the certain specified conditions. And the unit of the battery capacity is the ampere hour. And in fact, the battery capacity can be measured in watt hour, but the common unit is the ampere hour. And also when we read the datasheet of the battery, we will find that it's in ampere hour. So for this, we will discuss it in ampere hour. But from where this unit ampere hour comes? So we know that the energy equals the power multiplied by the time. So its unit is watt hour. However, the power equals the voltage times the current, so the energy will equal to the voltage times the current times the time. So the unit now is volt times ampere times hour. But as the voltage is constant, we can say now that the energy is represented in ampere hour as the voltage is constant, so we can cancel it. And the ampere hour is defined as the number of hours for which a battery can provide a current equal to the discharging rate of the nominal voltage of the battery. And let's illustrate that. For example, if we have a battery of 100 ampere hour, this means that the battery can provide 100 ampere for 1 hour, or it can provide 50 ampere for 2 hours, and so on. Note also that the 100 ampere hour means that if the battery is charged with 100 ampere, it will last 1 hour to reach its full capacity, or if we charge it for a period of 30 minutes, it will be charged with its half charge. So this looks like when you charge your mobile phone. If you connect the phone to the charge for 30 minutes, your phone will be charged with 40% of its full charge, for example. But if you charge your mobile phone for 1 hour, it will be charged with 70%. And if we charge it with more than that, it will be charged with 100%. But you know, when we say that we have a battery that has a capacity of 100 ampere hour, this doesn't mean that the battery will be able to provide 100 ampere hour. This is because the battery capacity is affected by some factors. And those factors are the rate of the charge and discharge, and the temperature of the battery itself, or the temperature of the surrounding, then the age and the history of the battery. So the old battery will have another capacity rather than the new battery, and so on. But we need to know in more details how those factors affect the battery capacity. So let's see now. The first thing is the effect of the discharge or charge on the capacity of the battery. Here we can say that the charging or the discharging rate affects the battery capacity directly. So if the battery is being discharged very quickly, so the discharge current will be high, then the amount of energy that be extracted from the battery is reduced, so the battery capacity will be lower. And that's why, because when the battery is discharged, some chemical reaction occurs inside the battery, and this will convert the chemical energy to an electrical energy. And as we said before, when the charging or the discharging rate is very fast, those chemical reactions haven't enough time to occur, and therefore the energy available is reduced. And also the opposite thing is right. When the battery is discharged with a very slow rate using a lower current, there will be more energy that can be extracted from the battery, and the battery capacity at this condition will be higher. Now the second factor, as we said, is the temperature. So when the temperature is higher, the battery capacity will be high, and when we have a lower temperature, the battery capacity will be low. And this is because the chemistry basics tells us that when the temperature increases, this will help the reaction to occur faster. So increasing the temperature is an effective method to increase the battery capacity, but this will also decrease the battery lifetime. So we cannot increase the temperature to decrease the battery capacity. This is because that will decrease the battery lifetime at that time. Now the third factor that affects the battery is the age or the history of the battery. As the age of the battery have a major impact on the capacity of the battery, because the battery capacity will be close to its rated capacity for a limited number of charging and discharging cycles according to its manufacturer, and then the capacity starts to decrease with the time. So if we have two batteries of 100 ampere hour, the first battery is used for 100 cycles, so its capacity after 100 cycles may be 9 ampere hour, and the second one is used for 150 cycles, so its capacity will be lower than 90 ampere hour, or lower than the first battery. And for this reason, we have to change the battery after a number of years depending on the type of the battery and its age and the number of cycles that has been charged and discharged with it. So this is about some different things related to the battery. Hope that's clear right now. Thank you for watching, and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. Today we will continue discussing the second module in the off-grid solar system, which is the battery. Are you ready? You should be ready. So fasten your belt and let's get started. Our first step today is to continue the battery specifications. As on the last tutorial, we talked about the first specification, that was the battery capacity. So let's go ahead. First of all, in the previous tutorial, we said that the main specification of the batteries are the battery capacity, the depth of this discharge, the state of this discharge, and finally the battery cycle. And we explained the battery capacity, and we said that the battery capacity is the energy that the battery can store, and we knew the factors that affects on it. Now let's move to the second specification, the depth of this discharge. Firstly, we should know that most of the solar batteries needs to retain some charge at all the time due to their chemical composition. In other words, the battery cannot be fully discharged. So if we have a solar system that needs 200 ampere hour, we have two batteries and each of them is 100 ampere hour. So the question now, can we use two batteries only to get 200 ampere hour? Of course, that's wrong. Because if we use two batteries only, we will discharge the two batteries with 100%. So the DOD at this condition will equal 100% and we will damage the battery quickly. And the right method, if we have a 100 ampere hour battery, to discharge it with 500%. So this is the most ideal case that will retain the battery life. Therefore, if we use 100% of battery charge, its useful life will be significantly shortened, and at this condition the importance of the depth of discharge concept comes now. So at this condition the ideal case is to use 4 batteries and each of them rated with 100 ampere hour. But we need to know exactly what is the meaning of the depth of discharge. So what does exactly mean? Here the depth of discharge is defined as the fraction or the percentage of the capacity which has been removed from the fully charged battery, or it refers to the amount of the battery capacity that has been used. For example, if we have a 100 ampere hour battery as you see on the left here and it has a DOD of 90%, you shouldn't use more than 90 ampere hour of the battery before recharging it again. Hence, generally speaking, a higher DOD means we will be able to utilize more battery's capacity. But you should take in your mind that there is a relationship between the DOD and the battery cycle, or the battery life cycle. And from this relation, we can understand the importance of the DOD, because the DOD affects the life expectancy of the battery directly. And this theory is applied to most of the rechargeable batteries, the lithium and the lead acid. So from this graph we can see a great difference on the battery life cycle and its DOD. So when the DOD is 30%, we will find that its life cycle is about 6,000 cycles. While when the DOD is 90%, we will find that its life cycle is only 1,000 cycles. Therefore, we can say that the battery cycle is inversely proportional to the DOD. And that means the larger DOD every cycle, the smaller available number of cycles. So manufacturers commonly declare the life cycle at a certain value of DOD, as the DOD is related to the life cycle. For example, the lithium-ion batteries declares its life cycle to be 1,900 cycles at a DOD of 90%. So manufacturers will specify a maximum DOD you should use at the optimum performance. But there is a note here. Practically, the optimum or the best value of the DOD is to be 50%, but at this case we will have to use more batteries and then the cost will be very high. And the maximum value of the DOD is about 75% to 80%, and its moderate value to be about 60%, but the worst case of the DOD to be about 80%, and this is a very bad percentage that will affect the battery lifetime badly. Alright, that's all about the DOD. Now let's move to the state of a charge, or the SOC. In fact, the SOC is the direct opposite of the DOD, as the SOC is defined as the level of charge of an electrical battery relative to its capacity, or it's the amount of energy remaining in the battery compared to its capacity. So when a battery is fully charged, we can say that the SOC of the battery is 100%. Therefore, if we have 3 batteries, the first one is fully charged, and the second one is 70% charged, and the third one is 40% charged. So the DOD of the first battery will be about 0% and its SOC will be 100%. And for the second battery, the DOD will about 30% and the SOC will about 70%. And for the last battery, the DOD is about 60% and the SOC will be about 40%. That's good. Now the last specification is the battery cycle, and as we said on the previous tutorial, when the battery is discharged and charged again, this will be a complete cycle. So the cycle is the process of fully charging or discharging a battery, as the life of the battery isn't measured by the years but by the cycles. For example, when a battery has a 1000 cycle, this means the battery can be discharged and charged again for 1000 times. So practically every battery has a finite life, and at the end of its life the cycle of the battery meets its death. The first one is the DOD and the second one is the battery temperature. So when the DOD increases, the life cycle will decrease, and that will increase the depth of discharge at that case. And also when the battery temperature increases, its life cycle will decrease. So the life cycle is inversely proportional to the DOD and the temperature of the battery. As we said before, the temperature affects the battery capacity and its life cycle. So when the temperature increases, the battery capacity increases because it increases the speed of the chemical reaction inside the batteries, but the battery life cycle will decrease. So that's all about the specification of the batteries. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial we will continue talking about the batteries, so fasten your belt and let's get started. The aim of this tutorial is to know some different connection of the batteries, to learn some tips about the batteries configuration and layout, and how can we design a solar system with the different connection of the batteries available. So let's go ahead. The first thing we need to know is how to connect a number of batteries together to get the voltage and the required ampere hour for the solar system. Here we can connect the batteries either in series or in the parallel, or to be a mix between them. So the series connection means that if we have two batteries like those ones here, we will connect the positive terminal of a battery to the negative of the other one and take the output from the two other terminals. And the parallel connection means that we connect the two positive terminals together and the two negative terminals together. And the mixed connection means that the batteries are divided into a series batteries in a branch, and those series branches are connected in parallel. So you can see that those are series branches and those are series branches, and both of them are connected in parallel here, like those two terminals and those two ones. And we all know that when the two batteries are connected in series, so the voltage will equal to the sum of the voltage of the two batteries. So the total voltage equals to V1 plus V2, V1 for the first battery and V2 for the second battery. But the total current will equal the same current of each battery. So the total ampere hour at this condition will equal I1 or will equal I2 of the second battery. Then the second case, when we have two batteries that are connected in parallel, so the total voltage will equal to the same voltage of each battery, so it's equal V1 plus V2, while the total current at this condition will be the sum of each battery current. So the total current equal I1 for the battery 1 and I2 for the battery 2. So you can note that the series connection is the inverse of the parallel connection. At series we have the summation of the total voltage, but we have only one value of the current. But at the parallel we have only one value of the voltage, but we have the summation of each battery current. That's very easy. The next example, I want you to pause the tutorial and answer this question. When we have two 12 volts batteries and each of them is 100 ampere hour are connected in series. So as the total capacity is 100 or 200 ampere hour, and how much the total energy will equal? Now you can think and answer. Have you got it? I hope that. Now the right answer is that the total capacity will equal 100 ampere hour, not 200, and the total energy will equal 2400 watt. And let's prove that now. Here the first thing you must know is that the total energy always equals the sum of the energy of each one or each part. This is in case of we have a series or the parallel. So at any case the total energy equals the summation of each part energy. So it's energy 1, so it's the energy of the battery 1 plus the energy of the battery 2. and we calculate the energy by multiplying the ampere hour with the voltage. So energy 1 equals 12 volts times 100 ampere hour, so it's equal 1200 watt hour. And energy 2 equals 12 volts times also 100 ampere hour, and it's equal identically 1200 watt hour. So the total energy will equal 1200 plus 1200, which equals 2400 watt hour. And we can get the total capacity by dividing the total energy over the voltage. And we know that the total voltage equals to the sum of the two voltages of the two batteries, the battery 1 and the battery 2, so it's equal 24 volts. So the total ampere hour equals to 2400 watts over 24 volts, which equals 100 ampere hour. And by the same way, when we have 12 volts battery and each of them is 100 ampere hour and they are connected in parallel as you see, so what will be the total capacity now? Here it will be 100 ampere hour or 200. Of course, it's equal 200 ampere hour, and the total energy equals 2400 watt hour. And the total energy equals the energy 1 plus energy 2. So energy 1 equals energy 2 equals 100 ampere hour times 12 volts, which equals to 1200 watt hour. So the total energy now equals energy 1 plus energy 2, which equals 2400 watt hour. But the parallel case has a total voltage equals 12 volts only, so the total ampere hour will equal 2400 watt over 12 volts, that is equal 200 ampere hour. Alright, now at this point we can say that the total battery capacity can be calculated as the current. In case of the series connection, the total capacity will not increase, so it's each battery capacity. And in case of we have a parallel connection, the total capacity will increase, and it's equal the sum of each battery capacity. So if we have 5 batteries that has 100 ampere hour of the total capacity of each one of them, so each one are 100 ampere hour, but they are connected in series, so the total capacity will equal 100 ampere hour. But if they are connected in parallel, the total capacity at this condition for the parallel, as we said, is 500 ampere hour. But the total energy at all the time remains constant, which equals to the sum of each battery energy. So at any case, the series, the parallel, the total energy remains constant. That's great. But mostly in the solar system, the batteries are connected in series and in parallel at the same time. So there may be some combinations of the series and the parallel connection. So we connect it in series to give us the required voltage and in parallel to give us the required ampere hour. For example, a battery system composed of 3 parallel branches and each branch has 4 series batteries. The question now is that, if each battery has 12 volts and 100 ampere hour, what will be the total voltage and the total capacity? Here the total voltage will equal the voltage of each branch, so it's equal 4 times 12, which is 48 volts. And this voltage is called also the pulse voltage, and we will know what is the pulse voltage means in the next slide. And the total ampere hour will equals 3 branches times 100 ampere hour, so it's equal 300 ampere hour. That's great. Now this is the connection of our batteries. As we said, we have 4 batteries in each branch and 3 parallel branches. Now let's know what is the pulse voltage. So when a number of batteries are connected together, the total voltage of them will be the pulse voltage. So the pulse voltage is defined as the total voltage of battery system, and we must select a certain value of voltage because when we select the charger controller and the inverter, they must be compatible with the battery's voltage, or they must have an input voltage the same as the batteries. And the common values of the pulse voltage is 12 volts, 24 volts, and 48 volts. And the pulse voltage is very important in designing a solar system, as we will know that in the next tutorial. Now suppose that we have a system consists of 4 batteries and each of them has 12 volts. How those batteries are connected to each other to give us a pulse voltage of 12 volts or 48 volts or 24 volts or for example 36 volts. So in case of we have a pulse voltage of 12 volts, we will connect 4 batteries in parallel, so the total voltage will equal to each single battery voltage. And in case of the pulse voltage is 48 volts, so the 4 batteries will be connected in series, as the total voltage will equal 12 times 4, which is 48 volts. But in case of 24 volts, so we will connect two batteries in series and two batteries in parallel. So we will get two parallel branches and each of them has two series branches. But here we have a question. If we have a source that has a constant current to charge those batteries, which case will charge faster? So we know that the current is divided in the parallel connection and it's not divided in the series connection. So when the four batteries are connected in series, the flowing current will be larger than if they are connected in parallel. So the 48 volts will be faster than the 24 and the 24 will be faster than the 12 volts and so on. And the final case we have is to get at 36 volts, and in that case we will connect three batteries in series and the last battery in parallel. So the fourth battery will be connected in parallel with each one of them. But this connection will cause an instability in the system because the current will be divided in two parallel batteries and then it will collect again. So the current flow through the two parallel batteries is smaller than the current flow through the other batteries. So the two series batteries will be charged faster than the two parallel batteries. That's good about the connection. But before to end our tutorials, we must mention some important information or some important notes about the design. Here the first one is that when we have a battery with 12 volts and it's fully charged, its voltage will equals to about 13.5 volts or 14 volts. And when it's fully discharged, its voltage will be about 11 volts. So we can say that its standard voltage is 12 volts, so you buy a battery with 12 volts, but this 12 volts is not constant as it has a tolerance, and this tolerance has a relation with the current. So when the current increases or the ampere hour increases on the battery, its voltage will increase, and when the current decreases at the battery, its voltage will decrease. That's good. Now the second note is that when a charged battery is put on the ground directly, so it's touching the ground now, it will be discharged with the time without using. So we shouldn't put a battery directly on the ground, but we should put it on a wooden material or on the foam material to be isolated from the ground and the temperature of the ground. Now the last thing we have, if we wanted to store some batteries without using them, so if we have some batteries and we will not use them now in the solar system or on any system, so to store the batteries, it's very recommended to discharge them firstly. So it's not recommended to store some batteries when they are charged, as this will affect their lifetime or their performance after that. So that's good about this tutorial, at which we have finished some aspects about the batteries connections and some notes related to it. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will start a new very important topic, which is how to design a complete off-grid photovoltaic solar system. And we will break this design into some few simple steps to make it easy to understand and tidy to use. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to understand the first two steps of designing any off-grid solar system, which are how to calculate the total power and energy for the loads that we wanted to feed with the off-grid solar system, and how to design some parameters related to the solar panel. Alright, now and firstly we need to calculate the total loads that we need to supply. And this is determined according to the case you are facing, which means that this depends on the customer who wanted to make a solar system. So suppose that the customer told you that he needs to make a solar system that feeds his home. Now the first step, you will ask him what are the total loads in his home that he wanted to supply. So you will make a table of the electric loads or devices of the customer as the first column. So suppose that the customer home loads are an air conditioner and some lamps and washing machine and so on. Now the second column will be the power for each load. Suppose that the air conditioner has a power of 2.5 kilowatts and the lamps have a power of 50 watts for each lamp and the washing machine have a power of 800 watts. Now the second column will be the quantity of each device. So we need to know what are the total number of devices that this customer has for each type of devices. For example, suppose that the customer has in his home 2 air conditioners and 10 lamps and only 1 washing machine. Here we did that to calculate the total power of the total loads. So the next column will be the total power, which are 2500 times 2, which will be 5000 watts, then 500 times 10, which will be 500 watts, and finally 800 watts. Now the next column will be the hours that each load will work each day. Therefore, suppose that the air conditioner will work for 6 hours and the lamps will work, for example, for 10 hours. And finally, the washing machine will work for 3 hours per day. So you may guess that we have determined the working duration for each load to calculate finally the energy that each load will consume per day. And actually that's right, as the energy equals to the power multiplied by the time. So it will be 6 times 5000, which will be 1000 watts hour for the air conditioner and 5000 watt hour for the lamps. And finally 1600 for the washing machine. And we will do so for all the loads that we have. Actually, I know that there is no home that has those 3 devices only, but I did this only for the demonstration purpose to give an example. So by this table, the important 2 columns that we have got are the total energy and the total power. So that's good for the first step. Now the second step is to design some parameters related to the solar panel. Actually, we have illustrated them before in details, but we will revise them now quickly to refresh our mind or for anyone who have jumped into this section directly. So the first thing is to get exactly the coordination of the place that we will design the solar system for it. And the coordination or the location is represented by the latitude and the longitude. And the second thing is the declination angle, which is the angle between the Earth axis and the universe axis. And it's equal to 23.5 times 360 over 365 times 284 plus D, where D is the number of day in the year, and we put it to be 21 of the December, because December has the lowest irradiation of the sun. So we make our design on the worst case to be on the safe side. Now the next parameter we need to design is the elevation angle alpha, which is the angle between the horizontal axis and the sun rays falling on the solar panel, and it's equal to 90 minus the latitude plus the declination angle. So we can get alpha now. And also the fourth parameter that we need is the tilted angle beta, which is the installation angle of the solar panel, or the angle between the ground and the solar panel. And finally, the last piece of information we need is S sub m, or the global tilted irradiation, which is the total number of hours that has the maximum irradiation of the sun rays on the solar panel when the solar rays are exactly perpendicular to the solar panel. So it's equal to S sub h times sine alpha plus beta over sine alpha. And we are calculating the global tilted irradiation or the peak sun hours 12 times because we calculate it each month of the 12 months in the year as we learned it before. So those are the parameters that we need to calculate in the second step of the GRID solar system design. And that's about the first 2 steps of the designing of the off-grid solar system. And at this point we have finished. So on the next tutorial we will continue illustrating some other steps and the designing of the off-grid photovoltaic solar system. Hope that's clear right now, and this is the website that we have got the photos from it. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In the previous tutorial we illustrated the first 2 steps of the off-grid solar system design. And on this tutorial we will continue illustrating those steps. So fasten your pill and let's get started. The third step that we have now is to calculate the solar system efficiency. I'm hearing you now saying that why we need to calculate the system efficiency. So let's take an example to know accurately what is the system efficiency. Suppose that we have some off-grid loads that has a total power of 10,000 watts. So we have bought some solar system panels that takes the power from the sun of 10,000 watts. So the output of the system will be 10,000 watts as the input, and the story has ended. Actually, this is a theoretical story that cannot be applied in the real world. This is because if we have a system that has an input of 10k watts equals to the output, which is also 10k watts, so the efficiency at this condition will be 100%, which means that there is no losses in the system. But in fact, there is no real system that has an efficiency of 100% or has no power losses. So we must make our calculations according to the system efficiency. So suppose that the solar system efficiency is 80% and we need the output power that reaches the electrical devices to be 10k watts. Since there will be losses of 20%, so this means that the solar system losses will be 2000 watts. So at this point, the input power that the solar system panel must receive will be the output plus the losses. So it will be 10,000 plus 2000, which is 12,000 watts. Therefore, in our case, the input power must be 12k watts or higher to get an output power of 10k watts. And if the input power is less than 12k watts, so the output power will be less than 10k watts, so it will be insufficient for feeding our loads. So at conclusion, we calculate the system efficiency to know what is the input must be to get the needed output. Now we need to ask how to calculate or how to get the efficiency. Here we can get the efficiency by getting the solar system losses, as the efficiency equals to the output power over the input power. But the output power equals to the input power minus the losses in the system. So we need to know what are the losses in the solar system and how to calculate it. Now the first loss comes of the solar panel, and the second loss comes of the charger controller, and the third loss comes of the batteries, and the inverter also will have some losses, and finally the cables that transmit this power will have some losses, whether they are DC or AC cables. Therefore, by calculating those losses, we can calculate the system efficiency. Alright, let's start now with the panel losses. The first thing that affects the panel losses output power is the panel temperature. This is because there is an inverse relation between the panel output power and the system panel temperature. Here, when the panel temperature increases, the output power will decrease and vice versa. Now we have two methods for calculating the panel losses due to the increasing temperature. The first method says that each increase of the location temperature by 1 degree Celsius will increase the panel's losses by a percentage, which is the temperature coefficient of maximum power. So when reforming this sentence, its equation will be the maximum temperature of the installation location minus 25, as 25 is the ideal temperature of the location, or the standard temperature to get the ideal output power. And this value will be multiplied by the temperature coefficient of the power, but at the maximum power, or it's called here, this coefficient is TCP. And we are getting the TCP from the panel datasheet as we learned it before. So we are choosing the location temperature as its maximum value to get the worst case or to get the higher losses, to make our design at its higher value of losses for us to be in the safe side for the design. But this method is an approximate one that we are using according to the experience, but it's not a scientific method, or it doesn't give some very accurate results. Here we say that it gives some approximate result. So for this reason, we have the second method for calculating the solar panels, which says that each increase of the panel temperature by 1 degree Celsius higher than the nominal operating cell temperature will increase, or it will affect the panel losses by a percentage of the temperature coefficient of the power at the maximum power. So at this method, we are comparing two temperature values of the solar panel, which are the cell temperature itself and the nominal operating cell temperature, or the cell temperature at the ideal case of working. While at the first method we were comparing two values of the temperature related to the location temperature, which were the maximum location temperature and 25. And 25, as we mentioned, is the ideal temperature of the location. But here in this second method, we need to know how to calculate the panel temperature or the cell temperature itself. So it's equal to the ambient temperature plus G times the nominal operating cell temperature over 800. But what are those two parameters, the ambient temperature and G? So the ambient temperature is the actual temperature of the location, and G is the irradiation of the sun at the optimal case or at the ideal solar condition, and its unit is watt for each meter squared, and we make it to P800 as this is the ideal case for the ideal testing condition. So it will be cancelled with the 800 on the denominator. Now we are ready to calculate the panel losses, which equals to the cell temperature minus the NOCT times the temperature coefficient of the power, which determines the losses in the power of each increase in the temperature of 1 degree. And both of those temperatures are related to the solar panel itself, not the surrounding temperature. Now the next losses related to the solar panel is the losses due to the dust that accumulates on the panel surface. Because this dust decreases the sun rays that reaches the solar panel, so it also decreases the output power in terms. And of the practical experience, we take the dust losses and the cable losses, both of them to be 3%. Now the second thing that has losses is the charger controller, and we got its efficiency as a given from the datasheet. But if it's not available in the datasheet, we consider it to be 5% also of the practical experience. But this is the worst case for us to be in the safe side and for taking the highest losses. Now the next losses that we have is the battery losses, and we will calculate it at the step of the battery sizing, not now. This is because we will get some accurate results when calculating the battery losses when designing the batteries itself and knowing exactly what is the number of batteries that we need to use. And now the last step that we have is the inverter losses, and it's given also from its datasheet, but if it's not available for us, we take it at its maximum value, which is 15%. And you will notice that the inverter takes the maximum value of the losses in the system. And this is true because the fact that the inverter is a power electronic semiconductor device that converts the total power of the system, so it has the most losses due to its conversion from DC power to the AC power. And at conclusion, the total losses percentage will be the panel, the charger, batteries, inverter, and cable losses. So at this point we have finished. And those are the websites for the photos that we have used in this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will continue illustrating the steps of designing any off-grid solar system. On the previous tutorial we illustrated the first 3 steps, which were how to calculate the load's power and energy, how to calculate some parameters related to the off-grid solar system like the required angles and the coordination, and how to calculate the system efficiency. And now let's continue those steps, so fasten your belt and let's get started. The aim of this tutorial is to know how to design the required panel system that will receive the solar radiation energy and convert it to the required electrical energy. So let's start with the 4th step. Suppose now that we wanted to get the number of panels that will receive the solar energy. So how can we get it? Here we need to link between it and anything that we can calculate to be able to get it, or we need to make a relation between the number of the required panels and any other known parameter. But we know previously or logically that if we have a small number of panels, the input power will be small, while if we have a large number of panels, the input power will be large. This is because the panels are the passage or the pipe that convert the solar energy to an electrical energy. So if we increase its capacity by increasing the number of panels, the input power at this condition will increase. So we consider now that the number of panels is equivalent to the input power to the solar system, Therefore, our aim now is to get the input power to the system. But we know of the previous tutorial that the efficiency equals to the output power over the input power. So when rearranging this equation, the input power will equal to the output power over the efficiency. Now we need to do the same thing, which is to get a relation between the output power and another known thing. So if you think a little bit, you will know that the output power is proportional to the electrical loads that we need to feed. So this means if we have a small number of loads, the required output power will be small, and if we have a large value of loads, at this condition the required output power will be large. So we can conclude that the output power is proportional to the loads that we wanted to feed. But if you remember of the previous tutorial, the load's power depends mainly on the energy that this load will consume. So we can say that the load's power equal to the load's energy that we have calculated before from the table over a time. And this is because the power equal the energy over a time. But at the first glance you will say that this time is equal to the load's time that those loads will work on. But this is totally wrong. This is because we are calculating the power relating to the solar panel. So this time will be the time that those panels will receive the energy at it. And we know that those panels will receive the power for an equivalent time equals to the peak sun hour, which is S sub m. So the load's equivalent power will equal to the total load's energy over the peak sun hour. So when substituting back on the input power equation, the input power will equal to the load's energy over the efficiency times the peak sun hour. And at this point we managed to get the input power because we have got those parameters, the total energy, the efficiency, and S sub m. So we have got them from the previous 3 steps. Now the number of panels will equal to the input power over the power of a single panel. This is because each panel will contribute in the input power by a fixed value and the total power equal to the sum of each single panel power. So the number of panels equals to the total power distributed on each panel power. And this value of each panel power is given from the panel datasheet. Alright, that's good about the panel's design, and at this point we have finished. So on the next tutorial we will continue those steps by illustrating the 5th step related to the battery's design of the off-grid solar system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will continue illustrating the steps of designing any off-grid solar system. On the previous tutorial, we illustrated the 4th step at which we knew how to design the panel system and detect its number and sizing. And now let's continue those steps, so fasten your pill and let's get started. The aim of this tutorial is to know how to design the required battery system that will store the electrical energy to supply the loads. So let's go ahead. First of all, any battery is described mainly by its ampere hour. So this is the most important parameter to buy the battery according to it. And the ampere describes the capacity of the battery or the amount of electrical charge that can be stored in the battery. For example, a small battery will have a capacity of 20 ampere, as 20 ampere is the maximum capacity that this battery is designed to store, while another battery will store 60 ampere, so its capacity is medium as it's designed to store up to 60 ampere on it. And if we try to supply it with much more electrical current than 60 ampere, it will not be charged as it have been saturated with 60 ampere. And another battery will have a large capacity of 100 ampere and so on. Now the second term is the hours, which is the charging or the discharging time, as the capacity of a battery is related to a time that this battery will consume. So this battery will consume this time to be charged by this capacity, for example. So suppose that we have a battery with 60 ampere hour. So this means that this battery will lose a time of an hour to be charged with 60 ampere. And also it will take a time of 30 minutes to be charged only by its half capacity of 30 ampere. So we conclude that the ampere hour of a battery is the charging or the discharging capacity related to the time that this battery is charged or discharged at it. Now we need to know how to get the total ampere hour of a battery system and the off-grid solar system. Here we say the total ampere hour, not only the ampere hour, because the battery system will have more than one battery. There may be 50 batteries, 70 batteries, 20 batteries, or any number according to the system capacity. So what I want you to understand is to distinguish between the single battery ampere hour and the total batteries ampere hour. So let's now deduce the total ampere hour for the total battery system. Previously, we know that the energy for any electrical device equals to the power that this device have multiplied by the time that this device will consume the energy at it. But the power equals to the voltage of the device multiplied by the current that this device will draw. Now if our electrical devices are some batteries, so the current multiplied by the time will be the total ampere hours of that battery. So when we write this equation, the total ampere hour of the batteries will be the total energy over the pass voltage. Here the energy on the numerator is the load energy that we have calculated on the first step, and the reason to consider the total load energy is that those batteries will feed the loads directly through the inverter. So the total ampere hour of the batteries must be designed to be sufficient for supplying the total loads. Also on the denominator we have the pass voltage. But what is the pass voltage, or what is the difference between it and the single battery voltage? Here we can illustrate with this example. Suppose that we have a battery system in an off-grid solar system, and this battery system consists of 4 batteries, and the voltage of each single battery is 12 volts as you see here. Also, as you see, those batteries are connected in parallel, which means that all positive terminals of all batteries are connected to each other with this white cable, and also each negative terminal of each batteries are connected to each other with this black cable here. So at this condition, the total equivalent voltage of those battery system will be only 12 volts, which is the same voltage of the single battery. This is because at the parallel connection, the total voltage will be the single battery voltage. Therefore, we say that the pass voltage now equals to the total system voltage, which is 12 volts. Now suppose that we have another case at which the batteries are connected in series. So the total system voltage will be the sum of each battery voltage, which is 12 multiplied by 4, which will be 48 volts. Therefore, at this condition, the pass voltage will be the total system voltage, which is 48 volts. So we conclude that the pass voltage is the total system voltage, and in some cases it will be different from each single battery voltage. But do you think that we have indeed reached the final equation for the total ampere hour of the battery system? Actually no, as the total ampere hour is not equal only the total load energy over the pass voltage. This is because the batteries has an efficiency that must be taken in consideration, and also there are some other considerations that we must take into our design. So let's hit it now. The first factor that affects the total capacity of the batteries is the autonomy days, or it's called the reverse days. And this factor is used to compensate the days at which the sun will not appear for a period of time, and this happens due to some reasons related to the extreme weather like the clouds in the sky or the heavy rain. So by the autonomy days factor, we suppose that there is an exceptional weather that prevents the solar rays to fall on the solar panels, and we consider this factor to be in range from 1.5 till 2. So this means that we need the battery sizing to be larger by 1.5 until doubling the battery size, and this is to make the batteries charging faster and the sun shining period to avoid the darkness period during the day due to the weather changes. Now the second parameter which affects the battery sizing is the DOD, or it's called the depth of discharge. Here the depth of discharge is a factor that supposes there is a fixed value of a charge in the battery that will not be used, or it will be stored in the batteries and not discharged. So when I say the depth of discharge is 80%, this means 80% of the battery's charge will be charged or discharged, while a value of 20% of the battery will not be used or it will not be charged or discharged. And also if we have another depth of discharge of 50%, this means only 50% of the battery will be available to be charged or discharged, while the other 50% will not be used. But you may ask, why we need to have a demand value or a fixed value in the battery that will not be discharged? So this is because we need to care about the battery life, as when the discharged value increases, this will affect the battery life badly. And when the DOD decreases, this will increase the battery life. So by having a lower value of DOD, we will increase the battery lifetime. But note also, on the other hand, this will increase the cost of the batteries, as we need a larger number of batteries when having a lower value of DOD. So we need to make a balance between the battery's lifetime care and the battery's total cost. And for this reason, we consider the DOD to be between 0.5 and 0.8, where 0.8 is the most bad value that decreases the battery's life but having a lower battery's price, while 0.5 is the best value that will give us the best lifetime, but on the other hand it will give us the highest battery sizing than the highest price. Now the last parameter related to the battery's ampere hour is the battery's efficiency, as the battery's efficiency is used to compensate the losses in the battery during the charging and the discharging operation. But you may ask why there is some losses in the batteries during the charging or the discharging operation. So this is because the charging or discharging time may change from one case to another. Suppose that we have a battery that its capacity is 150 ampere hour. Now if we discharged this battery in 30 hours, it will give us 150 ampere. But if we discharged this battery in 22 hours, it will give us 120 ampere hour, although its standard capacity is 150 ampere hour. Also, if you discharged it in a period of 90 hours, it will give you only 100 ampere hour. So this means when the discharging time decreases, and therefore the amount of a charge that you will get benefit from will decrease. But a question may hit your mind now. Why the discharging time decreases or increases, or why the discharging time is not a constant value? So this is because the number of loads that is applied that we need to supply may vary during the working operation. Suppose that all devices are energized at the same time, so the discharging time of the batteries will increase. While if only half of the loads are on at the same time, the discharging time of the batteries will increase at this condition. So if we wanted to get the efficiency, we consider it to be 85%, and this is in case of we don't have a data sheet of the batteries. But in case of we have the data sheet of the batteries, we detect the lowest time that those batteries will be discharged at, which from the loads that we have calculated before. So from the loads we can detect the lowest time that those loads will consume, and then we see from the data sheet the equivalent ampere hour of the battery at this specified time. Then we say that the efficiency equals to the ampere hour at that specific time over the standard ampere hour of the battery. So the actual value of ampere hour is the value of ampere hour corresponding to the time that your loads will consume the energy at it, and the maximum value of ampere hour is the value of ampere hour that you put those batteries according to it. For example, if you discharged the batteries at a period of 22 hours, So the battery efficiency will be 120 over 150 and so on. Now after getting the total ampere hour of the batteries, we need to know what will be specifically the other characteristic of the batteries, like the connection of the batteries and so on. So the number of the parallel branches in the batteries system equals to the total ampere hour over the ampere hour of each single branch. This is because the total ampere hour is the sum of each branch ampere hour. So if we divided the total ampere hour of the total batteries over the ampere hour of each branch, we will get each branch ampere hour at this point. But how can we get the ampere hour of each branch? Okay, the ampere hour of each branch equals to each single battery ampere hour times the number of batteries. This is because all batteries in each branch will be connected in series. So the total ampere hour of each branch is the sum of each battery ampere hour. But also we're still asking, how can we specify the number of batteries in each branch? So the number of batteries in each branch equals to the bus voltage over the battery voltage. And we knew previously the difference between the bus voltage and each single battery voltage. Now I'm hearing you asking how to specify the bus voltage. So the bus voltage is specified mainly according to the inverter voltage. This is because the inverter input voltage must be the same as the battery's voltage, because the inverter is connected directly to the batteries. So we specify the bus voltage according to the features of the inverter that we have both. That's good. Now the final thing remains to us to design a full battery system is to know what is the total number of the batteries. Easily we say that the total number of the batteries equals to the number of the batteries in each branch times the number of parallel branches. Now let's finish with an example that will reinforce those equations to design the battery system. Suppose that we have an inverter that is connected to the battery system and the inverter voltage is 48 volts, while each single battery voltage is 12 volts only. And the ampere hour of each single battery is 100 ampere hour. So at this condition, the first thing that we will deduce is the bus voltage, which will be like the inverter voltage, which is 48 volts. Now the number of the batteries in each branch will be the bus voltage over the battery's voltage, which is 48 volts over 12 volts, which equal to 4 batteries in each branch. Also, the ampere hour of each branch will be the ampere hour of each battery times the number of batteries in each branch, which is 100 ampere hour times 4, which is 400 ampere hour for each branch. Now the number of parallel branches will equal to the total ampere hour over each branch ampere hour. So suppose that the total required ampere hour, which we have calculated from our loads, is 800 ampere hours. So the number of parallel branches will be 800 over 400, which will be 2 parallel branches. And finally, the total number of batteries will be 2 branches multiplied by 4 in each branch, so it will be 8 batteries. So the final design will be like that one, 2 parallel branches and 4 series batteries in each branch to give us our total bus voltage of 48 volts. So that was about the batteries design in the off-grid solar system, and at this point we have finished. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will continue illustrating the steps of designing any off-grid solar system. On the previous tutorials we illustrated the first 5 steps of this design. And now let's continue those steps, so fasten your belt and let's get started. The aim of this tutorial is to know how to design the required charger controller system that will receive the electrical power from the solar panels and regulates it to charge the batteries with this power. And also how to design the required inverter system that will convert the electrical energy from its DC form to the AC form to feed the AC loads with this energy. So let's start with the 6th step. As we know previously, the charger function is to receive the energy from the panels and control the charging operation of the batteries, And when the batteries are fully charged, the charger will sense that and it will stop the charging operation. Now, if we wanted to calculate the charger sizing, it will be sized according to its voltage and current. So the voltage will be the same as the bus voltage, and the current will be the capacity of the charger that it can pass during its working operation. Now it's equal the panel's power over the bus voltage, and the panel's power is calculated easily by multiplying the number of solar panels by each solar panel power. But you may notice that we have calculated the minimum charging current of the charger, and this is because we suppose that the charger rating will be the same rating of the panels. But you know, the panel's rating may increase by the time according to its performance. So we are calculating the minimum following current from the panels to the charger. Now you may ask, why we calculated the charger current according to the panel's power, not the battery's power? This is because if the following current from the panels is 100 ampere, for example, there will be a lost value of this current and the charger controller, suppose that its value is 5 ampere, so the current that reaches the batteries is only 95 ampere, and this is not the 100 ampere as the actual rating of a panel. So we must design the charger rating according to its input current, which will be larger than the output current from it. As if we design the charger with a lower current than what it can withstand, the charger may not be able to withstand the higher rating of the current. Now suppose that we calculated the charger rating and it becomes 23 amperes, and the available ratings of the charger to pi is 20 amperes and 30 amperes. So the value that must be chosen is the 30 ampere, and it will be wrong to choose the 20 ampere. This is because we designed the charger rating according to its minimum value. So it will be wrong to have a lower value than the minimum value. But it will be a good idea to have a larger value than the rated value or than the design value. And we do that to be on the safe side, and also to avoid any case of overloading on the charger as a reason of increasing the panel's power if it becomes larger for any case. Alright, now let's move to the 7th step to design the inverter and know its exactly sizing. As we knew, the inverter takes its input from the batteries, then it supplies the load directly. So it converts the DC power to the AC power. And because the inverter is supplying the loads directly, we suppose its power rating to be the load's power multiplied by a safety factor. And this safety factor because there may be a sudden increase in the load's power for any reason. So we increase the inverter power to avoid the load change. So we consider this safety factor to be in range from 1.2 to 1.3. But this is not the full formula because the inverter sizing must be increased also by dividing it by the power factor. And the reason for that is the fact that the inverter is an AC device, and any AC device will have a power factor that specifies the amount of active power that this device will exactly get benefit from. Suppose that this power factor of the inverter is 0.8. And suppose that the input power to the inverter is 100 volt ampere, so we can consider it to be the complex power S or to be the active power because the input power is DC, not AC. So there will be no power factor for the DC power. Therefore S or the complex power will equal to P. Now as we mentioned, the power factor is 0.8. And this means the power factor angle will be the cosine inverse of 0.8, which will be 36.8. So the reactive power will be 100 times sine 36.8, which is 60 volt ampere. So 60 volt ampere will be neglected, and the active power that this load will get benefit from will equal to the complex power, which is 100 volt ampere times the power factor, so it will be 80 volt ampere. So we note that if the loads require a power of 80 volt ampere, the input power must be larger to be 100 volt ampere to compensate this reactive power losses. And for this reason, the inverter sizing must be divided by the power factor to increase the sizing to withstand the larger power. And also, it's recommended to get a larger inverter size to withstand the extensions or the increasing in the loads to avoid the need of buying another inverter, and this is in case of we predict that there may be some extensions in the loads in our system in the future. Now, after getting all the required components of the off-grid solar system, we need to see the full picture to know how those elements interact with each other. So we will start with the inverter as it specifies the bus voltage, and also the other components depends on the bus voltage and its design. Here if we say that the inverter input DC voltage is 48 volts, so the bus voltage will be 48 volts and the output voltage will be the three-phase AC voltage. Suppose also that those are the output three phases, or S and T, that will feed the AC loads. So this is the input bus voltage of the inverter, and this is the output three phases. Now suppose that we design the battery system and we found that the single battery voltage is 12 volts. So we need 4 series batteries to get the full bus voltage of 48 volts, which is the bus voltage. Now suppose that we have put the charger controller with an input voltage of 48 volts. So if we design the charger controller to get the total current that we need, that may be for example 60 ampere, and each charger gives us 30 ampere as a rated current, so we need now 2 charger controllers to give us the needed 60 ampere. So those 2 chargers must be in parallel to give us the fixed bus voltage, which is 48 volts, as the parallel connection will have the same voltage of each element, which is 48 volts. Now let's move to the panel design. Suppose that we calculated the needed number of panels, and there are 6 panels, and each panel voltage is 24 volts. So at this condition, there must be 2 panels in series in each branch and 3 parallel branches, so each branch voltage will be 24 times 2, which will be 48 volts. And this finally will give us a total bus voltage of 48 volts, like all other system of the charger, batteries, and inverters. So what we wanted to say is that the components of each system must be designed to get the final output voltage to be the same of the bus voltage. This is because all of them are connected to each other, and the points that are connected to each other must have the same voltage. So we made the required modifications in the series and parallel connections to get the final required bus voltage. Now you may wonder, what is the principle according to it we choose the inverter voltage, which will be the bus voltage? So is it to be 12 volts, 24 volts, 48 volts? Or how can we choose it? In general, we say that it's better to have the inverter voltage to be 48 volts, and this is because we have a constant transmitted power. But the power equals to the voltage multiplied by the current. So when the voltage increases, the current will decrease to get a constant power, as we mentioned. So when the current decreases, the power losses will decrease, as the power losses equals to the current square times the resistance. So when the power losses decreases, the system efficiency will increase. And this is our aim, is to get the most efficient system with the lowest losses. Also, another benefit is that when the current decreases, the cable sizing will decrease, as we need now a smaller cross-sectional area of the cables because the current has been decreased. So we save money now to have a smaller sizing of the cables. So that's about the advantages of having a larger inverter voltage. But there is nothing with only advantages, as there may be some disadvantages, as there must be some disadvantages of having a larger bus voltage. So when the bus voltage increases, this will increase the inverter price. Now the last thing that you might notice during this design is that The batteries and the panels design depends mainly on the energy, not the power. For the panels, if we increase the number of panels, we are increasing the time that those panels will charge the electric current through it. And for the same charging period, when increasing the number of panels, the charge will increase. And we can feed more electric loads with larger energy, and this proves that the panel sizing depends on the energy. Also, the same thing with the batteries, as if we have a larger number of the batteries, it will be discharged or supplying the loads in a larger time. So this means we are increasing the energy to feed much loads by increasing the battery sizing. Now the other two parts that depends on the power in designing, not the energy, are the inverter and the charger controller. This is because both of them works only as a passage or a tube that links between two other components. Therefore, they must withstand the power that follows through them regardless to the time that this power will follow through them at which. So the time is not a matter in the charger controller and inverter design, but only the power capacity for both of them. Okay, that was about the 7th step of the off-grid solar system. And I think that's enough till now. Basically right now, thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In this tutorial, as we are accustomed, we will continue illustrating the steps of designing any off-grid solar system. On the previous tutorials, we illustrated the first 7th step of this design, and now let's continue those steps. So fasten your pill and let's get it started. The aim of this tutorial is to know how to get the total area required for constructing the off-grid solar system. So let's go ahead. When we are talking about the area that the solar system needs, we are discussing the area that we need for the components to put the solar components at it. So let's start thinking step by step. If we are talking about the charger controller, in fact, its size and number that we need will not be large, so it will not consume a large area, and it's suitable to put it in between with the other components. So the charger not the matter due to its smaller size. Also the same thing with the batteries and inverters, as their size will be small and also their numbers. So the batteries can be constructed in a room to protect it from the sun rays to increase its lifetime. Therefore, what we want to say is that all the solar system components will take a smaller area, and only the part that will take a large area is the solar panels itself. This is because we need to spread the solar panels at a large area to get the most benefit of the solar rays, as when the area increases, the solar energy that falls on those panels will increase. So let's start to know how to calculate this area. The first thing we need to know is how to calculate the distance between each two panels. Suppose now a case at which we have two adjacent panels and there is a narrow distance between each of them, so there will be no problem for the forward panels because all the sun rays will fall into it as it's in front of the sun directly. But the problem will be on the back panel because there will be a smaller distance between the two panels, so some of the solar rays will fall on the back panel, but the other rays will not fall into it. This is because the forward panel prevents the solar rays to fall into the back panel. So at conclusion, we will get benefit from a part of the back panels while the other part will have a shadow into it which prevents the solar rays to fall into it. And as we mentioned, this problem is caused due to the narrow distance between the two panels. So to solve this problem, we need to get the minimum suitable distance between the two panels that make all the solar rays to fall into the back panel. Or in other words, we need to get the distance between the two adjacent panels that makes no shadow from the forward panel to get or to fall into the backward panel. And for this reason, we suppose that the distance between each two panels is the maximum shadow that can be obtained during the year. So if we detected the maximum shadow that can occur, and we suppose that this shadow will be on the ground. So at this point, when detecting this shadow on the ground, there will be no shadow that lays on the backward panel. And at this condition, we will ensure that at the worst case, there will be no shadow on the backward panel. So we are getting the most benefit of the panel's available area. Now the crucial question is that how to get the largest shadow that can occur during the year. So as we learned before, the worst day in the year that had the worst solar radiation is 21 of December. So at this worst radiation day, we will have the longest shadow in the year. So we will detect the longest shadow in the year by detecting the angle alpha at this day. And because alpha is the angle between the sun rays and the ground, so when getting alpha at 21 December, we are getting at this point the longest shadow. But in fact, we have detected alpha at 21 December from the second step of this design, if you remember. So we have now this triangle, and suppose that this shadow area on the ground to px, and this is distance x is the unknown distance that we need to calculate. And here y is the panel length, and it's available from the panel data sheet, so it's a known distance. And also the angle alpha is known as we mentioned, and beta also is known from the second step. Now from the trigonometric laws, we can say is that x over sine the opposite angle, which is 180 minus alpha plus beta, equals y over the opposite angle, which is sine alpha. So all the parameters of this equation is known except the shadow length or the distance between the two panels. So when we reform this equation, it will be, or we will have x equal y times sine 180 minus alpha plus beta over sine alpha. So by this way, we can detect the minimum available distance between each two panels. Alright. At this point, we are ready to get the area that each single panel will occupy. So suppose that those are the two adjacent panels, and the area for single panels equals to the panel width, which is given also from the panel data sheet, times the distance x between the two panels that we have just calculated. And after getting each single panel area, the total area is very easy now, as it's equal to each single panel area times the number of panels. So this is the total area that all the panels need to occupy. Now let's take some notes related to the area design. In some cases, the customer who wanted to make a solar system design may have a smaller area than the required area to construct his project. So the customer area in some cases is not sufficient. Suppose that the customer has a roof that he needs to spread the panels into it, so his electrical loads need a specific number of panels, but when you calculated the area for those panels, it becomes larger than the roof area. So at this point, the available area is smaller than the required area with a reasonable or a relative smaller value. At this point, we have some options to solve this problem. The first solution is that if you made your design on the polycrystalline panels, you can replace it with the monocrystalline panels. This is because the mono panels will have a larger output power than the poly panels, as we learned previously. And this means we will have a smaller area for the customer to construct this project. And now the second solution is that you can try to use some panels with a larger output power. But you may say, now when the panel's power increases, the area of the panel must increase. And at this point, we still have the same problem. But I will tell you that this is not totally right, because when the panel's power increases, the area of the panel will increase, but with a smaller percentage. So we can have a higher output power of the panels with a small increase in the panel size. So this can be a solution. And also another benefit of having a larger panel is that the watt price in the larger panel is cheaper than the watt price in the smaller panel size. So this can give us also more economic solution. But if those two solutions is not available, you can ask the customer to give up some of his loads that he need to feed with the solar system. So he can supply some of his loads from the utility, and supply the other loads from the solar panels. And of course, this is in case it's available for the customer according to his case. So that was about the designing area for the solar panels, and I think that's enough till now, and at this point we are finished. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will start on the 9th step of the off-grid solar system design, which will be the last step of our design. And at this point we need specially to characterize or specify the cable sizing and the protection devices. So our aim now is to know how to select a cable that will carry the electric current from one component to the other, and also we will know what are the electrical devices that we need as a protection for our system. But at first, let's know in details how the solar system components are connected to each other. And for this reason, we need to draw a full diagram for the solar system that specifies all the details that we need in our design. And the powerful software for drawing is the AutoCAD. So let's go ahead. We have now the main four modules of the off-grid solar system, which are the panels, the charger controller, the batteries, and the inverter. So let's see those systems closely. Here, those are the panels, and we design it to have the final pulse voltage of 48 volts. So here those are the panels, and we design them to have the final voltage, which is the pulse voltage, which is 48 volts in our case here. So each single panel, as you see here, is 12 volts, and we need 4 panels in each branch to get the final 48 volts. Here each panel has a positive terminal and a negative terminal, so for the series connection, each positive for the first panel is connected to each negative for the second panel. Here this positive is connected to this negative of this second panel, so we can get this series branch. But as you see, we have the final parallel connection. The positive for the first branch is connected to the positive for the second branch, and here also the negative for the first branch is connected to the negative for the second branch. So by those main cables here, this CN1 and this red one, we can get the final pulse voltage, which carries the final current from the battery system to the charger controller system. And our aim now is to know how to get the sizing of those cables related to those panels. For example, this cables here, this entire cables that carries the current from one panel to the other will have a different sizing from the cable that carries the full current. Here this is a main cable, and it will have a different sizing or a different cross-sectional area from this entire cable. And this is because a cable like this one is designed to carry only the power for this branch, but the cable like this one here is designed to carry the full branch's power. So if we have here, for example, 20 branches or 20 parallel branches, this main cable is designed to carry all those 20 parallel branches. While, for example, this cable is designed only to carry this branch or this series branch current. So this one will have the higher cross-sectional area than this one. And now after getting out of the solar panel, we will transmit the power to the charger controller system like this one here. But there is a distribution panel, or it's called the tie point, that connects the panel system with the charger controller. And the job of this distribution panel is to provide a protection tool for our system. This is because this panel has a fuse inside it, and the job of this fuse is to cut the circuit in case of there is a large current that follows through the system. For example, suppose that there is a case at which we have a short circuit in those cables, so the short circuit is a connection between those two cables, for example, so the positive one is connected to the negative one wrongly by any reason, but this is a very bad case at which we have a very large current that follows through the circuit. So there will be an excessive current or very huge current that follows through this panel to the charger, or from the panel system to the charger in case of we have a short circuit. And there is nothing to prevent it. At this point, the charger and the cables will be damaged or it may burn out. So we need a fuse as a protection device to protect the system element from any damage due to the high current. And on the next tutorial, we will learn how to design this fuse rating on this panel and know how to calculate it. Now the next part is the charger controller. Here we can zoom out to see it exactly, and it has 6 terminals as we learned it before, 2 for the input and 2 for the output and 2 for this load. Also, after the charger controller, we have another protection distribution panel with the same idea to have some fuses inside it to protect the circuit from any overload or any short circuit condition. And this distribution and protection panel links between the charger controller and the battery system. Now, when moving to the battery system, we will have 2 batteries in parallel, and each of them has a voltage of 48 volts, so the total voltage will be the pulse voltage as they are in parallel. Also, after the batteries, we have another protection here circuit, so it links the batteries with the inverter. And finally, this is our inverter, which converts from the DC power to the AC power, and here it converts the 48 volts to the 380 volts or the 220 volts for the other system. And now the inverter delivers its power to the AC distribution panel like this one here, and the job of this distribution panel is to feed the AC load that we need to supply from our solar system panel. And this AC distribution panel has a small thing that differentiates it between the DC distribution panel, which is that here this is a circuit breaker, or the protection device is a circuit breaker like this one here. While on the DC distribution panel, the fuse was the protection device. So here in the AC distribution panel, we have the circuit breaker for the protection, while here on the DC distribution panel, we have the fuse as a protection device. So this is the single line diagram for the AC circuit out of the inverter, or it takes its power from the inverter. And now suppose that the output of the inverter is a 3-phase, so it enters the distribution panel to be connected with the main circuit breaker of the distribution panel like this one here. This is the main circuit breaker. Then this busbar, as you see here, for the distribution panel that connects, or it can connect the loads to the distribution panel, and each load needs also another circuit breaker as you see. So this is the main circuit breaker, this is the busbar that connects our load with the main panel, and those are some circuit breakers related to each load. So load 1 has a circuit breaker, load 2 has another circuit breaker to connect it, and load 3 has a third circuit breaker to connect it. But this main circuit breaker is the main circuit breaker that control the full panel. So the circuit breaker control the full panel, while each of those circuit breakers control this load or control one load only. So our aim on the next tutorial is to know how to design this distribution panel and how to get the sizing for each circuit breaker for them like this one or this one, and also how to get the sizing for the fuses on the DC protection panel. And also we will know how to get all the cables required in the AC system and its sizing, and how to specify the cross-sectional area for the 3-phase cables like this one here. This is a 3-phase cable. We will learn how to get its cross-sectional area and how to get the cross-sectional area for the single-phase cable, and so on. And as you notice here, those 3 dashed lines means that this is a 3-phase cable, as the power output from the inverter is a 3-phase power, while each load of them has only 2 dashed lines. So this means that this load works with only single phase, as it has 2 lines here, or 2 dashed lines, one for the line and one for the neutral, while here those 3 lines, each of them for a single phase. So those are the 3 phases, R and S and T, but we are here designing a single line diagram, so we represent it by only a single line. So we can conclude here that between each two DC components like the panels and the charger, we have a DC protection panels. Here this DC protection panel lays between the panel system and the charger system, and also this another one is between the charger system and the battery system, and this other one is between the battery system and the inverter system. So between each two DC components we have a protection distribution panel or a DC protection distribution panel, and between our loads here and the inverter, so this is an AC power and those loads works with AC power, so logically between this one and this one we have an AC protection panel or an AC controlling panel. And our aim on the next tutorials is to get the sizing for those cables and fuses and circuit breakers, as this is the final step of the off-grid solar system design. So I think that's enough till now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will continue the 9th step of the off-grid solar system design. As on the previous tutorial we took a tour or an overview on the wiring diagram of the off-grid solar system, and now this is the time to design the rating and sizing of those components. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to know how to design the rating of the current required for the cables and the protection devices used in the connection between the different elements, and also we will learn how to design the standard rating for those elements to know how to select them from the market. And finally, we will learn how to select the suitable cross-sectional area for the cables through the fault system. Now let's start from the panel zone, as the panels are the first element for our design. So we need firstly to know what is the rated current that will pass through the series branch like this one here. So simply we say that the total current through each branch is the single panel rated current, and this is because they are connected in series, not parallel. And to get this value we can get it from the datasheet of the solar panels used. For example, from a datasheet we have a value of current of 6.1 ampere, and we selected the short circuit current as you see here to select the worst case or the largest current that can pass through the branch, as we must make the design on the worst case for us to be on the safe side. Now we need to calculate the fuse rating that is used in this design. And we use a fuse as we mentioned before because the DC power is protected by fuses, while the AC power is protected by the circuit breaker in most cases. So the fuse rating is equal to a safety factor times the rated current. And according to the IEC standard, this safety factor is equal to 1.25. So the value will be 6.1 times 1.25, which will be 7.6 ampere. And you may ask, why we need to multiply the rated current by a safety factor? So this is because this current is the current that the fuse will cut the circuit at which, and we need to give the fuse a range of the current before it cuts the circuit, as it must cut the circuit in case of overloading or short circuit condition. So we must ensure that this is a real overloading or short circuit condition by having a margin of increasing the current before the fuse explodes and it cuts the circuit. So the safety margin is 25% increasing than the rated current. And now we need to select the fuse rating, and this is because when you buy a fuse from the market, there will be some standard rating of the fuse ratings because not all the calculated values are available on the market. So the ratings of the fuses current on the market are here those values: 6 ampere, 10, 16, 20, 25, 32, 40 amperes, 50 ampere, 63, 80, 100, 125, 160, 200 till 1000 ampere. So those are the ranges that you can select from them on the market. Now to choose the fuse rating, we choose the nearest rating that's larger than the calculated value. So here it will be 10 ampere, which is the nearest largest rating than 7.6 ampere, which is the design value. Now, after getting the fuse rating, we need to select the cable rating that will carry that current. So the cable rating is equal to the fuse rating over a factor called the derating factor. And this derating factor is used to increase the cable current than the fuse rating because the cable may lay under the ground. In another case, it may be put in an area that has a larger heat, or it may be put in some ducts that increases the temperature. So all of those conditions will increase the cable resistance than the usual or the ideal case. So for this reason, we must choose a cable that can withstand a rating of the current larger than the normal rating, or to withstand those probable physical conditions. And we select this derating factor to be about 0.8. So the cable current at this condition equals to 10 over 0.8, which equals to 12.5 amperes. But you may ask now, why the cable current is larger than the fuse current? Here the fuse current that it will break the circuit after which is 10 amperes, while the cable current that it can withstand is 12.5 amperes. So this is because the fuse is designed mainly to protect the cable, so it must cut the circuit at a current less than the cable current to ensure that the cable has no damage when there is a fault condition. Now, after getting the cable current, we need to get the cross-sectional area of that cable, and we can get it easily from the cable catalog or the cable data sheet. So each company that manufacturing the cable has a data sheet for its products, and you can use it to get the cable cross-sectional area. For example, this is a data sheet for a cable, and we enter the table with the cable current to get its corresponding cross-sectional area. Here, if our cable is put inside a tube, so the nearest rating for our case is 13 ampere, and when accessing the cross-sectional area, it will be 1.5 millimeter square. So our cable cross-sectional area now is 1.5 millimeter square. But there is an important note here, which is that we are selecting now a single core cable. So we are entering the data sheet from a single core cable table. But each panel needs two cables, one for the positive terminal and one for the negative terminal. So when describing the cable that we have selected, it will be 2 times and brackets and 1 times 1 millimeter square. So 2 for the 2 cables and 1 times 1.5 means we are choosing a single core cable from the catalog, but we use a couple of those single core cables, one for the positive and one for the negative. Alright, we have just now selected the cables and the fuses for the series branch. So let's move a little bit to see how to choose the main cables used and the panel's connection and the main fuses for the main protection panel. Now, to calculate the rated current that this main cable will carry, it will be 2 times the rated current of the single panel. And this is because we have 2 parallel branches, but the current for the single branch is the single panel power. So the power for the 2 branches equals to the number of branches times each single panel power. So it's equal to 2 times 6.1, which is 12.2 amperes. Also, we will repeat the same equation as the fuse current equals to the rated current times the safety factor, which is 12.2 times 1.25, so it's equal to 15.2 amperes. So when selecting the nearest largest fuse rating, it will be 16 ampere. So the fuse used in this protection panel will have a rating of 16 ampere. But when calculating the cable current, it will be exactly as what we did for the series branch. So the cable current equals to the fuse current over the derating factor. Here it's 16 over 0.8, which is 20 amperes. And when selecting the suitable cross-sectional area from the table, as you see, we suppose that the cable will be installed in some means of the ducts or the pipes to save it from the external weather conditions. So when checking the pipe column, we find that the nearest current is 21 ampere and its corresponding cross-sectional area is 3 millimeters square. And the final description of the cable is it's 2 times 1 times 3 millimeters square. Now let's move a little bit to the next component, which is the charger controller. So if you think a little bit, you will find that the charger cables and its protection panel fuses will have the same rating of the panel's main cable. And this is logically because there is no change in the power or the voltage or the current. So the charger fuse rating and its cable cross-sectional area will be the same at the panel. Also, when moving to the next step, here when going left we will face the batteries, and the batteries has an input and an output. So for the batteries input, it will be the same as the charger output, which is mainly the same as the panel's main cables. So it also had the same rating which we had just calculated in the panel's main cables. Now when moving to the battery's output, we will find that we have a different rating than the battery's input cables. And this is because the input cable's current depends mainly on the panel's charging current, while the battery's output cable's power depends mainly on the inverter required power or the inverter required electric current. So the rated current for that branch will equal to the inverter power over the pass voltage. And after that, the fuse current equals to the same safety factor 1.25 times the fuse current. And finally, we select the fuse rating from the standard rating as we learned it before. Also, when we select the cable current and cross-sectional area, it will be by the same way with no changes. Also, when moving to the inverter zone, we have here the inverter input cable and panel sizing, which are the battery's output cable and protection panel itself. And this is because the output of the previous component is the input of the current component. So what we wanted to say is that there is no changes in the inverter input fuse or the input cable's rating, but the only change will be on the inverter output itself. And the first note here is that the inverter output is an AC power, not DC. So the rest of the rating will be AC power, not DC power. And for this reason, it will have some changes. Firstly, we need to calculate the output power, as the cable sizing depends mainly on the output power, which is the sum of the load's power. Here we have 3 loads, load 1, 2, 3. So we must sum them to get the total output power. And after calculating the sum of those loads' active power in kilowatts, we need to convert it to the complex power S, as the complex power equal to the apparent power over the power factor. And we suppose here the power factor to be 0.8. So after calculating the complex power in kilovolt ampere, now the rated current of that main cable will be 1.5 times the kilovolt ampere. Then we need to calculate the circuit breaker current, and we use a circuit breaker as we mentioned because we are on the AC zone, not the DC zone. So the circuit breaker current equals to the rated current times the same safety factor 1.25. And to detect the circuit breaker rating, it has the same standard as the fuse rating. And now to calculate the cable current, it's equal to the circuit breaker rating over the same derating factor 0.8. But the only change is the selection of the cable from the catalog, as here we are handling with the 3-phase output power. So the cable that we will use is a 3-phase cable with 4 cores, 3 for the 3 phases and 1 for the neutral. So when going to the catalog, we can jump to the 4-core cable and select by the same way as we learned it before. Now the last thing remaining for us is to calculate the cable and the circuit breaker for each load branch. And at this point we have 2 cases. The first one is that in case of we have a 3-phase load, so if our load we wanted to phase is a 3-phase load, at this condition the calculations will be exactly the same as what we did on the main inverter cable and the main distribution panel circuit breaker with no changes. Here we calculated the single load kilovolt ampere, and then the rated current equals to 1.5 times the kilovolt ampere of the single load, and after that the circuit breaker current is equals to 1.5 times the rated current, then selecting the circuit breaker, and finally jump to the 4th core cable to find the required cross-sectional area. Now the second case we have is if the load that we wanted to feed is a single phase load, not a 3-phase, and at this condition we will have only 2 changes. The first one is that the rated current will be 4.5 times the single load kilovolt ampere, not 1.5 as we did on the three-phase load. And secondly, when going to the cable selection, we will select a single core cable again, not a three-core cable. And this is because our load is a single phase load, so we need two cables, one for the line and the other one for the neutral. So we select two single core cables for this condition. So that's all about the cables and the protection devices designing of the off-grid solar system, and at this point we have finished. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorials we have learned the different steps of designing any off-grid solar system, and in this tutorial this is the time to practically apply all what we learned, as we will design a complete Excel program that is capable of calculating all the parameters required in the off-grid solar system. As you may know before, the manual calculations are very tiring and you may have some mistakes, and also if you need to make a new design, you need to repeat all the calculations the other time. So for those reasons, we will make a full automated Excel design that is capable of designing any required solar system, as you just need to enter the data as an input and the program will make all the required calculations. Now we will start with the first step, which is to specify the electrical loads, power and energy that you are making the solar design to feed them. So we suppose now we are making the design for a house and we need to feed the electrical appliances of that house with the solar design or the off-grid solar design. So let's specify this cell firstly and type loads. Then let's increase the font. And also we can make its style to be Century Gothic and increase the cell width. Then we can fill this cell with the move color, and also we can make the color to be white, and we can center the content of this cell. So that's good. Then for each device in the house, we need to enter its power in the watt, its quantity, and its number of working hours. So we need to know what's the hour that it will work during the day, and also its energy. So let's firstly copy the format of this cell, and let's make those 5 cells with the same format. Now we can change their color, for example, to be this blue one, and here we can type the power. Enter, and let's increase the cell width, and on the second cell the quantity, and on the third cell the hours, and on the next cell the total power in watts, and on the final cell we have the energy, and it will be in watt hour. Now let's select those cells, and we can make their border to be like this one here and press enter. That's good. Also we will type the different appliances in the home in that column here, so we can copy the cell format and drag down here for those cells. That's good. Now we can select them also, or select those ones and make them to be green, so we will fill them with the green color. Now for the first load that we have, it's a ceiling fan, so we type ceiling fan and press enter. Then increase the width, and its power is 70 watts, so we type here 70 and press enter. And its quantity is 3, so we type 3, as we have 3 ceiling fans in this house, for example, and the number of working time, so it may be 12 hours in the day, and press enter. Now we can select those 3 cells and increase their font, for example to P14, and we can make them also to be Century Gothic, and also we can pull them and center them. That's great. Now we will fill this table with the other devices we have, so we may have some lamps, and the power of each lamp is 20 watt, for example, and we have 10 lamps, so we type 10, and also its working hour may be 10 hours in the day, and also we may have some computers, and the power of each one may be 120 watts, and its quantity may be 2, and the number of working hours may be 8 hours in the day, and we may have also a washing machine, and its power is 70 watts, for example, and we have only one of it, and its number of working hour may be 2 hours, and also we may have a refrigerator, and its power in watts may be 130 watts, and its quantity is 1, so we have only one refrigerator in the house, and its number of working hours is 10 hours in the day. So you may ask, now the refrigerator is working all the day, so this is right, but the refrigerator is designed to work on about 10 hours in the day, so this is its internal design. Its motor is energized for a time and it's off for another time, so this is an automated process inside the refrigerator itself. Now we will have, or we may have also microwave, and its power is about 1200 watts, and its quantity is 1, and it will work, for example, for 1 hour a day. And we may have a vacuum machine or vacuum cleaner, and its power is also about 1200 watts, and we have also one vacuum cleaner, and we suppose that it will work for 0.5 hours, so it will work for a half hour in the day. And also we may have a hand mixer, and it will work for about 0.2 hours in the day. That's good. Now for the total power for each device, it will be the number of devices times the power of each single one. So we select this cell, type equal, and then select the power of each one, and it will be times, and select the quantity and press enter. And for the rest of the devices, what we only need to do is to drag from up here to down to the final device. So this is the total power for each device, also the energy for each single device as the total power times the time. So we select this cell here and type equal, and select the total power, then times, and select the number of hours that each device will work for, and press enter. So this is the total energy that the ceiling fan will consume per day, so it's 2520 watt-hour. And now for the rest of the cells, we will do the same thing. We will go to the bottom of this cell and drag down, so we have applied the same equation on the rest of the devices. Here the lamp has a total energy of 2000 watt-hour, and the hand mixer has a total energy of 50 watt-hour. Its energy is smaller than its power. This is actually because it will work only for 0.2 hours in the day. So when we access its equation, it's exactly E9, which is the total power, times V9, which is the hour that it will work for. But also we need to get the total power that the total devices will work for, as we have got the power for each single device, but we need to get the total power or the accumulated power for all the devices. So we need to sum the power of those total devices. And for this we can type here power of all loads, and let's increase its width. And here, as we will assign the total power, so we can select all of those cells and then merge and center. Then we can make its fill color to be red, for example, and also we can increase its font to be 36. So as we need the total power, or as we need to sum the total power, so we will use a function inside the Excel which is called sum. So we type equal sum and parentheses, and we will select from this cell here, and easily we can drag down from the first cell to the last cell, and another parentheses. That's great. We have calculated here the total power of the total loads to be 4130 watts. Now the energy can be done by the same thing, by selecting this cell or those two cells and copy them. And let's go here and go to this cell and press Ctrl V, and let's increase its width. And instead of the power of all loads, we will type the total energy. Now for the total energy, it's done automatically as it has summed the next column. Here this is the column from the first device energy to the last device energy. So we have a total energy for those loads of 10,990 watt-hour, and we have a total power of about 4,000 watts. Now we can delete those cells as we don't need them. Now the second step is to get the panel's peaks and hours, and because we designed this Excel sheet previously that calculates the peaks and hours, we will paste it here for a short time. So this is the previous Excel design for the peaks and hour that we have calculated, and we can copy it. Here, select those cells and copy them, Control C, and let's go back to the first Excel sheet. Then we select this cell and press Control and V. Now we press on Control and select this option, which is to keep the source column width. That's great. Here, if you forgot anything of this design for the elevation angle, the declination, the tilted angle, you can easily jump back to this section and revise this design for this Excel sheet. So this design was made for New York, which has a latitude for 40 and a longitude for -74. But suppose now we are working, for example, on Brasilia, so we need to get its latitude and its longitude firstly. And for this, we will open the latlong.net website, which we had used before. So this is our website, latlong again, and we can type here Brasilia. So those are the latitude and the longitude for Brasilia. Here its latitude is -15.8 and its longitude is -47.9. Now let's go back to our Excel sheet, and here we can change this 40 to P-15 and press enter. And for the longitude, it's -47 instead of -74. Now we need to get the global horizontal irradiation for each month for Brasilia. As we said before, each location in the world has a different value for the S sub H, and for this we will open the NASA database text file and then press the Command Control F and select the -16, so it's nearer to -16, and -48, and press enter. So this is -16 and -48, and those are the corresponding global horizontal irradiation for each month. Here we can select from January to December and Control C to copy them and go back to the Excel sheet. And here we can paste them, so we can select those values and press Control V. Now we will press OK. So we will press on Control, use text import weather, and next, and finally finish and press OK. So the values has been changed to the new values of the S sub H for Brasilia instead of New York, and also we have a change of the latitude and the longitude, and also all the final outputs has been changed because we had to change the inputs here. So the peaks an hour has been changed to P4.75 and its maximum value and its minimum value. The beta has changed also to P15, and the beta calculation has been changed, the elevation angle and the declination. So by changing the input, all the output will be changed automatically. So by this way we have got the total power for the loads, the total energy, and also we have got the peaks an hour for the location which we are working on, which is Brasilia. And on the next tutorials we will continue the rest of this design steps. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial we started designing the Excel program for calculating the required off-grid solar system parameters, and we calculated the required power and energy for that system, and also we got the peaks and hours. And in this tutorial we will continue to calculate the required parameters for the panels and the batteries. So let's start with the panels. Now let's copy the format of this cell and paste it for those two cells. That's good. Now let's type here parameters and enter. Let's increase its width, and also here 12p for the panels. We can change the fill color for this cell. Here let's make its fill color to be this purple one. That's good. Now to enter the panels parameter like its power, for example, we need to get this data from the panels datasheet that we will work on. So let's access the panel datasheet. Here this is the datasheet for the panels. As you see, it's 250 watt, and it appears that from the panel figure, as you see, that it's of the monotype. So it's of the monocrystalline type because of the cut of the edges that it has. Now let's go down. So we have an open circuit voltage of 37.4 volts, and also we have a short circuit current of 8.63 ampere. And now let's go down a little bit. So we will find that we have a nominal operating cell temperature of 45 degrees Celsius with positive and negative 2 degree as a tolerance. So the NOCT now is 45 degrees Celsius. And also for the temperature coefficient of the power, here it's about 0.45%. So that's about the TCP and that's about the NOCT, as we will need all of those parameters in our design. And those are the curves of the power and current and voltage. So this is the relation between the current and the voltage here. And we will find that when we have a solar irradiation of 800 watt per meter square, we are working on this yellow curve here. So this yellow curve is the curve that we will use. Also, we will find that those are the dimensions of the solar panel. Here its length is 1.6 meter and its width is about 1 meter. As we will need those dimensions and the area design as we learned it before. That's good. This is about the solar panel data sheet, and now let's go back to the Excel file to enter those data. Here, before entering the data, we can copy the format of this cell, for example, and make those cells to be with the same format. Now let's enter each single panel power. Its power will be 250 watt as we got from the datasheet. Then the ambient temperature, which is the temperature of the place. So it depends on the worst temperature that this location can reach, as we are making the design at the worst case. So for Brasilia, it will be 33 degrees Celsius, for example. So we will type here T ambient. Now it will be 33 and press enter. Also for the solar irradiation, its standard value, as we mentioned, is 800 watt per meter square. So we will type here solar irradiation. Then we enter it to P800 and press enter. And for the NOCT, which is the nominal operating cell temperature, is 45 as we detected from the datasheet. So we type NOCT and press enter. And here it's 45 and press enter. And for the TCP, or the temperature coefficient of the power, it's 0.45. So we will type TCP. Now for the cell temperature, it's easy. The ambient temperature plus the solar irradiation times the NOCT minus 20 over 800. So that's the equation that we have illustrated before, if you remember. Now we can type T cell. And now we will enter it, and as it's an equation, we will type equal, then the ambient temperature cell, we will select it, and plus the solar irradiation, and we will open a parentheses, and it will be times the NOCT minus 20, and close the parentheses, and it will be over 800. And press enter. So the cell temperature now is 58 degrees Celsius. And now for the panel losses, it's easily equal the cell temperature minus the nominal operating cell temperature times the temperature coefficient of the power. So we will type here losses equal and open a parentheses and choose the cell temperature minus the NOCT and then close the parentheses and times. So it will be times the TCP. Here we select the TCP and press enter. So we have a final value for the losses of the panels of 5.85%. So that's about the panel's design. Now for the Patrice design, we can copy the staple here. So select the staple and copy it and go to this cell and press Ctrl V. So we press on Control, then we choose this option here, which is to keep the source column width. And also let's go right a little bit and change the panels to be the Patrice. So to get the Patrice design, we need to access the Patrice datasheet also to get the required data. Here this is the datasheet of the battery that we will use. Its terminal voltage is 12 volts. So this is the first piece of information that we need. Its rated voltage, and as you see, it will give us a total discharging capacity of 200 ampere hour. This is in case of if we discharge it in 20 hours. But you can see that the maximum capacity of this battery is 220 ampere hour. This is in case of we discharge it in 100 hours. And if we discharge it in 10 hours, it will give us a rated capacity, or it will give us a total ampere hour value of 180 ampere hour. So we will suppose that we are discharging it in 20 hours, and for this we will use this value, which is 200 ampere hour as its total capacity. And for this, its efficiency will be the current discharging value over the maximum discharging value. So it will be 200 over 220, which will be approximately about 0.9 or the 90%. So its efficiency now is 90% as we will choose this value of the discharging. That's good. Those are the three values that we will enter in the Excel sheet from this data sheet here. So we have got the battery voltage, which is 12 volts, and we have got the rated capacity, which is 200 ampere hour, and also its efficiency to be 90%. Now let's go back to the Excel sheet. Here we will enter the battery voltage, so change this power to PV battery, and we will change this one to P12. Also, we will enter the single battery ampere hour, so we will type here ampere hour and enter, and here it will be 200. And for the autonomy day factor, as we said before, it ranges from 1.5 till 2, so we can choose it to be, for example, 1.7. Here we can delete this one and type autonomy day, then we choose it to be 1.7 and enter. And now for the battery efficiency, so we will type efficiency, and we will choose it to be, as we said, 90% or 0.9. Also, we need to select the PVSYST voltage, which will be the final panel terminal voltage. So we will select here this one and make it to be the VPVSYST. As we have got just now the open circuit voltage of the panels to be about 38 or 37 volts. So we will choose it now and assign it to be 38 volts and press enter. Also, for the depth of the discharge, we can select it to be 60%. So when choosing it with 60%, it's a good value. It's higher than 0.5, but it's a good value. So we can save the battery's life. Here, let's select this one and type DOD and enter. Let's select those ones and delete them, and it will be 0.6. And after entering those input parameters, we can detect now the total ampere hour required for the batteries, which is equal the total load's energy times the autonomy day over the DOD times the battery efficiency times the PVSYST voltage. So we can select this one and type total ampere hour, and then select this one and delete those. Now we need to access the total load's energy, so we can go back here and select this one. So this is the total energy that we need for the loads, and then we type times, then the autonomy day, so this is the autonomy day value, and then over and open a parentheses, and then select the efficiency, and it will be times the DOD, so this is the DOD, and we finally specify the PVSYST voltage and close the parentheses and press enter. So the total ampere hour we need for the batteries to store the required energy to feed those AC loads is 810 ampere hour. Also, we need some other specifications for the batteries design, like the number of parallel branches and the number of batteries in each branch. And for the number of parallel branches, we type here N and parallel branches, and as we learned it before, the number of parallel branches equals to the total ampere hour over each branch ampere hour, but each branch ampere hour is exactly each single panel ampere hour, as the panels are in series. So we easily type equal and select the total ampere hour, and then over each branch or each battery ampere hour and press enter. But the number of parallel branches now is a float value, which is 4.5, but this is exactly can exist. We need it to be an integer number, and for this we will choose a function inside the Excel, which is called round up, that can approximate the number to the nearest highest integer. So we can type here round up and then a parentheses. But this function round up takes two parameters. The first one is the number that we need to approximate it, and the second one is the number of digits after the decimal point. So we will type comma here, and then we need no number after the decimal point, so we need to make it an integer number, and for this we type 0. And then close the parentheses and press enter. So that's good. We have 5 branches instead of 4.5, as there is no 4.5 branches, but we approximate its value. Now after getting the number of parallel branches, we need to know what are the number of batteries in each branch. And for this we type here number of batteries for each branch. And as we learned before, the number of batteries for each branch equals the bus voltage over each single battery voltage. So we can type equal and select the bus voltage and then type over each single battery voltage and press enter. So the number of batteries in each branch is 3.1. So we can round this value also, but we need now to round it to the lowest integer, not the nearest integer, as it's 3.1. And for this we use the inverse of the previous function. As previously we used the round up, now we will use the round down. So we will type round down, and then we choose the number of digits after the decimal point to be 0, and close the parentheses and enter. So it's 3. That's good. And finally we need the total number of batteries that we need for this design. So the total number of batteries very easily equals to the number of parallel branches times the number of batteries in each branch. So we will type here number of batteries, then it will be the number of parallel branches times the number of batteries per each branch, and press enter. So this is about the batteries and the panel design, and on the next tutorial we will continue the rest of the design to see how to specify the required specifications for the inverter, for the charger, and so on. So at this point we have finished. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In the previous couple of tutorials we learned how to get some parameters related to the off-grid solar system design, like the load energy and power and the peaks and hours, and also we learned how to get some parameters related to the panels and the batteries. And in this tutorial we will continue this design to finish it. So the next step which we have is to get the system losses. As we learned, the system losses are represented by the total losses of the panels, the inverter, the charger, the cables, and the batteries. But for the batteries we have calculated its losses previously by getting its efficiency. So its efficiency from the previous tutorial is 0.9, and now we will continue getting the rest of their losses. So let's copy this table here. For example, let's select it and Control C, and let's go to the cell and go right, and then paste it, Control V, and keep source column width. That's good. Now we will change this parameter to be the components, as we will get it for each component, and then this panel will be the losses. So the first component we have is the panels. We type here panels, and for the panels it will be what we have got on the previous tutorial. So we have got the panel losses by this value here, so we can select this cell and type equal and specify this cell. And for the charger, its losses will be about 2%, so we can here type charger and make the losses to be about 2%. And for the inverter, its losses will be about 4%. Here we type inverter and press enter, then choose it to be 4% for example. And finally for the cables and dust, the total losses for them is about 3%. So we type here cables plus dust and we make it to be 3%. And finally, to get the total losses of the system, here we can delete those two cells. And then we can select the cell and change its cell color to be red, and also increase its font size to be 26 for example, and make it to be white. And here we can type total losses. Now for the total losses we will type here sum, so we will sum all the losses values and start at from this cell, so its range will start from this cell until this last cell, and close the parentheses and press enter. So this is the total value of the losses that we have for our system, which is 15.3%. Now let's give it the same format of this cell. That's great. But you may notice of the previous tutorial that we haven't got the total number of panels that we need for our system till now. So this is because the total number of panels depends on the total losses that we have in the system. And here to get the total number of panels, we can select this cell and type number of panels So if you remember, the number of panels equal the total load energy over the peaks an hour times the single panel power times the efficiency. So we can type here equal. So let's get the total load energy. Here let's go back, and this is the energy selected. And now we type each single panel power. So we select each single panel power, then times, then the system efficiency. So the system efficiency is 1 minus, and here let's go to get the total losses. So it's 1 minus the total losses over 100, and then close the parentheses, and then it will be times also the peaks and hours. So let's select the peaks and hours. And that's it. Here it's the total energy over the power of single panels times the efficiency of the system times the peaks an hour. Now close this parentheses and press enter. So the number of panels that we have now is 10.9 panels, which is approximately 11 panels. So we need to make the number of panels to be an integer number, and for this we will use the same function that we used on the previous tutorial, which is the round up. So we type here round up and then a parentheses, and then we select the number of digits after the decimal point to be 0 as we did on the previous tutorial, and then close the parentheses, and here it's 11. We need now 11 panels to produce the required electricity to feed our loads. Now we need to detect the inverter required data and specifications, and for this we can copy this table here, Ctrl C, and we can paste it there. So we paste it here, Ctrl V, and now we will change this panel cell to P inverter. Now we need to get the inverter required data and specifications. So the first thing we need to enter is the safety factor to increase the inverter power for any extension and the future and the power. So we can here change this power to be the safety factor and press enter, and we can make it to P 1.3. Then we need to set the power factor. So the power factor will be 0.9 for our case. Here we type power factor, and let's make it 0.9 and press enter. And finally, the rated power will be the load's power times the safety factor over the power factor. So we will type here the rated power, and let's change this one so it's equal the safety factor times the load power. So let's go back to get the load's power. Here those are the power of the loads, select them and go back, and we can make it over the power factor. So select the power factor cell and press enter. So the required power for the inverter, or its rated power, is 5,900 watt, which is approximately 6,000 watts. Now let's delete those cells. So those are some extensions that we don't need. Delete them. Also, we need to specify the minimum charging current for the charger. As for the charger, the very important thing for us is the charging current, which is equal to the total number of panels times each panel power over the pulse voltage. And for this we can copy those cells here. Let's copy them, and we can go there right here and paste them, Ctrl V. That's great. Here we can change this one to be the charger, and for the charger we need its minimum charging current, so it's I many. Now for its value, it will equal the number of panels. So let's go to the number of panels that we have just got. Here this is the number of panels times each single panel power. So it will be times, and let's go to get each single panel power. Here it's 250 watts, and it will be over the pulse voltage. So we will get the pulse voltage from the batteries here. This is the pulse voltage of 38 volts, and now press enter. That's great. We have a charging current for the charger of 72.3 ampere. Now the final thing we have in this design is to get the panel's required area that we will spread the panels on it. And for this we can copy this table, for example, and we can go there and go to the cell and Ctrl V. Now we can select those two cells and merge them, and then change this filling color to be this one, for example, and we can change this component to be dimensions. Then we need to enter the panel's length, so we type here length, and we type here width, So for its length, we have got it from the previous tutorial to P equal 1.6 meter, and for its width it was about 1 meter. And then the spacing equation equals to sine 180 minus alpha plus beta over sine alpha. So let's detect it here. Let's delete this inverter and type spacing and enter. Then we can type here, but let's increase our width. So let's go right and then type equal sine in a parentheses 180 and then another parentheses and alpha plus beta. So we need to detect alpha and beta, and for this we will go left here to detect the elevation angle. So we will need to detect the elevation angle at the worst case, which is 21 of December. So this is the elevation angle. Let's detect it at 21 December. So at 21 December we will have the worst case, which is the highest shadow. So when having the highest shadow we will have the highest area. So we increase our spacing to the maximum size at this condition. So we select the elevation at this angle and then go back and type plus, and then we need beta or the tilted angle. So the tilted angle is a fixed value through the year, so we will select it with this value, for example, and go back. And then we close the parentheses. Here we forget a minus sign, so we type minus, and then another parentheses, and go there, and another parentheses. And then we will multiply by 3.14 over 180 to convert from the radian system to the degree system. So times 3.14 over 180, and then close the parentheses and also close the sign parentheses, and then it will be times the length. So the length here is this cell. Let's select it. And then it will be over sine alpha. So sine and then a parentheses, and let's go back to select the elevation angle again. So this is the elevation angle, and let's go there and also copy this 3.14 over 180, Control C, and here Control V, and close the parentheses, and then press enter. So that's good. This is the spacing value that we need to be between each two adjacent panels. So the spacing now is 1.6 meter. And then after getting the spacing, we need to get each panel area. So we will change this one to P, panel area. So the panel area will equal the spacing between each two panels times the panel width. So we will type equal, then the spacing, and then times, and the panel width, and press enter. So by this way we will have the same value for the area, but here this is in meters square, so the area that each single panel will consume is 1.6 meters square. And finally we need the total area, so we type here total and then enter. So the total area will equal each single panel area times the number of panels. So we type times and go back to select the number of panels. So we have 11 panels, select them and go there and press enter. So the total area that those panel system will consume is 17.6 meters square, and for this we can provide this area for installing our panels. So by this way we made a complete solar system design at which we have calculated the power for the loads and then the peaks and hours and then the required parameters for the panels. For the batteries we have determined the component losses and also the inverter parameters and the charger current, and finally the dimensions for our system. So at this point we have finished holistically right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In the previous tutorial we have completed the Excel file that we will use for calculating the parameters required for the off-grid solar system. And in this tutorial we will collect the required components for the system, and we will see the coordination between them to have a full picture about how the solar system components can interact with each other. So the first thing we need to do is to select the pulse voltage for the system. Here we have selected the pulse voltage previously to be 38 volts. which was the open circuit voltage for the panels, but we need to select another common value that we will choose the charger and the inverter and the batteries according to it. So let's go right here, and now we can change this pulse voltage to make it to 48 volts and press enter. So we have changed the pulse voltage from 38 to a one common value, which is 48. And you can notice that the total ampere hour has been changed. So if we go back, we will find that it's 110. And if we go up, we will find that it's 720. So this is the change in the value between 110 and 720. And this is because when the pulse voltage increases, the current will decrease. And the current will decrease because we have a constant power, which is the load's power. So when the current increase, we will find that the total ampere hour will increase. And also we can find that the charger current has been decreased. So the charger current was, as you see, 72 ampere. This is in case of we have a pulse voltage of 38 volts. But in case when we press Ctrl Y, so we will have 57 ampere only for the charging current. So those are the differences between the two systems. Now we need to increase the inverter losses to be a more worse value, as we need to make our design in the bad case so it can cope with the hard conditions. And for this, let's increase this 4% to be 10%, for example, and press enter. Now let's go back to see the number of panels that has changed. Here, as you see, the number of panels has been changed from 11 to 12. So Control Z, it's 11 here when the inverter losses is 4, but when the inverter losses is 10%, you will find that the number of panels is 12. And this is because the total losses has been increased from 15 to 21. So the number of panels itself in its equation, it depends on the total losses. So when the total losses here, the cell which has an address of AE7, so when it increases, the number of panels will increase. Also, we can decrease the power factor of the loads that the inverter will feed. So we can decrease the load's power factor to be on its worst case, which is 0.8, and press enter. And also by increasing the power factor, we will see that the rated power has been increased to 6,700 instead of 5,900. So the rated power has been increased, as the rated power equals to the safety factor times the power of the loads over the power factor. So we press enter. So we are changing those values to make our system more reliable and more practical, one that has more practical values to complete our design or to see the full design. Now we can summarize the rating values that we have got from the design. That is, we need an inverter that's rated 7 kilowatts and it has an input voltage of 48 volts, as this is the pulse voltage that we have entered. So we can buy the inverter from the market with those values. And for this, we have detected an inverter that has those rated values. So this is the inverter that we can use. Here it's data sheet and this is its manufacturing company. We can go down to see its rated values. So the manufacturing company is providing some standard ratings of the power. Here it's 1000 volt ampere and 7000 and 4000. So you can call it with volt ampere or the watt. This is because the inverter itself has no power factor, but the power factor is determined from the AC loads that the inverter will feed. So the value that we will choose is this 7000 volt ampere, and you see its input voltage is 48 volts or 48 DC voltage, as this is the voltage which we need. So this is a suitable value for us to work on. It works on 50 or 60 hertz, so any system of them, and its output voltage is 230 volt AC or 220 for the 60 hertz system. Now the second component we need is the batteries, and as we calculated from the Excel sheet, we need 16 batteries, and each of them is rated with 12 volts and 200 ampere hour. And here this is the data sheet for the battery that we will use, and we have illustrated it in the previous tutorial. So those are the parameters of it and we don't need to explain it again. Now for the charger, we need a charger of 60.2 ampere, but the nearest standard value for it is 70 ampere. So we will use the 70 ampere charger that has an input voltage which is the pulse voltage of 48 volts. And here this is the charger that we will use. This is its data sheet. Let's go down to see its parameters. Here it says that it can work on a battery voltage of 12 volts or 24 volts or 48 volts. So it has the auto select option. Here it can select the volts that it will work on to supply the batteries. Also, we have some versions from this charger. Here, this 45 ampere, this 60 amperes, this 70 amperes, this 85, and this 100. So what we will select as this 70 ampere, and we will not select this 60, although the 60 is very nearer to the value which we have, which is 62, but the 62 ampere is the minimum value that we calculated. So we can't use a value that is lower than it. And for this, we will use the 70 ampere charger. And you can see its efficiency is 98%, and also it has a variety ranges of the input voltage. So its range starts from 13 volts to 57 volts. So it's suitable for our design, as the battery's input is the panels, which has a maximum voltage of 38 volts, which is the open circuit voltage. Also, this charger has an output voltage for some standard ranges, so we will use the 48 volts as the pulse voltage. Now the final thing we have is the panels itself, as we need 12 panels that is rated of 250 watt. So we have the open circuit voltage of 38 volts, and it has an open circuit voltage, as we mentioned, of 38 volts. And here this is the data sheet for the panels that we have illustrated before. That's great. Now we can summarize the rating values that we have got from the design. To pay that, we need an inverter that's rated of 7 kilowatts, and it has an input voltage of 48 volts, which is the pulse voltage that we have entered. So we can buy an inverter from the market with those values. Now let's summarize the full design. For the full diagram, here we have 12 panels that are connected in parallel, which have a final value of voltage of the maximum value of 38 volts for each panel, and then we have the power flow from them to the charger controller. So the input voltage of the charger is a variable one according to the solar panel irradiation case. Then the charger will supply the batteries with the charging power. Here we have 4 batteries in each branch and 4 parallel branches. So the terminal voltage is 4 batteries times 12 volts for each battery. So it's 48 volts, which is the same pulse voltage. Also, the batteries will feed the inverter that has the same input voltage of 48 volts. So for this reason, we have selected the inverter with an input voltage of 48 DC volts. And finally, the inverter will feed the AC load with a standard input voltage of 220 volts for the single phase. Now you may wonder, although the load's power is 4100 watts, but we got the inverter with a power of 7000 watts. So this is because in many cases we don't know the actual power of the devices, and we enter it with an approximate value. So we can suppose that this power of the devices, which is 4100, is the apparent power in volt ampere, not the active power in watts. Therefore, we suppose that the power factor to be 0.8, and for this reason we will get the power of the devices of 5100 watts. Then we multiply it with the safety factor, so the safety factor ranges from 1.2 to 1.3, and here we maximize it to be 1.3, and finally we will get an output power of 6600 watts. So the nearest standard range for the inverter to the 6600 is the 7000 watts. Now let's go back to the Excel sheet. Here what I want to say is that if those values of each device power are the actual and accurate values, so you know them exactly, at this condition you don't need to divide the power over the power factor. So let's go back to the power equation of the inverter. Here, if you know exactly the power of the devices, you don't need to divide over the power factor, which is 0.8. So we can cancel this power factor, which is 0.8, and press enter, and you can see that the rated power has been decreased from 6600 to 5300 watts only. This is in case of we know the actual power of the devices. But if we don't know the actual power, we cannot cancel the power factor, so we need to divide over the power factor at this condition. So anyway, when we get a larger inverter size, this will help in increasing the loads in the future, so you can extend the number of loads that are connected, and you don't need to buy another inverter in case of you have a larger inverter size. So that's about this tutorial. Hope that's clear right now. Thank you for watching, and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial we discussed the full diagram of the Excel design and we learned how to select the required components according to its parameters of the rated values. And now we will discuss some other cases of the connection and the different solar system elements. So fasten your belt and let's get started. If you remember, in the previous tutorial we selected an inverter with a rating of 7 kilowatt to feed our loads. But you know, in some practical cases we cannot find an inverter with the required rating. Or for some reasons you may use an inverter with a different rating than the calculated value. Suppose we put a package of some inverters that we will use in a project and there are two remaining inverters that you don't use in this project. And for a second project, you need to use those two inverters not to lose their money, but actually the load's rating is different than those inverters' rating. So at this condition, you have to use those two inverters at the same time in the second project. Suppose now each of those two inverters is rated 3.5 kilowatt and their operating voltage is 48 volts. So at this condition we will not use one inverter that's rated of 7 kilowatt, but we will use a couple of inverters, each of them rated 3.5 kilowatt. But the question now is that how to connect those two inverters in the system, as all what we did before in the connection and wiring was for only one inverter. So we say now that the system will be divided into a number of subsystems and this number of subsystems will equal to the number of the inverters we have. So if we have two inverters, the system will be divided into two systems. And if we have three inverters, we will have three subsystems and so on. So at our condition now, we have divided our system into two systems half by half. And this means that instead of using 16 batteries connected to each other, now the half of the batteries will be connected to each other into a subsystem and the other half of the batteries will be connected to each other into the second subsystem. And also instead of getting one charger that is rated of 70 amperes, we will use two chargers, each of them rated of 45 ampere, as the 45 ampere is the nearest value to the half value, which is 35. So the nearest standard value that we can buy from the market is 45 ampere. Also for the panels, we will divide it into two groups, 6 panels into one system and 6 other panels into the other system. And this will be the full diagram of the system. Here it's separated into two groups that has equal powers, and this is because each inverter is rated exactly as the other. So each of them is 3.5 kilowatt. And for this, each system of them will feed the half of the loads. But suppose that the two inverters will have a different value of the rated power. For example, one inverter have a value of power of 4.5 kilowatts and the second inverter has a rated value of 2.5 kilowatts. So at this condition, the ratio between the two inverter will be about 1 to 3rd. So 4.5 over 2.5 will be about 1 to 3rd. So the third of those components will be connected to the 1/3 inverter, which is 2.5 kilowatt, and the 2/3 of the loads will be connected to the inverter that is rated 2/3, which is 4.5 kilowatts. So what we want to say is that according to the number of inverters, we will split the system into a number of separated subsystems. And also according to the power of each inverter, we will split the weight of the components and then the loads with a percentage that is equal to the inverter's power percentage. Now suppose that we have another case at which we have the full capacity of the inverter. So it's available with its full range of 7 kilowatt. So we will use only one inverter that's rated 7 kilowatts, and the battery sizing is available also with the required value, which is 16 batteries, each rated of 200 ampere hour and each as 12 volts. But the problem now is in the charger controllers, as you have a rated value of the charger controller of 45 ampere only, so we don't have a 70 ampere charger controllers. And at this case, we have to use two charger controllers now, and each of them is rated 45 amperes. So at this case, any component comes before the charger must be split into two groups. So the panels will be split into two subgroups, as we have a total of 12 panels. So we will split them into 6 panels and other 6 panels. And this will be the full diagram. As you see, the loads are only one group, as we have only one inverter, and the batteries also are one group that consists of 16 batteries, and the splitting operation will start from the charger. Here we have 2 groups of the charger, and each group of them is connected to 6 panels. So what's separated in that case is the charger controllers and the panels only. So that's about the off-grid solar system connection at some special cases. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will introduce some AutoCAD basic orders that will help us in designing the solar design layout. As we need to express our design well in the AutoCAD layout to show all the details that we made in our solar system design, starting from the panels, ending at the loads that we need to feed. So let's start to learn how to apply those orders. The first order, if we need to make a line, so if we need to draw a line in the AutoCAD, easily we type L and enter, and then start with a left click and then move with the mouse. So when moving with the mouse we can draw the required line. Then when pressing another left click, so we have drawn our line, so this is our line. And if we need to continue drawing another line, we will move also with the mouse and have another left click, so this is another line. And also if we need to draw another line, we move with the mouse and move again and move again. So all of those are some lines. And if we need to end this line process, we press enter. So if we need to repeat this order again, we can press enter, and then it asks us to specify the first point. So here another left click and move to draw the line and another line and so on. So if we need to end again, we press an enter. Here this is about the line order. Now we can delete those, for example. So if we need to delete, we can select those lines and then press on delete. Now the second order we have is called the polyline. So we can apply the polyline order easily by press on P and L. So P and L and then enter. Then it asks us to specify the first point. So left click and then move with the same technique of the line, and then move and then move. So this is the polyline and then move. And if we need to end the order, we press on enter. Now you can ask, what is the difference between the polyline and the line? As here this is a line order and we made it exactly by the same way of the polyline. So let's see the difference between them easily. Here if I select a part of the line, you can see that this part only of the line is selected. This is because I typed it or I have drawn it by the line order. But on the other hand, when I select this one, you can see all the line is selected. So again, when I select this one only is selected, not the total line. And if I select this one, for example, so I'm selecting now the whole of the line. So we can say that the polyline is producing a continuous line. And when you select any part of it, you will select the whole of the part. And here for the line, it draws a discrete line. So the line order draw a discrete line, but the polyline draw a continuous line. Now the next order we have is the ortho mode. So what's the ortho mode? Here when I need to draw a line, I press L and enter, and then I specify the first point. So you can see that the line is moving with your mouse at any direction. So it moves at any degree of the 360. But on the other hand, we have this tab here, which is the ortho mode. So when you press on the ortho mode, and when I press L again to type a line, you only are able to move at the perpendicular direction. So the ortho mode enables you only to draw a perpendicular line, a vertical line or a horizontal line, like this one here, this one, and this one, and it doesn't enable you to draw a line in any direction or any other direction. So when we deactivate the ortho mode, we can type L and enter, and then we are moving at any direction. But at the ortho mode, we are moving only vertically and horizontally. That's good. Now there are some popular shapes that we need to draw, like the circle, the rectangle, the triangle. So to draw a circle easily, we press C and enter, and then it asks you to specify the center of the circle. So when we press a left click and then we are moving, so you can see that this is the circle and this is its radius. When I move with the mouse, its radius decreases or increase. So when I press another left click, here I'm making this circle. And also if you need to draw a rectangle, it's very easily. You type a command RE and C. So by RE and C, you are drawing a rectangle and then press enter. Here it asks you to specify the first corner of the rectangle. I specify this first corner, and when I move, you can see this is your rectangle. Here when I press another left click, I have made the rectangle. That's great. The next note we have in the AutoCAD is the selecting options, as the AutoCAD has two selecting options. The first one, when I press a left click and then I drag from the right to the left. So when I drag from the right to the left, you can see that the selecting color is this green. But on the other hand, when I press a left click, then I drag from the left to the right. So the dragging from the left to the right come up with the blue select. So we need to see the difference between the blue select and the green select. Easily we can say that when I'm making a green select, you can see when I select only a part of the object, the whole part is selected. But when I'm making the blue select, so when I select the part of the object, not all the part is selected, or the part is actually doesn't select. So to select the object with the blue drag, you need to include the whole of the object. As you see here, the rectangle is selected when I selected the whole of it, or when I included all of it and the blue select. While on the other hand, when I select only a part of the object and the green select, it's all selected. So this is the difference between both of them. Now the next order we need is to cancel the order. For example, when I press an L and enter, so I need to type a line now. But what about if I need to cancel this order? So if you need to cancel the order, you easily press on the escape button in your keyboard, and the escape order in your keyboard is the left upper corner button. So the left upper corner is the escape button. When I press on it, I'm cancel any order. Here when I press a rectangle and press enter, then I'm select the rectangle. But now I have changed this idea. I don't need to draw a rectangle, so I press on the escape button. Here I cancel it. So this is for canceling any order you are working on. Also another popular geometric shape is the arc. So if you need to draw an arc, you easily press on A and enter. So when you press on A and enter, it asks you to specify the first point of the arc. So I type this point. Then it asks you to specify the second point. I can select the second point, and it asks you to specify the third point. So you can see I can draw this arc. I can draw it to be like this one, like this one. So when I press on this one here, this is our arc. Here again, when I press A and enter, the first point, then the second point of the arc, and then the third point, and that's it. Now let's delete those garbage. That's great. The next order we have is the mirror order. And the mirror order, if you need to mirror any object, or if you need to copy it but to appear on the other side like the appearance in the mirror. So to do so, you easily press on M and I and then enter. So M and I is the short for the mirror order. Press enter. Here it asks us to select the object that we need to mirror. I select this object and then I press enter. Then it asks us for the first mirror point, as the mirror will be done according to the line that you need to mirror across it. So I can specify this first point, for example, and here according to the second point, the mirror will be done. So when I made a vertical point, let's activate the ortho mode, and you can see if I made it to be a horizontal one, the mirror will be done at this line, and if I made it to be a vertical line, the mirror will be done at this way to be vertically. Here when I press a second click, so it asks us if we need to erase this first object. I can press no or I can press yes, but for this I press no and an enter. So it has been mirrored. Here this rectangle has been mirrored. Now let's do that again, but deactivate the ortho mode. And then to repeat the last order, you can press on enter directly. So I can press on enter directly, or I can type the short of the order. And for that, I'll press on enter. Here it asks us to select the object. I select this rectangle and press enter. It asks us to specify the first point of the mirror. I select this point and this point, and it asks us if we need to erase the source object. So I press on yes now. So I'll press on yes now and press enter. So the object has been mirrored and the source object has been erased. That's good. Now what about if we need to move an object? For example, I need to move this arc, and to move an object we easily can select it and press on M. M is the short of the move order. I press on M and enter. It asks us to specify the paste point. So the paste point is the point that we will pick the object from it. Here I'll pick the object, for example, from this point. You can see that it moves with you. So the object is moved with you, or the arc, and I can paste it at any location I need. Here I paste it there, and that's it. Now the first order we have is called the hatch. But what about the hatch? The hatch is an order that enables you to fill any object or to fill any closed object with any style of drawing you need. So if I need to fill an object with some dashed lines, we can do that. If I need to fill an object with a solid color, we can do that, and so on. And to activate the hatch order, we press on H and enter. Then it asks us to pick an internal point, so the hatch is done for only the closed objects. And for this it asks us to pick an internal point from the object, and for this I need to hatch the internal side of this rectangle. I press at any point inside it. So I'll press at any point inside this rectangle, but at first those are some options related to the hatch order. Here when I press on it, those are some styles that you can select one of them. Here I can select this one, and you can see this is a style, and also we have, for example, this is style. So those are some dashed lines, and you can see also we can select the solid mode. So when you select the solid mode, all the solid will be filled with the color. And also we have, for example, this mode, and we can select another one like this one here, and so on. So for us, we can select this one here and press on enter. So this is about the hatch mode. And to close the hatch, we will press on close hatch creation, or we will press on escape. So we will press on escape now. That's great. Here we have hatched this rectangle. Alright, now the next order we have is the trim order. So for example, if we need to trim a line, how can we do that? And to do that easily, we can type here line, L and enter, specify the first point, that's 1, and press enter, then press enter again to activate the order. So to end the order or to activate it again, we press on enter. Here enter, and specify the first point and the first point, and enter. So suppose that this part of the line here on the down is an extension one, or we don't need it. So if we don't to trim this part of the line, easily we type T and R, then press enter. Here it asks us the object we need to trim. So we select the first object we need to trim. Then it asks us to select the second object, as the trim order is done by selecting two objects, the first one and the second one. And for this we will select the second object, and then we press on enter. Then it asks us for the part we need to trim. I'll select this part. So that's easily, it has trimmed this part. Now I press enter again to end the order, and also I can press enter again to activate the trim order again. And here it asks us to select the object. So not to select each object individually, by selecting here, by a left click, we can drag to select the whole objects that we need to trim a part of it. So I'll select those objects, and then I press enter. So it asks us for the part we need to trim, and easily I can trim this small part here. That's great, we have trimmed it. And press enter to cancel the line. That's great. Also, we have an order which is to copy. So a very popular order is to copy an object that you have in your AutoCAD drawing. And to copy an object, you easily need to select it and then press C, O, and enter. So it asks us to specify the point that we need to pick the object from it. So we select this object as we will pick this object from this point, and then it's moving with us now. When I press a left click, so I have paste it here, and it's still moving with us now. So we can paste it many times we need. I paste it here and here and here, and another left click and another left click, and when I press escape or enter, I'll end the order. So this is to copy any object easily. And finally, the final order we have for this tutorial is to exclude an object. So what is about the exclude? Here, let's delete this one. Here we select it and delete it. So you can see when we select this rectangle, it's selected as a whole part. So when I select it with the green select, you can see it's selected as one block or as a whole block, which means that those 4 lines that represent the rectangle are plugged to each other, or they are consisting only one block. But when I need to exclude this rectangle, so I need to make this line a separate line that is separate from this one and separate from this one. And for this, we will press on X and enter. So the exclude mode is X and enter, and it asks us to select the object that we need to exclude. I can select this rectangle, and it asks us to select any other object if we need. So I don't need any other object, and for this I'll press on enter, and that's it. Here to check that we have excluded this rectangle when I select it. So that's great. I select only this line, and when I select this line, so I selected only this line, not the whole rectangle as what was done previously. So I can move this line now when I press M and enter, and I move it from this part, so it has been separated exactly from the rectangle. But for this rectangle, for example, it's one block, so when I select it as one object, and if I need to move it, I'll move the whole rectangle. This is because it's one block, and by this way we can exclude any object that we need. So that was about some important orders related to the AutoCAD design that will help us very greatly in the next tutorial and the solar system layout. Hope that's it clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In the previous tutorial we have discussed some very essential and important AutoCAD orders, and on this tutorial we will continue those orders. So the first order now is that what about if we need to measure the area of any object? So for measuring the area, let's firstly draw a rectangle. Here rectangle, and press enter and specify the first point and the next point, and that's it. Here for measuring the area, we press the command area. So the command area will enable us to measure the area, and press enter. Then it asks us to specify the first corner. We specify the first corner, and it asks us to specify the second point. So I can specify the second point, and it asks us to specify a third point. So at this point I can end or I can continue. So I can continue to any infinite number of points that I need for the area that I need to measure. As for example, I need to measure the half of this rectangle. So I press on enter to end the order. And here it appears that the area is 3.7 meters square. Also, when I try to measure the full area of this rectangle, here I press enter again as it will activate the last order. And I specify the first point, the second point, the third point, and here the fourth point, and I press enter now. So the full area of the rectangle is 7.5 meters square, which is actually the double of the previous area. That's good. Here I press on escape. And now the next order is to measure the length of any object. So I need to measure the length now. And for this we press on MEA. and then S. So when we press on MEA and S, it appears here the measure, and it asks us if we need to measure a distance or a radius or an angle or an area. So this is a global order, and here I press on distance. Here it asks us to specify the first point and then the second point. So as you see, when I'm moving, the length is increasing with us. Here the number is increasing, and I can press on this point, and that's it. It tells us that the distance is 4.7 meters. Also, we can press on enter again, and it asks us to specify the first point. Here the first point, and it asks us to specify the second point. So this is the second point, and that's it. Here it tells us that the distance is 4.3 meters. That's great. Also, we can do the same thing but with another way by pressing easily on linear here, and it asks us to specify the first point, then the second point, and that's it. Here it tells us that the length is 4.3 meters, and when I press a left click, I can fix the length here. So this linear option, if we need to express the length on the drawing, or if we need to express it as a part of the drawing. Here, this is a part of the drawing, and we can select it and delete it. So that's it. Those are two ways for measuring the distance. Now what about if we need to change the style or the color or the width of the lines that you are using? Here this is done easily by selecting this tab and choose any color you need. Here I can change the yellow, and when I press on L and enter, so I specify the second point. That's great. The color has changed to P yellow, so that's for the line color. Also, if I need to change the line width, I press on this part here, and I can select any width I need. Here let's select this 0.2 meter. And when I press enter again to type a line, so from this point to this point to this point, and that's it. So this is the width of this line. I can select another one, and I can increase it to P 0.5 millimeter, for example, and press enter and select this one and this one and this line. That's great. Here the line width has been increased greatly. Now let's decrease it back to P, for example, 0.25. Also, to select the style of the line, we can press on this mode here, and it asks us if we need the line to be a continuous, or we need it to be dashed like this one, or we need any other. So we can select this line style, for example, and L and enter and specify the first point and the second point. And that's it. Here this is another style, and you can select the style that you need for your color. Now let's delete those lines here and those ones, and also we can delete this one. That's great. The next order we have now is the array order. So what's about the array order? Here, if you need to make an array of any number of objects, you can easily type AR and then enter, and here it asks you to select the object that you need to make an array of it. I select this rectangle here, and it asks us if we need any other object. I press enter, so I don't need. Here it asks us if we need the array type to be a rectangular one or a path one or a polar one, so I press on rectangle, and that's it. This is an array of rectangles, and here those options are the related options to it. So it asks us for the number of columns that we need for that array. It's 4. I can change it to P3, for example, and you can note now the difference. Here I have decreased the column from 4 to P3, and I can make it, for example, to P10. So it has increased to P10 columns. Here we have 10 columns, and for the rows it's 3 here, so we have 3 rows, this one and this one and this one. I can change them to P, for example, 5, and press enter. So this is about the array mode, and those also are some other options. It asks us for the distance between each two objects or each two rectangles. Here we can make it, for example, to be 6 and press enter. So the offset distance has been increased. And also if we need to increase the width between them, here it's 6, so I can change it to P12 and enter. Here we have increased the offset between them, and that's it. Now we can close the array option. Now the next order we have, if you need to refresh your program. So sometimes your program works heavily and you need to refresh it. And for this our order now is called the regenerate. And to activate the regenerate order, we press R, E, and G. And then select the second one, not the first one. And then press enter. So by selecting the regenerate order, we are refreshing our program and we are decrease the size file, as there may be an increase in the size of the file, and this made your file more heavier and the operation. That's good. Now we need to delete those ones, but you can see when I select them, all of them are selected as one object. And this is because they are supposed to be one group or one object. And as we learned it before, if we need to explode a grouped object, we can press on X and enter. So we have exploded them. Now I can select those only and I can delete them, and that's it. Now what about if I need to do the inverse of the previous operation, which is to group an object? So we have learned how to explode an object, and now we need to learn how to group an object. This is easily done by selecting the object and then press G and enter. And that's it. When I select any one of them, the whole of them are selected as the whole of them are made to be one group. Here I can explode them again, X and enter. So when I select any part of them, it's selected separately. So this line is selected separately and so on. Now the next very important order that we need very much in our design is to block an object. So to block an object, it looks like the group operation, but it has some other facilities or some extensions and the facilities. And for this I select the object and I'll press on P and enter. So it asks us for the block name. Here I can rename it to P rectangle 1, so rect1, and I press enter. So when I press on this object here, it seems that it has converted to a block. So the block has some special facilities. That is, for example, I can't edit it. So I can't edit its color, for example, its width, its length, its scale. Here when I select it, and I need to change its color to pea green, for example, so it hasn't been selected. This is because the blocked object is supposed to be a frozen object that is can't edited by the normal operations. And for this I'll select it again, and to edit it I'll have a double click on it. So it asks us if we need to access the rectangle 1. I'll press on OK. So the program will lead us to another window like this one, and this is a special window for the block at which we can edit anything or any property related to our object. Here I can select it and I can go to the home mode and I can change its color to pea green, for example, and I can close the block editor. It asks us if we need to save the changes. I'll press yes, I need to save the changes. That's it. Here we have changed the block. So if you need to change any property of the block, you need to access it separately, and you can't edit it at the global window of all of the objects in your AutoCAD design. Now a very important order we have also is the scale order. So the scale order enables you to scale any object you need. So you can increase its scale or decrease its scale. And it's done easily by selecting the object and then press SC and enter. It asks you to specify the base point that you need to start the scaling operation from it. I'll press on this point, for example. Then here you see I'm increasing the object or I decreasing it. So by the scale point I can decrease or increase the object scale. Also, if you need to do this operation very sharply, you can enter the scale value in this part. So when I enter the scale value to P5, for example, and press enter, so the object or this rectangle has been increased or it has been maximized to a scale of 5 times its original scale, and that's it. Also, we have another order which is called the fillet. And to know what's the fillet order, we need firstly to draw a line, L and enter. So that's one good. And also we need to draw another line, L and enter. And here, that's it. Now the fillet order enables you to make a fillet for any angle you need. So for this corner, we can make a fillet by press on F and enter. So it asks you to select the object that you need to fillet. I'll select this object, and it asks us for the second object. I'll select this object, and that's it. But you can't see the fillet here as the fillet radius is very small, and for this I'll press on F again and enter. So instead of selecting the object, here it asks us if we need to select object or another thing. So I'll press on the down arrow and I'll choose, here you can choose undo, polyline and radius. So we will choose the radius of the fillet and press enter. Here it asks us to enter the fillet radius. I'll press on 0.2. and press enter. Select the object, this one, that's good. Here when we made the fillet radius to be 0.2, you can see that the fillet has been appeared, as the fillet radius on the previous one was a very small value, so it didn't appear on the previous time. And finally, the final order we have is to rotate an object, and to rotate an object we easily select it, like this one here, and press R and O and then enter. So it asks us to specify the point that we need to make the scaling operation around it. I'll select this point, and then you can rotate the object at any degree that you need. So this is to rotate an object at any degree that you need. I can activate the ortho mode if I need to rotate it to be vertically or horizontally rotated, and that's it. So that was about some very important AutoCAD orders. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will start designing our solar system layout. So we need to express our work of the different components of the solar system and how it's connected to each other. And for this, let's start with the panels to draw it. So for working on the panels, we will create a layer and call it panels. Here press on layer properties, then press on this tab to insert a new layer, and we will call it solar panels. And press enter. Now we will make its color to be yellow, for example. Here this yellow, and press OK. And we will close this layer properties, and now we will select the solar layer to work on it, and we will make our color to be pi layer. So pi layer will make our color that we are working on is the same color for our layer. Here we have this pi layer yellow and this one yellow. And now let's start constructing the panel or the first panel. Here we will draw a rectangle, rect, and press enter. And let's specify it to be with this size, for example. And also we need to express the sols inside the panel. So we will make some vertical lines and some horizontal lines. And to make them equally distributed, we will make a line here, L and enter, and start from this point till this point here, and then press enter. And after that, we will divide this line that we have just made. So divide div and enter. Select the object. Here, let's select this object. And then it asks us for the number of segments. So we need, for example, 3 parallel lines or 3 vertical lines. And for this, we will make 4 points. 4 and enter. That's great. Also, we need some horizontal lines here. And for this, we will make another line, L and enter. From this point to this point, and then enter, and then div and enter, and select this line that we had just made. Now we will make the number of segments to be 5, for example, and press enter. That's great. Now we will make our lines, L and enter, starting from this point till this point. And you can note that we are activating the ortho mode. Press enter again, enter to repeat the order from this point till this point. That's good. And now another one. That's great. Now we will do the same job, enter, and starting from here till that point, and another one starting from that point to that point, and another one from that point to that point, and finally this one. And enter. Now let's delete those points and delete those helping points also. Now we need to rotate this panel with an angle that refers to the tilt angle, so it refers that those angles are tilted to the ground, and for this we will select the whole object and then press RO and enter for the rotate and specify the space point, and we will deactivate the ortho mode. So we need to rotate it freely with any angle, not to be horizontally or vertically rotated. And we will make the rotating angle, for example, to be -15. And press enter. That's good. Here, this is a rotated one. Now let's draw the terminals of our panel. Here, L and enter. Specify the space point, for example, and till this point. And enter. And now let's copy this one, CO, and enter. Copy it from that point to that point, for example. That's good. Now we will make this one to be red, and this one to be in blue. And we need a positive terminal and a negative terminal. And for this we will type T and enter for the text. We will specify this area, and then the text will be a plus sign, and escape, yes, and let's scale it. So we will select it and SC and enter. Here let's scale it to P 0.3 of its original size and enter. That's great. Now we can copy it, CO and enter, and specify the space point and paste it here. And also paste it here, and this one will be a negative sign, minus, and enter, and yes. Also we can select this one and rotate them with the same angle, which is -15, so -15. That's good. Here this plus sign is parallel to our panel, and also this negative sign. Let's delete this one and align this one here. Let's move it, M and enter. Now we need to change the color of this plus sign. So let's open it and make it to P with red. And yes. And also this one to P in blue. And OK. Also we need to express the value of the voltage of this panel. So this will be an important data for the panel. And for this it's open circuit voltage as we learned it before. And for this, the open circuit voltage for the panel that we have worked on is about 38 volts. And for this, we will type a text, T and enter, and specify this area here, and type 37 volt, and escape, and yes. And let's make it to scale to P 0.3 and enter. That's good. Now we can rotate it, RO and enter, with the same angle, -15, to P parallel to our panel. Now let's move it. So we select it here and make it to go there. Good job. Now let's make this panel on a special plug. So we will select it and type P and enter. Let's make it to be the panel or the solar panel, and then press enter. That's great. Now let's move it to be here, and we need to make an array of it. As we have discussed before, our system consists of 12 panels which are connected in parallel, so we will make an array of 12 rows and only one column. And for that we will select our panel and press A, R and enter. and it asks us if we need it to be rectangle or path or polar, so we will make it to be rectangle. Then the number of columns is 1 and the number of rows is 16, but we will make the number of rows to be 4 only, and we will see why that now, and press enter. That's good. Here we have 4 panels and we will close the array. Now if you see, if I select any one of them, it looks like they are on a group, and for this I'll press on X to explode this group. Here each one is separated. Now I'll select this one and delete it, and I'll make some points down here to refer that we have a number of panels. This is because if I draw 12 panels here, their number will be a very large and our drawing will be a pad 1, so it will have a pad appearance. And for this we are making a sample of the panels, and we will make some points down here to refer that we have a number of panels. And for this we will press on T and enter to type a text, and then make the text at this area, then a point and enter, and another point and enter, and another point and enter, and another point, and that's it. Press escape and then yes. Now I'll move those points here. Let's select it. That's good. Here we have our panels, and now we will type a text that expresses their dimension or the number, and it will be 1 times 12. So 1 column and 12 panels in each column, and for this we'll press T and enter and specify this area. Then it will be 1 times 12 and escape, yes. Now we can scale it as C and enter and make it to P 0.7. That's good. Here those are our panels represented in only 1 column. Now we need to make a rectangle that contains our panels. Here we type R, E, and C and enter, and it will be from this point till this point, for example. That's good. And now let's change its color, so select it and change its color to P magenta and enter. And also we need to express that this is the panel system, so we need another text, T and enter, and specify this area. Now it will be panel system. Now we can pull it and we can make it to be italic and press escape and yes. That's good. Here this is our panel system. Now after finishing the first part of our system, which is the panels, we need to draw another part, which is the protection panel system. And for this we will make another layer. So the solar layer we're using any part related to the solar panels, and here we need another layer for the protection panels. And for this we will press on layer properties and then insert a new layer, and we will rename it to P protection board. And then press enter. Now let's make its color to be the blue and OK. And also, as we will work on the protection panels for the new layer, here we will select our new layer, protection board, and we will draw a rectangle and enter. Then specify this area, for example, to make our protection panel at wedge. Then we will type a text, so T and enter, and specify this area. So the text will be named protection distribution port. Now let's justify it and press escape and yes. Also we need to rescale this text. That's good. Here we need to change its color. Yellow is a good one. And also we need to justify it here and the rectangle. That's good. Also let's make a plug for this distribution port. Here we can select it, P and enter, and let's make its name to P, the protection port, and press OK. That's great. We have made it to P at 1 block. Now after finishing the first 2 modules, which is the protection port and the panel system, we need to make another system, which is the wiring. And for the wiring between those components, we will make another layer So properties, and then insert a new layer, and let's rename it to P, the wiring, and then let's make its color to P and red, and OK. Now we will select the new layer, which is the wiring, as we will make the wiring system, and then we will press L and enter, and we will make some lines here for the wiring, but for that we need some parallel and horizontal lines, and for this we will press on the ortho mode, then make a line, and enter, then another line, enter again to activate the last order, and press enter, and also another line, L and enter. Then that's good. Here we need also some other lines for the negative terminal. That's great. Now let's make the vertical line that will collect all of those positive terminals, as all of those will be in parallel. Here press on L and enter again. Then let's start from this point to this point here. And also make another one. That's great. Now we need to delete the extensions in the lines, and for this we will press on trim. So the trim will delete the extensions, TR and enter, and we will select all of those objects at one time, and also those ones, then press and enter. Here it asks us to select the object exactly that we need to trim. So this part is the extension, and this one, and also this one, and this one, and we can select this one, and this one, and also this, and also this one, and finally this one. That's good. Now we can make another line that going out to the protection panel, and for this we will press on L and enter from this point, then to this point, then going down and to the protection panel. That's great. Press enter. Then we need another one, so enter again. Another line which will represent the negative terminal here to this point, and at this point, and finally till this point, and press enter. Now to distinguish between the positive terminal and the negative terminal, we will select those red ones which are connected to the blue terminal, and we will change their color to P blue or cyan. So their color is exactly the cyan one. Here those are the cyan ones. And also to make the appearance of the lines more better, we can make a fillet for each corner here. So F and enter, and select this object and this one, then another one, enter. That's great. Now we are making a fillet to make the design more realistic, as those are representing some cables, and the cables will not have an angle with 90 degrees, but it will be curved like this beauty one here. Now the final thing we need is to pull the protection fuse. As we learned before, this protection panel has some fuses, but those fuses for the main cables that carry the main current, but also between each panel and the other there will be a fuse, as if there is any short circuit condition at those connections, and for this the fuse will be included also in the wiring system. So we will make a rectangle, but let's change its color to P white, then press R, A and C and enter. Then let's make the fuse to P from this point till this point here. That's good. Also we can copy it, C, O and enter, starting from this point till this point, and finally the last fuse at this point here. That's great. So this is our first step for designing the layout, which has to express the panel system and the protection port system. Each of them are handled on a different layer and on a different plug. Here the protection at the plug, and also the panels at the plug, and the wiring is in a layer. You can see it's in the wiring layer, and you can see the panels are on the different layers, so all things are handled and designed well. Hope that's it right now. Thank you for watching, and see you in next tutorials. Hello and welcome everyone. In the previous tutorial, we started making the first step of the layout design of the solar system or the off-grid solar system, at which we designed the solar panels and the protection port. And now we will continue our design with the next step, which is to design the charger controller system. Now for the charger controller, we will create another layer. Here, press on Properties. Now a new layer. And we will name it to P Charger Controller and close the Layer tab. Now we will access the Charger Controller layer. Here the Charger Controller, and for that we will draw a rectangle that represents the Charger Controller. Here rectangle, and let's make it to P with this size, for example. That's good. Now we can make it to P in yellow. And as we learned, the charger has 6 terminals, 2 for the input and 2 for the output, and 2 if we have an external load that we need to feed. And for each terminal, it will be a screw, so we will represent the screw with a circle. Here type C and enter, and specify the starting point to P, this one, and let's make the screw to P like this one here, and then copy the circle CO and enter, and specify this point. And it will be good to insert it here. Then we need another one at this position, and that's good. Now for the 2 screws, C and enter, and specify this point. Let's make them smaller to distinguish between them. Add this one, let's move it, M and enter, then specify this point. At this position, let's copy it, C, O, and enter from this point, and let's activate the ortho mode till this point, for example. That's good. Now we need to make the cross for the screw, so we will make a plus sign. Here L and enter from this point till this point, and enter, then another one, and now we can copy those 2 lines, C, O, and enter, and copy them to put them here. That's great. Now another 1, L and enter, starting from this point, till this one. That's great. Now as we know, each 2 terminals are positive and negative, so we need to make the positive like this red one here, and the negative like this cyan one here. So let's change the color of those 2, and also this one, and also those 3 to P in red, and press enter. That's great. This is for our charger controller. Now we can make another rectangle for it that contains it. So RA and C and enter, and specify this area, for example, for the charger. That's good. Now let's make it to P and purple or magenta, and let's copy this text, CO, and enter, and put it here, but we need to rename it to P Charger Controller instead of Panel System, and escape, then yes. Then we need to connect from the protection distribution port and the charger controller, but don't forget that we are working now on the charger controller layer. So for converting, we will convert to the wiring system. Then we will draw a line from this point here till this point, but let's activate the ortho mode and then enter, and another one, L and enter, from this point to this point. This one will be in cyan, and this one will be in red. Good job. Now as we know, after the charger controller, we have another protection port. So we will copy this protection port, C, O, and enter, and specify the space point, for example, and put it here. Also connect from the charger controller to the protection port. Also the charger controller output is 48 volts. So we know that the voltage that is coming out from the panels is a variable one, and it has an open circuit value of 37 volts. But starting from the charger, after going out of it, we have a fixed voltage of 48 volts for our system, as this is the pulse voltage. And for this, we will type a text that represents the pulse voltage. Here type T and enter, and specify this area, and it will be 48 volts, and press escape, yes. That's good. So our pulse voltage now is 48 volts. And after the charger controller, we have the battery system. So let's construct another layer. Here, press on this layer properties and new layer. And let's rename it to P, the battery system. Then close the layer tab and access the battery system. And let's draw a rectangle here that represents the first battery. This is our first battery. And also we need to draw the two terminals of the battery, the positive and the negative. And for that we will draw two small rectangles. That's good. Now let's copy it, C, O and enter. That's good. Now we will hatch this one. So let's press H and enter. And it asks us to pick an internal point. So let's pick this internal point and let's make its style to be solid. Then its color to be the cyan. Now hatch this one also, H and enter. That's great. Also for this rectangle, it will be good to make it in red. And for this rectangle to be in cyan. Good job. Now we can copy the plus and the negative signs. Good job. Now as we made our design before, we have 16 batteries, 4 rows and 4 columns. So 4 batteries for each series branch. And for this we will make an array of the batteries. Here select it, A, R and enter. And we will make it to P rectangle and close the array. Here we can move them. And now we need to connect between each of them. So we will press L and enter, starting from this point. Then L and enter, starting from this point till this point. Then trim, T, R and enter, select all of them. Then we need to trim this part and trim this part and trim this part. Now we need to copy those for all of the other batteries. Here we can select them. Then C, O and enter, starting from this point till this one. And finally this one. Then we need another group of the series batteries as those only are 3. Now we can copy those. C, O and enter. That's good. Now we need to make the main wiring. So another line L and enter. Starting from this point to this point. Then enter. Then another one. Starting from this point to this point. And another one from this point to this point. And also another one from this point here to this point. And finally another one from this point to this point. And also we will repeat that thing. We can copy all of those, C, O and enter. And now we need to select all of those wires and make them to P on the wiring system or on the wiring layer. Here we select them and go to the wiring layer and put them there. That's great. Also we need a rectangle that contains all the battery system. So rectangle and start from that point to that point. Now we can make it to P at the magenta color. Then we need to express the voltage of each battery. So as each battery is 12 volts, here we can copy this one, Control C and Control V. Now we need to name it also, so we can copy this one, C, O and enter. Also change this one to P for the batteries. And we can change its color to P in yellow. Also, if we press on the charger controller, we will find that this is the wrong thing. It's in the solar panels. So we can change it to P on the charger controller. Now we can change its color again to P yellow. And the final thing we have is to connect from this protection panel to the battery system. And for this we convert to the wiring system. And make a line, L and enter. Starting from this point and the ortho mode. And then make a line. Good job. Now we can change the color of this line here. That's great. Now let's delete this garbage panel and then delete those wires also. So trim, TR and enter. Select this object. That's good. Here we have designed the battery system, the charger controller and the panel system, and on the next tutorial we will continue the rest of these steps. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. On the previous couple of tutorials we have learned in details how to design the components of the off-grid solar system to make the required layout for it. We have made the panel system, the charger controller, the protection devices and the battery system. And now for this tutorial we will continue our design, but not to waste your time, and as you have learned exactly how to make all the elements, how to make a shape like this one, how to make these circles. So we have made the inverter sample and some samples of the distribution port for the loads that we will feed, and now we will connect all of them to finish our drawing. And for this we can select this inverter and make a layer for it. Here, layers, then new layer, and rename it to P inverter, and then press enter and close it. Now let's make the inverter to P on its layer. Here we have the inverter layer. Now the inverter will take two lines, one for the positive terminal and one for the negative terminal. So let's type L and enter and start from this point and activate the ortho mode till this point here, at this point and this one. Now we make all of those wires on the wiring layer. Now color this one by the red and this one by the cyan. Good job. Also we need to connect from the inverter to the final distribution panel. So let's make another line, but let's make it to P in green, then L and enter, starting from this point to this point, then another one, L and enter. That's great. And copy this one, CO and enter, and here go at this point and at this point. Then we can increase the size of this part here. So it's our distribution panel, increase its size to P, for example, 35. That's good. Now we can delete this extension in the line. That's good. Now let's draw another rectangle to include the distribution panel. Rectangle. And let's make it to P like this one. It can P in magenta, and we can copy here this text and make it to P the distribution panel. Now we can select all of those parts and make another layer and rename it here to P the distribution panel, and include all of those parts and make them to P and the distribution panel layer. Now this text will P load 2, for example, and this one will P load 1 and exit and yes. And also let's move to the inverter layer, and now let's draw another rectangle and let's change its color. And here we have finished. So we have designed all the required components for the off-grid solar system layout. Here if you select any part it will refer to its layer. This is the solar panel, this is the protection port, and this is for the charger controller. And if you select this one it will be for the wiring, and this one for the battery system, and here this one for the inverter, and finally this one for the distribution port. So by this way you have learned how to express any off-grid solar system diagram or any on-grid solar system also diagram. You have known what's the idea, how to draw the parts, how to make different layers, how to make a plug for anything you need for any device, and so on. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In this tutorial we will start on the second main part of the solar system, which is the GRIDTIE solar system. as what we illustrated before was about the off-grid solar system where we are feeding some electrical loads in your building. But now this is the time to see how the grid-tie solar energy is different. So fasten your belt and let's get started. The aim of this tutorial is to know what is the concept behind the grid-tie solar system, and also we will know the different components that represent this solar system. So let's go ahead. The main concept behind the grid-tie solar energy is that the power produced from it is going directly to the electrical utility or the grid. So we can say that we are generating the electricity to feed the grid with it. And there are two main types. The first one is the solar farms. And at those solar farms we have a huge number of solar panels as you see here. And those panels are spread on a large area. Then they are generating a large amount of electricity. And for this reason, this type is used as an economic project that you can construct to supply the utility with the electrical power like any other power stations. So we have a power station here of the solar farms, but it consists of a large number of solar panels, not the wind generator or the steam generator like the other power sources. Then we get the price of the electricity you supply from the utility or from your government. And for this, we can estimate that the components of the on-grid solar systems are the panels and the inverters only. Then the power is injected into the grid. So there is no need to have a charger controller or some batteries, as we don't need to store the energy because there is no loads that we need to feed. But we just convert the solar energy to an electrical energy directly to the grid. So that's about the first strategy, which is the solar farms. Now the second strategy is the tie-on projects that are applied in the building roofs. And those projects are implemented if you have a roof area that is empty, then you are spreading some solar panels on it to generate the electricity and then to supply the grid with this electricity. Therefore, this type has also the same process. The panels, then the inverter, then the grid. But you as a building owner has two types of electricity or two sources of electricity. The first one is from the panels to the grid, and the second one is from the grid to the building, as your building at this time is fed directly from the grid. And at this case, the government treats you in a way called the net metering. And at the net metering, the money that you will receive equals to the money that your panels generated due to the produced energy minus the money that your building consumes. As you are consuming electricity that you must pay for, and also you are generating some electricity that you will get its money back. So this is about the second part of the building project. That's good. Now let's talk about the different components that are used in this type of the solar energy. Here the first component is the panels, and it's exactly as we illustrated in the off-grid system. It's the same main three types, the monocrystalline, the polycrystalline, and the thin film. You can differentiate between the polycrystalline and the monocrystalline in that the monotype has the declined edges of the cells, while the polytype has a sharp square angles, so it's a complete rectangle. While the thin film looks like a clear flat as you see. And also we knew before that the monocrystalline is the most efficient and it has the highest price as it produces the largest output power. And also for the grid-tied solar energy we have the same output powers ranges for the panels. Here 100 watts, 150, 255, 260 and up to 320 watts. So you can choose the panels that gives you the total output power you need to produce. But note that also when the panel's power increases, its size or dimension increases also. And now the second part of this system is the inverter. As the inverter job is to convert from the DC power that is produced from the panels to the AC power that we will feed the grid with it. So those are some types of the grid inverters. Here there are many companies that produces those type grid inverters. Hence they do the same job, but they differs only in the output power in each of them. So we have a wide range of the power that those inverters can produce. And you select the inverter as we learned before according to the power that you are generating. But you may ask now, Does the grid tie inverters do the same job of the tie-off inverters, or they has exactly the same facilities? This is actually wrong, because there are two main differences between each of them. Here at the on-grid inverters, there must be a synchronization option available in the inverter. And the synchronization is that the inverter must produce the output electrical energy with the same value of the voltage that the grid need. So the grid and the inverter must have identical the same value of voltage. Also with the same frequency and with the same phase shift. This is because the utility from its name is called the ring main unit, which means that it's a global ring that receives the power from any source and transmits the power to any consumer. So it must have the same value of the voltage and frequency, and those values mustn't be changed. And for this, the inverter must be automatically programmed, not be connected to the grid unless the inverter and the grid have the same condition of the power and the frequency. While on the off-grid system, the inverter is not connected to the utility, but is connected directly to the electrical load. Therefore, there is no need to have a synchronization option in those inverters. Alright, now the second difference is that at the on-grid solar system, the inverters are designed to receive an input voltage at a high range of about 1000 volts. So its input voltage range is very high than the off-grid solar system, and you may wonder now, why that crucial difference between those types of inverters? Or why we need to increase the voltage at this high range? This is because at the on-grid inverters we have a large number of panels, and this is because we need to produce a large output power to inject the grid with it, so we can get a valuable economical income from that project. But as the power is large, suppose now the voltage is a lower value, now the current will be a very large value. This is because we have a constant large power. So when the current increases, the power losses will increase, and then the voltage drop will increase. And also the cable sizing will increase to carry this large current. So all of those are some disadvantages that we don't need in our system. But on the other hand, if we increase the voltage to a large value, the current level will decrease, and then we will get a smaller power losses and a smaller voltage drop, and also a smaller sizing of the cable cross-sectional area. So for those reasons, we use the inverters that has a large voltage range. On the other hand, at the off-grid system, the power is naturally small. This is because we are feeding some devices in the building, so we don't need a large power as what was on the on-grid system. Hence, the number of panels is small, and then we use a smaller range of voltage and current, and this is because the power itself is small, so we don't need to increase any of the voltage or the current. And for this reason, we use a lower range of the input of the inverter to be about 48 volts. So that's about the different components of the GRIDTIE solar system and its overview. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In the previous tutorial, we took a tour on the on-grid solar system as a whole, and this is the time to go in depth in this interesting part of the solar system world. So fasten your belt and let's get started. The aim of this tutorial is to know the different steps of implementing the on-grid solar system project. As we are breaking the project into some simple steps to understand it well. So let's go ahead. The first step of designing the on-grid solar system is to detect the location of the latitude and the longitude. This is what we did exactly in the off-grid system. As the solar radiation, then the energy depends on the location of the solar station or the solar farm on the Earth. Now the second step is to calculate the required angles, and the first angle we need is beta, the tilted angle, which is the angle that the solar panel will be installed on the Earth with. And on the on-grid system, we put it to be equal to the latitude. And this differs from what we did in the off-grid system, because at the off-grid system we install beta based on the worst case, which is 21 December, which has the worst solar radiation in the year. And we did the thing at the off-grid system because we were related to the electrical loads that we need to feed. So we must make the system able to supply the loads at any case, the worst case and the best case. So there must be no probability that our design system fails to supply the electrical loads. But here at the on-grid system, we are not connected to any loads, but we just inject the generated energy to the grid. So there is no constraints on the system that imposes us to produce a specific amount of energy. As we are not related to any load, so there is no need to assume the worst case. But when install beta to P equal to the latitude at this condition, we get the best average benefit during the year or during all the months. So the best average benefit is got when beta equals the latitude, as the solar rays will be perpendicular to the panels. Therefore, we are getting the most economic income as we are having the higher electrical output through the year. And this is our aim now, is to get the most better revenue through the year, as we are constructing basically an economic project. Alright, now the next angle is to get the average declination angle at each day in the month. So we get it at each day in the month to get the declination angle in the average of the month. And therefore, after getting the declination at each month, we get the elevation angle according to each month day, and then we get the average of each month. So the declination has the same equation as what we did in the off-grid system. Here it's equal 23.5 times 360 over 365, which is the number of days in the year, times 284 plus D, where D is the day number in the year. So the declination angle depends only on one variable, which is the day number that we detect the declination angle of the Earth on it. And also the elevation angle depends on the latitude and the declination. So it's equal 90 minus the elevation angle plus the declination angle. So we get those values for the average of each month. But for simplification in the manual calculations, we will get it to P at 21 of each month. This is to get the declination angle 12 times, only one for each month. But it will be very hard for the manual calculation to get the declination angle 356 times in the year. Then the elevation angle also 356 times also. So to shorten those hard steps in the manual calculations, we get it at 21 of each month. That's good. Now the next step is to get the peak sun hour at each month, and we get it with the same equation as we did on the off-grid system. Here S sub m equal S sub h times sine alpha plus beta over sine alpha, where S sub h is the global horizontal irradiation, and we get it also from the NASA database, and beta is the tilt angle, which equals the latitude as we said, which we got as we mentioned at the average of each month. So we have the global horizontal irradiation and the beta design value, and the alpha we get it at the average of each month, and for simplification also we get it at 21 of each month. So this means when we get S sub m at 21 of each month, we will calculate it in the manual calculations only 12 times. But for the average of each month, we will calculate it each day of the month, then get each average of each month. Now the first step is to get the spacing between each two adjacent panels, and as we learned before, the spacing design depends on the maximum shadow that each panel can produce. So we calculate the spacing, which will be long enough not to make a shadow from any panel on the adjacent panel. Here the spacing X is determined according to the same equation of the off-grid system. So it's equal sine 180 minus alpha plus beta times Y, which is the panel width. So X here is the maximum shadow, and we get it at the worst irradiation day in the year, which is 21 December, which has the longest shadow as it has the worst irradiation. And then after getting the maximum shadow, we can get each single panel area, which equals to the maximum shadow times each panel width. And after that, the number of panels that we will use will equal to the total available area of the project over each single panel area. As on those projects, the crucial factor is the available area, as we need to get the highest available output power, then the highest income. But what will limit you is the available area, as if you are constructing the on-grid solar system on a building roof, the available area will be limited. So you need to calculate the available number of panels to use according to the total available area. While if we have a large area to construct a farm project, we can get a larger number of panels as we have a larger area to spread them on it. And also, after getting the number of panels, we can get the total power of the station, which equals to the number of panels times each panel power. And you can note that we have neglected the total losses in the station, so we suppose that the total power generated from the panels is the power that the grid will actually receive. And you know, this is practically right for two reasons. The first one is that the losses in the on-grid system is very small, as there is no charger and no batteries, so there is no losses in such those parts. And also the on-grid inverters themselves, so the inverter themselves are manufacturing with a higher quality than the off-grid inverters, so the losses at the on-grid inverter will be very smaller than the losses at the off-grid inverter. Here the losses at the on-grid inverter may be about 3%, while the losses at the off-grid inverters can exceed 12%. And also the second reason for neglecting the losses is that we are not connected to a load, so there is no need to produce a specific amount of power, as if the power decreases there will be no problem, so any amount of power produced is injected directly into the grid. Therefore, no matter what its amount is. Therefore, there is no commitment with a specific load that has a specific power that we need to feed. Then we can detect the inverter sizing according to the power of the station, but there is an important note here that we face on the practical working, which is that in the small project which lays in the small building roofs, the total power of the station will be large. Hence, we can get one single inverter that can convert the total station power. But in the large power stations, the power of the station will be larger than each inverter power, and then we use a common strategy which is called the string inverters. So if each inverter power is 1/3 of the total power of the panels, we group 1/3 of the panels on one inverter to get the first string. And then the other two strings are equally divided to be equal to the first string. And all of them are connected to the same grid. So 1/3 of the panels are connected to one inverter, and the other 1/3 are connected to the second inverter, and so on. So that's about the first 6 steps of designing the GRIDTIE solar system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial, we started illustrating the steps of designing any GRIDTIE solar system, and in this tutorial, we will continue those steps. So fasten your belt and let's get started. The aim of this tutorial is to complete the different steps of implementing the on-grid solar project. As we are breaking the project into some simple steps to understand it well. So let's go ahead. At the 7th step, we have to specify the required information about the connection of your panels. We have known previously the power of the station is larger than the inverter power. We split the system into some strings. So that's about the inverter connection. But for now, what about the panels connection, not the inverter? So we know that the panels are connected in series and in parallel. So what will be the number of panels that are connected in series at each branch? Here the number of panels per each branch equals to the total branch voltage with its pass voltage over the panel voltage, which is the open circuit voltage of the panel. So for the pass voltage, it's specified according to the inverter input voltage. As we said before, the GRIDTIE inverters have a higher input voltage range. It's about 1000 volts, and we detect this value from the inverter datasheet itself. And for each panel open circuit voltage, we get this value from the panel datasheet. Now to get the number of panels, it's equal to the total number of panels over the number of panels at each branch, as the number of panels was calculated from the previous step. And for the number of panels per each branch, we have just calculated it. Now we have the 8th step, which is a very important one, which is the feasibility study. So at this step, we need to know what is the total revenue that you can achieve from the project and what is the net income that is available. Firstly, we need to calculate the energy that our station produces each month, and it's equal to the total power generated, which is the station power times the peaks an hour for each month. As we calculated the peaks an hours 12 times, 1 for each month, times the number of days in that month. This is because the energy equals the power multiplied by the time, but the time now is the total hours in the month that we have generated this power at which, so it's the peaks and hours times the day numbers. Now, after getting the energy, we need to get the total income per month, and it's easily equal the energy per month times the tariff. And the tariff is the price of each kilowatt hour of the generated energy, or it's the money that you as a station owner will gain from the government for each kilowatt hour that you generate or that your station generates. Also, after getting the energy per month, the total income per year equals to the summation of all of the month's income. But after getting the income, we need to know what will be the cost that you will pay for to construct this project. So the capital cost equals to the panels price plus the inverter price. And we are getting those prices from the market that we are handling, so there is no fixed price for the panels or for the inverters, but this depends on some factors like the manufacturing company that manufactures those panels and inverters, as there are some projects with a high quality and hence a higher price, and also there are some components with a lower quality and also a lower price. So the capital cost varies greatly according to your case. And finally, in the feasibility study, we need to know what is the number of years that you as a project owner need to pay for the capital cost that you have spent. So this is equal the capital cost that you have spent over the total income per year. Which means after those years you will get a net income that represents the net amount of money that you will get per each year. Now the steps that we need to follow in the GRIDTIE system is summarized in this table here. Firstly, we need to get the horizontal irradiation at each month and the year from the NASA database. Then we calculate the tilt angle across the year, which equals the latitude. After that, we get the declination angle at each month average days, or we get it at 21 of each month for simplification. Then we get the elevation angle according to the declination determined. Also, we get the peaks and hours or the global tilted irradiation according to the angles beta, alpha, and also the S sub h determined previously. So we get it at each month also. And then we get the income per month, which equals the energy per month times the tariff. And after that, we get the income per year, which is the summation of the total month's income in the year. And then the capital cost is determined according to the component's price. And finally, we get the net income after paying the capital cost. So that's about the steps of designing the GRIDTIE solar system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we're all together again. In the previous tutorial, we have finished discussing the steps required for designing any GRIDTIE solar system. And in this tutorial, we will start on a practical example to apply on those steps. So fasten your pull and let's get started. Firstly, we need to specify the location that we are constructing the GRIDTIE system at which. So suppose now we are working for a project in Rome, Italy. Then we need to get the coordination of Rome. And as used, we will use the lat.long website to detect the latitude and the longitude. So let's hit it. Here, this is the website and we can type now in this part Rome and then find. That's good. Here, those are the coordinations of Rome. Its latitude is 41.9 and its longitude is 12.4. Now let's go back. Here, after detecting the latitude and the longitude, we need to detect the tilt angle theta. So the tilt angle theta equals the latitude as we illustrated on the previous tutorial. So it's 41, but the nearest standard value is 45. So we select the installation angle of the panels on the ground to be with 45 degrees. Then we need to detect the declination angle at 21 of each month. But for now, we will take a sample only to calculate it at 21 December. So the day number 21 December equals 355. Then the declination equals minus 23.5. And after that, the elevation depends on the declination and the latitude, so it's equal to 24.6 also at 21 December. Now, after getting the angles, we can move to the next step to calculate the peaks an hour. So it depends on the global horizontal irradiation, alpha and beta. Then we get the S sub h from the NASA database, and we have actually detected it at each month. So those are the 12 months value of the global horizontal irradiation. And because we got alpha and beta at 21 December, so we will get the peaks and hours also at 21 December. And at this condition, the global horizontal irradiation at December equal 1.48, then alpha equal 24.6 and beta equal 45. So those are the values that we have just calculated on the previous slide. And then the peaks an hour at December will equal 3.33 hours. Also, we need to detect the peaks an hour of all of the months, but we are taking now just an example. That's good. The next step is to detect the spacing between each two panels, and for this we need to detect the panel length. So we detect it from the panel datasheet. Here those are the dimensions of the panel that we will use. As you see, its length is about 2 meters and its width is about 0.99 meters. Now we get the spacing between each two panels to P with the length of the maximum shadow available in the year, which is at 21 December, so it's equal 4.5 meters. As alpha is detected at 21 December, so the value of the spacing will be got at 21 December. Now, after getting the spacing, we are ready to get each panel the required area. So the panel's required area equals to the width of the panel times the maximum shadow. So the width equals to 0.99 meter and the width equal to, and the shadow equal to 4 meter. So the single panel area will equal to 4.46 meters square. And then the number of panels needed to use are equal to the total available area over each single panel area. Hence, suppose now you as a project owner has a piece of land that you will spread the panels at which, and its area is about 1950 meters square. And at this condition, the number of panels will be 437 panels. And then we need to get the power of the station, which equals each single panel power times the number of panels. So we have 437 panels, and from the datasheet of the panels we use a panel of a power 345 watts. But there is a note here. You may have noticed that the length of the panel we are using is 2 meters, which is longer than the panel which we use in the off-grid design. So at the off-grid design, its length was about 1.6 meters, but the power output from it was about 250 watts. While here, this panel produces a larger power, larger than 300 watts, and for this reason, its length is higher than the previous panel length. Now the total power of the station is about 150 kilowatts, so we are constructing a solar station that gives us a total power of about 150 kilowatts. That's good. Now for the inverter sizing, it must be equivalent. That's good. Now for the inverter sizing, it must be equivalent to the power of the station, but the inverter that we will use has a power only of 50 kilowatts. And for this, we will use the string strategy. And as each inverter power is about the third of the total power of the station, so we will use 3 inverters or 3 strings. Hence, this is the datasheet of the inverter that we will use. Its input DC power is about 55 kilowatt, and its input DC voltage range has a maximum value of about 1100 volts. And for this, we will use the pulse voltage to be about 1000 volts. And because each inverter will have 1/3 of the station power, so we will divide the panels into 3 parts for each inverter. Therefore, we find that 437 panels over 3 strings will give us about 145 panels. So each string has 145 panels that is connected separately to one inverter. Then this inverter injects its power to the grid directly. Good job. Now for the connections, we will find that the number of panels for each branch will equal to the pulse voltage over the panel open circuit voltage. And from the datasheet of the panel, we will find that the open circuit voltage equals to 46.4 volts. So the number of panels at this condition will be 1000 volt over 46.4, which is about 21 panels. And also the number of parallel branch logically will equal the total number of panels over the number of panels per branch, so it will be about 7 branches. Alright. The final thing we have now is the feasibility study. Therefore, we need to calculate the profit from the project. And firstly, we got the energy for each month, but for simplicity, we will get it at December only, as we have got the peaks an hour at December. Here it's equal to the total power times the peaks an hour per each month, or for that month, which is December, times the number of days. So the total power is about 150 kilowatt, and the peaks an hour at December is 3.33, and the number of days is 31. So the total energy per month at December will be about 15.56 megawatt hour. And then the total income per month will equal to the energy times the tariff. And the tariff may change from one country to the other, but for a standard value it's equal about $0.4 per kilowatt hour generated. So this means the total income that we will get at December is about $6.22K. And then after calculating the total income per month, we need to calculate the total income per year, which is equal to the summation of each month's income. Now after calculating the total income at the whole of the year, we need to calculate the capital cost that we will pay for. So the capital cost equals to the panels cost plus the inverter cost. And as we mentioned, the prices of those components varies greatly according to some factors, as they have no standard values, but from the market we have detected the panel's price to be about $100 per each panel, so 100 times the number of panels plus the inverter cost, so the cost per each inverter is about $150K per each inverter. Then we have 3 inverters, then the capital cost will be about $493.7K. And finally, the required years to pay the cost for this project, so we need to compensate the capital cost that we have paid for, so the years after which we will pay for those components will equal to the capital cost we have paid over the total income per year. So that's about a sample of the manual calculations, and on the next tutorial we will see how to do all of those calculations automatically on the Excel software. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In the previous tutorial we have finished the calculations of the practical GRIDTIE solar system design, and now this is the time to design its layout on the AutoCAD drawing to express our working in a pretty diagram. And if you remember, at the OFFGRID solar system design we have learned from scratch how to draw any design and how to apply any AutoCAD order from scratch, so we will not repeat those steps from very beginning, but you can try that yourself to practice yourself on the AutoCAD design and to be familiar with the AutoCAD orders, as you have now all the required AutoCAD orders to apply on any design. And if you forgot any of the design steps, you can jump back to the OFFGRID AutoCAD design, as we illustrated all things and details there. And now let's understand how the on-grid system components are connected to each other, as this is the diagram of the practical system that we designed on the previous tutorial. So let's anchor it. First of all, you can notice that we have 3 strings, and each string of them is connected to one inverter, here those 3 inverters, and then the whole inverters are connected to the transformer, and then from the transformer to the utility or the grid. So the transformer step up the voltage to inject the power from the inverters to the grid. And we have 3 strings because, as we mentioned before, we have 3 inverters, and each inverter is rated of about 50 kilowatt, so the total power is 150 kilowatt. Hence we can say that about 33% of the panels are connected to one inverter, and another 33% is connected to the other inverter, and the third part or the remaining part is connected to the third inverter. Now when focusing on the panels at one string, we will find that each panel open circuit voltage is about 46.4 volts, and we have 26 panels that are connected in series, and also we have 7 branches, so when going down we will find that we have 7 parallel branches, and each of them consists of 26 panels. And by this way, when multiplying 26 panels times 7 branches, we can get the total number of panels that are connected to each string. Then you will find that for each series branch we have a fuse here, and this fuse, as we illustrated before, is used as a protection device to protect the circuit from any short circuit condition. And also the calculations of the cable sizing and protection of the on-grid solar system design are the same as the off-grid design, so you can revise those steps from the off-grid design tutorials if you forgot any of them. So as we made our design on the previous tutorial, we will find that when we have 26 panels in each branch and each open circuit voltage, which is the maximum voltage of each panel, is 46.4 volts. So when calculating the total pulse voltage, it will be about 1000 volts. So the 1000 volts here is the input of the protection distribution panel, and then from it to the inverter system. So after the panel system, we have the protection and distribution panel that has some fuses also inside it to protect the main cables from any short circuit condition that may damage the system. Then the output of the protection panel is going to be an input for the inverter, and the inverter rating is about 50 kilowatts. So the inverter converts from the DC power to the AC power for a three-phase output AC power that has a line voltage of about 400 volts or 380 volts after the losses. This is for the British standard, and for the American standard it will be 220 volts for the three-phase. And here we have those three dashed lines that represents the three-phase. So this is a single line diagram that's represented by a single line, but we have those three lines to represent that system to be a three-phase, not a single phase. And then we have a circuit breaker that works as a protection device also and a controlling device for the power. So as we illustrated before, at the low voltage AC power, the protection devices are the circuit breakers, while at the DC power, the protection devices as the fuses, like what we have inside the protection panels here. And finally, the circuit breaker feeds the main transformer. So we have a connection point here, or we have a distribution panel that connects those three strings with each other. So we can say that this first string or this first module is exactly identical to the second string, and it's identical to also the third string, and both of them are connected to the same transformer here, and the transformer has a circuit breaker also that is outgoing for this distribution panel. So the circuit breaker works as a protection and controlling device also, and it's an ingoing circuit breaker that's rated to withstand the full power, which is the three inverters power of 150 kilovolts. And then, as we mentioned, the transformer is supplying the power to the grid. So by this way we can express the single line diagram of the GRIDTIE solar system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In the previous tutorial we finished the manual example of the on-grid solar system, and this is the time to generalize it by constructing an Excel program to be able to design any GRIDTIE solar system and calculate its parameters easily. So let's get started. If you remember, this is the Excel program that we constructed for the off-grid solar system, and now we will modify it to be an on-grid program, not an off-grid. So let's delete those power and energy tables, as we are not connected to any electrical load to feed it, but we just inject the energy produced into the grid. That's good. Now we need to delete those tables also, as we don't need them. We only will work on this table and we will modify it. So let's delete those tables. Good job. Now the first thing we need to do is to change the latitude and the longitude. So those are the latitude and the longitude of the previous example. Here, this latitude and this longitude, we need to change them as we are working now in Rome in Italy. Here the latitude equals 41.9 and the longitude equals 12.4. Then we need to insert a column for the number of days in each month, as we need it in the energy calculations. For that we will select this row and then press insert and insert sheet row. Now rename it to P, number of days. And I have prepared those values previously, so let's paste them here. And for the number of each month days, I have prepared them previously, so we can insert them here. Very good. Now we need to modify the equation of the tilt angle, as it's equal to the latitude now. So we go to it and then delete those ones and refer to the latitude, so X is the latitude angle, and then press OK So as you see, all the cells of the tilted angle has been changed automatically, and also the design value of the peta has changed directly to 45 as it's the nearest value to the 41, which is the latitude. But there is a hint here. If you jump directly to this section without watching the Excel design tutorial in the OFFGRID system, or if you have forgotten any of the steps of the OFFGRID design, you need to go back and revise it, as all what we are constructing here depends mainly on the construction of the OFFGRID solar Excel design, and we are just making some modifications to make it an on-grid one. Now we need also to detect those 3 columns, as we don't need them. We don't need the SM minimum, we don't need the minimum peaks and hours or the maximum or the peaks and hours final value also, as we will not work on those values. Here we select them and then delete them. That's great. And also we need to add another 16 rows, as we will work on additional another 16 rows, and for this we can select this row and then drag down to go to the row of 27. Here 27 is the final row we need, and then we can have a right click and then insert. That's good. Here we have entered those 16 rows for the new data that we need to enter. Now the first piece of information we need to enter is the panel length. So we type here panel length, and then it will equal 2 meters. So equal 2 meter. And now merge those cells, merge and center. And we need to merge the rest of the 7 upcoming cells. So we can copy the format of this cell, then drag down to 7 rows. That's good. Also we enter the panel width now, so we type panel, and it will be 0.992 meters. So those are the same values that we entered in the manual calculation. And now for the spacing, we need to type spacing, then it will equal sine 180 minus the elevation angle at 21 December. So this is the elevation at 21 plus the tilted angle, which has a standard value. Now it will be times 3.14 for the conversion from the radian to the degree system over 180. Then it will be times the panel length. So select the panel length and then over sine the elevation angle. So we can copy the elevation angle here, Control C, and paste it there. Then times 3.14 over 180, and then close the parentheses and press enter. Then we have forgot another parentheses here and another one, then press enter. So that's good. We have got the spacing between each 2 panels to be 4.5 meter. Also for each panel area, it will equal the spacing times the panel width. So we type here panel area. Then we can type equal and select the spacing, then times the panel width. So select the panel width cell and press enter. So as you see, each panel will consume an area of 4.4 meters square. And for the total area we have, it was about 1,950 meters square. So we can assign it here, total area. Then it will equal 1,950 meter. And for the number of panels, it's equal the total area over each single panel area. So the num of panel, and then it's equal, and select the total area over each single panel area and press enter. So we will have about 436 panel, but we don't need it to be a float value, as it must be an integer value, as it's a number of panels. So we have no float values. So for this, we can use the integer function inside the Excel. Here we type int and open a parentheses and close it here and press enter. So that's the number of panels that we need for this design. Alright. And at this time, we need to enter each single panel power. And for this, we can type here panel power. Then, as we have got from the datasheet on the previous tutorial, it was about 345 watts. Therefore, at this point, we are ready to get the full power of the station, which equals to the number of panels times each panel power. And for this, we type power of the station, and we will get it in kilowatt, not in watt. So we press K watt, and it's equal the number of panels. Here this is the number of panels, then times, then each single panel power, so access each single panel power, and press enter. But for now, let's unmerge those two cells as we don't need them. Here, let's press that. And we can enter the second cell value at February to be equal to the first cell value. So let's type equal and then assign this cell and press enter. And also we will drag to the last cell, as at all of the year's months we will have the same output power. This is because this is the output power or the maximum output power of the station. It's not the energy, so it doesn't depend on the time or the peaks and hours, as we are talking about the power now. That's great. We have got our solar station power to be about 105,000 kilowatt, but we need to divide it by 1000 as we need to get it in kilowatt, not in watt. So we divide it by 1000 and all of the values will be changed automatically. So that's about the power of the station, and on the next tutorial we will continue the rest of the design. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we're all together again. In the previous tutorial we calculated most of the on-grid Excel program calculations, and we ended with the calculations of the total power of the station, and at this tutorial we will continue this journey. So the first thing we need to do is to enter each single inverter power, and for this we can copy the content of this cell and let's paste it here, Ctrl V. And we can change the station to be inverter. So we will enter the power of the inverter in kilowatt. And if you remember on the previous tutorials in the manual calculation, it was 50 kilowatt. So we type 50 and press enter. Now the number of strings equals to the power of the station over each inverter power. So let's go there and type number of strings. And here it's equal the power of the station, so select the power of the station cell over each inverter power, so this is each inverter power cell, and press enter. And at that point we have approximately 3 strings, and for this we don't need it to be a float number, we need it to be an integer, so we type here int and close this one, and it's sharply 3 strings. But you know, till now we didn't get the energy of the station at each month, and to do that we easily type energy per month, and it's equal the power of the station times the peaks an hour at January. So let's go up and select the peaks an hour at January, then times the number of days. So the number of days at January is 31, and for this reason we have inserted the number of days here at this row. Now press enter. Good job. Here the energy generated from the station at January equals to 17,127.9 kilowatt hour. And we can apply the same formula for the rest of the months easily by going to this cell down and drag to the last cell. So those are the values of the generated energy from the station at each month. And it's in kilowatt hours, so let's type here kilowatt hour. And also we need to enter the tariff at which we will get the money. So it's a fixed value, as we said before, to be $0.4 per kilowatt hour. And for this we type here tariff. Then it's equal to 0.4. Then enter. And to apply that on the rest of the cells, we easily type on the next cell, it's equal to the first one. So select this cell. Now drag from the second cell to the last one. Good job. So at this point we are ready to get the total income for each month, and it's equal to the tariff times the energy per month. So we type here income per month, and it will be in K dollars. Then it's equal the energy at each month, so we select the energy at January, then times the tariff. So we select the tariff and press enter, and we can drag to apply that on all of these cells. And this, for example, the income for March, which is $9,693. So we need to divide by 1,000 to get it in K dollars, not in dollars. Here we divide by 1,000. And we can drag this cell to apply the changes in all the other cells. That's good. Here those values in K dollars. Then to get the income per year, it's easily, we type here income, and it will be per year. Then we can merge all of those cells, merge and center, and let's fill them to be, for example, this white blue, and we can make the color to be white. Now we can increase the font to be, for example, 36, and then it will equal sum, so we will use the sum function inside the Excel. Then start from the first cell income per month to the last cell, so the first cell is K24, so here from K24, and then it will be until, here this last cell is V24, so V24, and then close the parentheses and press enter. Very good. We have a total value of income per year of $113.4K. So this is the total income that we will get from the station at each year. But the next step now is to get the capital cost. So we type here capital cost. And then for the capital cost, we will format those cells quickly, not to waste our time. That's good. We have formatted them. Here the first cell for the inverter price. So we type inverter. And here it's a price equal $150K. Then we need to enter the panel price. So the second cell will be for the panels. And the cost for each panel, as we said before with the cables, is about $100. So it's about $0.1K. And finally, for the total cost, here the total, it will be the inverter cost plus the panels cost. So we type here, and it will be times the number of inverters or the number of strings, so they are equal. Here we select the number of strings, then plus the cost of the panels, and then times the number of panels. So we have a number of panels of 436. Let's select it and press enter. Here we have a total capital cost of this project of about $493.6K. And finally, for this tutorial, we need to detect the number of years after which we will finish paying the costs of this project, and we will start receiving a net amount of money. And for that, we type here years for paying money, and then merge those cells, and it will be the total capital cost over the yearly income. So we will type equal the total capital cost over the income per year. This is the income per year, and this is the total capital cost, and now we press enter. That's great. Here we need about 4 years to compensate all the money that we have paid, and after those 4 years, we will receive a net income from our GRIDTIE solar station. Hence, by this way, we have learned how to calculate a complete program to calculate all the required parameters of the GRIDTIE solar system. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. This is the first tutorial for us to apply on all what we learned on the solar energy design on the strong and the widely used software, the PVSYST. So when we open the software, this is the basic window that's appeared for us. And on the upper left, we have the files window, the preferences, the language, the license, and the help tabs. So when you open the language tab, for example, it asks you for the language that you need to work with, English, French, German, and so on. And when we press on preferences, then preferences, here we have 6 tabs. The first one is the user information. Suppose that you have a company and you need to enter your company name, your last name, your address, your zip code, your country, and so on. Also, you can import your company logo here, so that's about some information that you may enter. And then when we press on the internationalization, you can find that those are some settings you can use if you need to use the comma, the dot. Also, this is about the language. You can change it to any language you need. And now when go to the default values, here you can change the units of the program. For example, the energy has a default value of kilowatt hour. You can change it to the megajoule, but we are working on the default values. Also for the pressure, the water flow, and so on. Now when going back to the main window, here you will find that we have those two important windows in the left, the primary design and the project design. So at the primary design, we enter some slide data about the project to make some quick calculations. So we are not going in depth or getting all the details about the project, but we just use it for quick calculations to quickly come up with the results, for example. And on the right here, we have the types of the projects that we can work on in the primary primary design, here the grid connected system, which has the GRIDTIE or the on-grid system, and also the standalone, which has the off-grid system, and also we can make a solar energy design for the pumping systems. So those three types are included in the primary design. But at the second tab on the left, we have the project design, which is the complete project at which we will enter the complete data of the project at all details. Then we can get the results in all details also with all the specifications of the project. So when pressing on it, you will find that you can make an on-grid system design also, an off-grid system design, and also a pumping design. And here we have additional system which is the DC grid. So let's start in this tutorial with the preliminary design. Here we press into it, and then let's choose the grid connected or the on-grid design. Then this window appears to us that represents the diagram of the on-grid design. Here those are the panels connected to the inverter, and then the inverter injects the power through the grid, and the grid also has another flow of the power from it to the loads in the house. So as we illustrated before, we are working at this design with the net metering technology. So this meter has two flow of the power, flow from the grid to the house to feed the appliances, and another flow from the panels to the grid to feed the electrical grid. So the electric meter at this condition calculates the difference between the incoming energy and the outgoing energy. Now let's start with this slide design by pressing on the side and meter tab here. So the meter word, for anyone who doesn't know it, it describes the climate condition or the weather at this place. Now this primary window that appears for us, it asks us to enter the project name, and also it asks us to enter the country that we are making the design at which, and also to enter the city and the country that we are making the design at which. So we can choose, for example, the United Kingdom, and let's choose the city to be London. And press enter. Now we can rename the project to GRIDTIE at London. Then we can press on OK, and then we will press on the system tab to enter the required information about the project. So on the left it asks you to choose one of those three options, to enter the project area, or to enter the nominal power that we need to get out of the project, or to enter the output annual energy that we need to get from the project. So we have two strategies now. If we have a specific area that it can be increased, we must enter it. But if we have an available area and we need to get a specific value of power output of the project, we can choose the power. Or if we need a specific value of energy at the year or at each year, we can choose the energy. And for now, we will suppose that we have a specific area of the project, so we will press on area. Then it asks you to enter the area of the project in meters square, so we will type, for example, 40 meters square. Suppose we have an area of 40 meters square. And here on the down, it asks you to enter the tilt angle, which is the installation angle of the panels, and also the azimuth angle, which is the angle that the solar panels makes with the south direction on the horizontal plane. So according to those angles, we get the output power of the station. But the best thing about this program is that it allows you to get the best optimized result, and then it chooses for you the required angles according to the result that you need to get. So anyone who don't understand any of the manual calculations or the engineering concepts behind the solar design can choose this optimization option tab here and change the output results through those two curves to get the best output results. Here you can change the tilt angle from this tab here up and down, and also you can change the azimuth angle here from this tab, and you can do the same thing by those two figures here. By picking up this red point up and down, so you can see by picking it up and down, you can change the output value through those curves. And also at the azimuth angle, you can change it by this tab here. So we can pick up this red point to change the output results. But as you see, this is for the annual yield, which has to make a balance for all of the output results or to get the best power for the average of the year. And when changing it to be the summer, for example, you will find that we have a good results. But when changing the results of the summer to get the most better results, so let's make the output results at the peak value here at this. and also we can change this one to P at the peak value. But now when going on the winter, we will find that we have a bad results here. So at this curve, the output power is lower here, not at the peak value. And when changing the tilt value to get the most better results here at the peak value, when going back to the summer, we will find that we have a bad results for the summer. You can see at this curve, those are some bad results, not at the peak value. And this is because when adjusting the winter results to the PVSYST value, that affects the summer results. And also the inverse. When adjusting the summer results to the PVSYST value, this affects the winter results badly. So when changing the summer results again to the PVSYST value here by decreasing the tilt angle, we will find that when going to the winter results that we have also the bad results. So what we want to say is that if we are working on a project that will be constructed in the summer months only, you can make the angle to the PVSYST value at the summer. And the inverse also is right. If you are making a project that will work on the winter months only, or we need to get the PVSYST values from this project at the winter months, so we will adjust the winter results to the PVSYST value. But if we are making a global design that works at all the year, we need to set the peak values at the annual yields. So when going to the annual yields and we are setting the PVSYST values at the annual yields here according to those two curves, we can change the azimuth and also we can change the tilt angle to the PVSYST value. So by this way we are getting an average PVSYST value for the summer and the winter at the same time. So the annual yield gives us the most optimization of the average values of all of the year months at one time, not only the summer months or the winter months. So when going to the summer results, we will find that we have a relational better results, and also in the winter we have a relational better results. Now after finishing this point, we can press on next. Then it asks us about the module type, so it will be standard. Then the technology, it asks us if we are working on a polycrystalline cells or the monocrystalline. So this depends on the panels that we have to work on the project. Here we can select the monocrystalline panels. And also it asks us for the mounting type, if we have a flat roof or we have a tilt roof, or also if we are mounting the solar panels at the ground. So let's select the flat roof for example, and then hit OK. And now we are ready to see the results, so we can hit the results tab. Here this curve represents the irradiation from the sun across all of the months. So on the x-axis we have all of the months in the year. And on the y-axis we have the irradiation of kilowatt hour per meter square. And those here two types of the irradiation. Here the brown represents the global horizontal irradiation and the green represents the global tilted irradiation. So as we illustrated before, the global horizontal irradiation is the irradiation that falls directly to the ground, and the global tilted irradiation, which is the most important one for us now, is the irradiation that falls on the panels we have. And you can notice that for both of them we have the PVSYST peak values or the PVSYST available values at the summer months, then the values decays that you see after it at the winter, and also it decays before the summer months at the autumn and spring. And this is, as we mentioned before, because the declination angle at the summer becomes with a positive value that allows a larger area of the earth to be exposed to the solar rays for a longer period of time at the day. And here at the upper right we have the results. So the output nominal power of this station is about 64 kilowatt, and the output energy across the year is about 62 megawatt hour, and then the total investment that we will pay for is about $227,000, and the cost of the kilowatt hour is about $0.36 per kilowatt hour. And also you can see those data depends on the type of the panels that we used, as we use the monocrystalline panel here. Now we can press on the system output tab here. So this curve represents the energy produced across each month in the year. Also, this is the results table. We can press on it. You can find that this is a summary table for all the results we need at each month from January till December. We have the global horizontal irradiation of kilowatt hour per meter square for each day, and also the system output energy per each day for each month. So each day for January will give us an output energy of 74.3 kilowatt hour. hour, but for the total energy at January, it's about 2,305 kilowatt hour. And finally, we have the summation of all of those values to get the total output energy and the total global horizontal irradiation. Now the final thing we have is the cost analysis in this project, so we can press on costs. Here this is the currency of the project. We can choose it at any one we need, but for us we will work on the dollar or the United States dollar. So the summary tells us about the total module costs or the panels costs, and also the support or the stands at which we will install the panels, and the inverters and wiring, and the mounting costs, and so on. And finally, this total invest cost is the summation of those total costs, and those total costs are the capital costs that we have discussed before. So this is about the invest costs or the capital cost. But we have also a maintenance cost that we can take into consideration, and this running cost is represented at the annuities and the maintenance cost. Then the summation of the annuities and the maintenance cost give us the total yearly cost. So this is a running cost that we will pay for each year, and according to the number of years that we will pay for those costs, we can change the value that we will pay for each month. For example, at 20 years here, we will pay for about $22.4K per year. But for example, if we decrease it to be only 10 years, we will find that the value has been increased to $33.5K per year. This is because we have decreased the period at which we will pay for the annual costs that we need to spend. While at all the time the capital costs is fixed, because the capital costs doesn't depend on the duration, we only pay for it at one time. Now, after finishing the project, it asks us if we need to load another project, if we need to save those results of this project, if we need to print it, cancel, and OK. So we can save our project. Here you have a description about the project, and here this is the project name. We can rename it to GRIDTIE in London, and then press save. That's good. Here from this load project tab, you can load any project that you need to work on, and also you can print the output results of your project. So those are some options in the program, and we can close this one and this one also. So at this point we have finished some of the primary design, at which we are entering some quick data and get some quick results about the program, and at this point we have finished. So basically right now, thank you for watching and see you next tutorials. Hello and welcome everyone. We're happy that we are all together again. In the previous tutorial we illustrated some details about the basic design of the PV software, and now we will continue on the preliminary design to make another example with some different conditions. So let's go ahead. Firstly, hit the preliminary design tab and then press on the grid connected, as we will continue on the grid connected design. Then we press on site emitter, and now we will work on the same example that we have worked on the previous tutorial, which was London. So we can select here all countries. Let's go up and then search for London. Let's go down. That's good. Here this is London. Press OK, and now we will press OK, and at this point we will hit the system tab to modify the parameters of the system. Now we can choose the area. For example, here select the area and let's make it to be, for example, 400 meters square. And we will not change those parameters of the tilt or the azimuth, as we have talked about them on the previous tutorial. But for now we will press on this plus sign here, and those are three options that appears for us. As you see, the first one is the single fixed plan, and the second one is the shades disposition, and we have the third one is the sun shield disposition. So the default option is the single fixed plan, which means that the design that we did on the previous tutorial was supposed to be on one single plan. And this default option means that we have only a row of the panels and we have not some rows one behind the other. Or in other words, the panels we have spread are only on one line, one panel and beside it one panel and beside it one another panel, and so on. So there is no panels behind each other, but there is some panels beside each other. But at this condition, there will be no shading effect from one panel to the other. This is because there is no panels behind each other, so there is no shades from one panel to the other. Now when selecting the sheet's disposition, at this position we are making the panels at a condition to be constructed in rows as you see here. This is a row and this is another row behind it and this is a third row behind it and so on. And at this condition the shadow effect will appear as a factor in the design because according to the distance between each two panels there may be a shadow that appears from one panel to the other. So this diagram shows each panel to be this blue line here, and this yellow ray is the incident ray that falls from the sun on the panel. And then as we learned it before, we can estimate that this angle between the ground level here and this incident ray is the elevation angle. So this is the elevation angle and this one is the elevation angle. Now on the down you can note that we have some parameters that we need to enter for the panels. Here the first one is the pitch, and the pitch is the distance between each panel to the other. So you can note that its default value is 6.6 meter, and that's what appeared in the diagram. Here the distance from that point to that point is about 6.6 meter, and also from that point to that point is 6.6 meter. And as you see, the second option here is the collector bandwidth, and the collector bandwidth is the length of the panel itself. So this is the length of the panel that we were getting its value from the panel's data sheet. Here when increasing it, for example, to be 4 meter, you can note that the length of the panel has been increased. Here we can select it and increase it manually. So you can note that when I'm lengthening it, so the length is increased or the length is decreased according to the condition. Now let's make it back to be 3 meter. And here the third option is the top inactive band. And the top inactive band is the difference in the length of the stand of the panel and the panel itself. This is because, as we learned, the panels are installed in some stands. But it's not necessary to have the same length of the panel and the stand. So the stand may be larger in length from the panel. And here this inactive bandwidth is the difference in the length. So when I'm increasing the stand length, you can note that the difference in the distance is increasing. Here it's 1.7 meter, here it's 2 meter, and when I'm decreasing it to make the two objects align with each other exactly, so the difference is 0. But you know, it's recommended to get the stands for the panels with the same length of the panels itself, not to increase the shadow from one panel to the other. This is because when I'm increasing the stand length, so the shadow will increase on the panel to the other. Also at the bottom we have the bottom inactive band, which is the inverse of the top inactive band. So it's the difference between the panel length and the stand length, but from the bottom. Here I can decrease the difference between them to be, for example, 0.5 meter. And you can note here that there is a difference between the panel length and the stand length. So this is the difference, but from the bottom, not the top. So these values may be 0, and this depends on the mechanical structure of the panels. And for now we will make this one to P0 and this one to P0 to align the panel and the stand. Alright, now our aim of the optimization is to use the largest available area of the 400 meters square that we have by spreading the highest number of panels available to get finally the highest output power available, but at the same time getting the lowest shadow available from the panels on the other. And to check if we have a higher shadow or no, and also to check if we are consuming a larger area from the total area we have, we can see on the upper here we have two parameters, the shading limit angle and the ground coverage ratio. So the shading limit angle represents the value of the elevation angle of the solar rays, that if the elevation angle is smaller than it, so the elevation angle is smaller than this limit angle, there will be a shadow from the panel to the other. This is because the elevation angle changes from the day to 0 when the sun starts to rise until 90 degrees at the peak value of that place. So it's logically that when alpha is a smaller value, the backward panel like this one here will be shaded. And when the sun rises, so when the sun rises on the sky to be at this position, for example, so this backward panel will have no shadow from the front panel. This is because the elevation angle alpha has increased and the sun has rises up to this position, so the sun will cover all the panel. So we can say that alpha limited here is the critical value or the critical angle. Before it there will be a shadow on the backward panel, and after it, or when having a value of alpha higher than it, there will be no shadow on the backward panel. And here we can represent this concept by this animation. Starting from 6 a.m. to 7 a.m. the sun is rising, so the elevation angle alpha still a small value. Then there will be a shadow from the front panel to the backward panel. And after that, at the period from 7 a.m. to 8 a.m. the sun will start rises more and more in the sky, so the elevation angle increases until it reaches the limited angle alpha. So exactly at this point there will be no shadow from the front panel to the backward panel, while before it there will be a shadow and after it there will be no shadow. So for this reason it's called the limit angle. And for this reason, when increasing the distance between each two panels, we find that the limit angle decreases, because the shadow from the front panel to the backward panel decreases. And now we need to try that by increasing the distance between each panel to the other. So let's make it to be 9 meters, for example. So you can note that the shading limit angle has been decreased from 20 to 13. But you can note also when increasing the pitch distance, the ground coverage ratio is decreased. So it's 0.33 now. And this ground coverage ratio represents the ratio between the used area of the panels and the unused area. So when this percentage decreases, the area that we are exactly using will decrease, and then we will use a smaller number of panels. So we are losing area now when increasing the pitch distance. So we can conclude now that our challenge is to make a balance between the ground covering ratio and the limited elevation angle to increase the limited elevation angle as much as possible, then get the lowest shadow from one panel to the other, and at the same time increase the used area as much as possible to achieve the highest output power. Now after making the pitch distance of 9 meters and we have a ground covering ratio of 0.33, we can open the graphs to show our results. So we press on shading graph and then maximize it. Now you can see this yellow curve represents the solar radiation during the day. So we can see at 6 a.m. we have a lower radiation, and then at 7 we have a larger, at 8 a larger. So the radiation is increasing as we learned it before until getting the maximum value at 12 p.m. at which the sunlight rays are perpendicular to the place. And here you can note that we have 7 curves on this yellow curve, starting from 1, 2, 3 until 7 at the down. And here at the upper right, this is the description of each curve. So it says that the curve 1 here at the upper is for June, and the curve 2 is from May to July, and the curve 3 is from April to August, and the curve 4 is from March to September. And this means that the curve 1 and curve 2, which is for June and from May to July, which are the summer months, they have the highest irradiation, as this is the largest irradiation, and this is a lower one, and this is a lower one. And that's what we have learned before, that the summer months has the highest solar irradiation, while December has the lowest solar irradiation. So December is the curve 7. You can see that it has the lowest solar irradiation. But the very important curve now is this dotted curve here, this upper dotted curve, and its description here is that it's the shading limiting angle curve. So this curve looks like a border, and after it there will be no shading, or the area after it has no shading, and the area down it will have a shading from one panel to the other. This is because it's the limiting angle curve. But when looking at the peak of the curve and when going left here to see its intersection with the time, we will find that it intersects with the time at 5:13 a.m. So this means that before 5:13 there will be a shadow, and after 5:13 there will be no shadow. But actually the sun starts to rise at about 6 a.m., which means there is no need to decrease the value of the limited elevation angle to be very low at this level, as we will not get a valuable solar irradiation anyway. This is because we have a very weak solar irradiation at this time. And for this we can go back to our optimization and we can change the value of the pitch. So let's decrease its distance to be 6 meters, for example. So you can note that we have got a more better value of the ground covering ratio. Here it's 0.5. So we are using now about 0.5 of the ground area. And also the limited shading angle has been increased to be about 23.8. And now let's check the graph results by pressing on the shading graph again, and let's maximize it. So you can notice that this curve area has been increased. This is because we have decreased the distance, and then the limited shading angle has been increased. And when going to the peak of the curve to see its intersection with the time curve, we will find that it's about 6.13. So before 6.13, an area of the backward panel will be shaded, and after 6.13 there will be no shading from the front panel to the backward panel. But you know, those are some good results because the solar irradiation before 6.13 actually weak. So we don't need to increase the irradiation on the backward panel before 6.13, as it's actually not important for us. But on the other hand, the valuable gain will increase because the covering area is increased. So let's go back again and change the distance. For example, let's make it to P5 meter. So the coverage ratio has been increased to P0.6, and also the shading limited angle has been increased. Let's go back to the graph and increase it. So that's good. When going to the intersection of the peak value with the time, we will find that it's about 7.30. So at this point we have made a balance between the ratio of the coverage area and also the shading limited angle. As actually on the practical work we got the valuable irradiation from the sun on the panels starting from 8 a.m. for example, and starting from 8 a.m. there is no problem or there is no shadow, as our limited shading angle is smaller than it. And also notice that we have those two dotted curves here on the diode, this one and this one, which represents the shading of 20% and the shading of 40%. So it's logically that when going down the shading increases on the panel, so the percentage of the panel area that has the shading increases because the limited angle is increased, or the value of the elevation angle itself decreased when going down. That's good. Now let's close this window. And now the last thing we have on this tutorial is to show the optimization. So when press and show optimization and then maximize the window, so we can note that we have this green curve here, which represents the ideal solar irradiation on the panel when we have no shading effect. So this is the ideal case with no shading, and this black curve is the actual curve that we are working on. So it represents the irradiation value when we have a shading from the front panel to the backward panel with a limited value of alpha of 32 that we are working exactly on it. So this is the actual curve, and the program tells us that the difference between them is about 6.1%. So this is the difference between the ideal case and the case that we are working on to have a losses of 6.1%. And now to see the curve on a lower scale, we can press on this tab here to decrease it. So we will find that this is a relation between the output energy on the y-axis and the tilt angle on the x-axis. So this means that by increasing the tilt angle, the output energy increase until getting to the maximum value. So the maximum optimum value here at this point, when going down, we will find that it's about 30 degrees of the tilt angle. While when going further to the right, we will find that the tilt angle decreases gradually. So we need to capture the optimum tilt angle at this point. So by this way, we can adjust the relation between the coverage area and the pitch distance and the tilt angle. Hope that's clear right now. Thank you for watching and see you next tutorials. Hello and welcome everyone. Very happy that we are all together again. In the previous tutorials we have learned how to design the GRIDTIE solar system with the preliminary design on the PVSYST software. And in this tutorial, this is the time to explore the project design, which is the complete project with all the details required. So let's go ahead. Firstly, we press on project design, and then press on grid connected. As until now we are working on the grid connected projects. Now it asks us to enter the file name and the project name and the site of the file and the meta file. So suppose now we are working on a project in Bonn, Germany. Here we type Bonn. Then let's make the project name to be on grid at Bonn. Now we need to press on meta database and then geographical sites. Then we need to choose Bonn, so this is Bonn that we have, and then we will press on open. Now we will press on import, then yes, and after that press on OK, yes, OK, yes, and then save, and then close, and close. That's good. Here we have selected the file that we need. You can select any file at any location. It's up to you. Now to activate the project, we will press on save. So it asks us to save the project. We will press on save and press save. That's good. Now we need to open the orientation tab. Firstly, it asks us for the type of installation, if we need a fixed plan, or if we need some several orientations, if we need a seasonal tilt adjustment. This is because we can adjust the panels with a tilt angle on the summer and another tilt angle for the winter. So by the seasonal tilt adjustment, we can change the tilt angle at some months in the year. Also, it asks us if we have a tracking system, but for us now, we will go up and choose the fixed orientation. And now let's open the optimization tab. Now, as we learned it before, when changing the tilt angle, we can have a good results or more better results during the year. This is by changing the tilt angle and also by changing the azimuth to see its direction or the direction that the panels will be in front of it. So it has a peak value at this position, for example. And now when going to the summer results, so we will see that we have also about the optimum value or the peak value. And for the winter, here for the winter also we have some relative good results. So this is for the yearly yield. It gives a good average value as we said before. That's good. Now you can see we have a factor here. It's called the transposition factor, which is equal 1.19. So the transposition factor is the ratio between the incident solar rays that falls on the panel to the global horizontal radiation that falls on it. So this ratio may represent the losses in the system as it calculates the amount of radiation that the panels exactly get benefit from. But from the practical side of view, we find that the transposition factor helps us to know what is the best tilt angle that we choose to get the best output of the solar system or to decrease the losses as much as possible. So suppose we need to make a design for the summer only. So our case now is that we need a system that will supply us with the electricity at the summer months only. So we are focusing now on the summer months, and hence we need to get the best output values of the month. We need to get the best tilt angle for the month and the best azimuth. Then the transposition factor will help us to get the most accurate result at a specific point or at a specific case that we need. Good job. Now after adjusting the tilt angle and the azimuth, now we press on OK. Then we have finished the orientation. Let's go to the system. Here the first thing we need to specify the required output power from the project, and the required output power is specified here. So suppose for example we need an output power from the project of about 5 kilowatts. So we type here 5 and press enter. That's good. Then we can go to this part to select the panel that we need to work on. So by dragging down this toolbox, we have many companies that we can work on. We can choose a very strong and widely spread company. That's the Canadian company. You can face it in the practical work very much. Here we can press on Canadian. C for Canadian. That's good. Then we need to select the specification of the panel that we will work on. Suppose we will work on a solar panel that has a power of 280 watts. So let's go down. This is the 280 watt. Here we can choose this panel for example. Now we can open its data sheet. So those are the features of the panel. You can see its open circuit voltage is about 38 volts and its voltage of the maximum power point tracking is about 31 volts. Now we press on OK and cancel. Now this is the type to choose the inverter. So from this tab we can choose the required inverter. Let's type Schneider Electric. So we will work on Schneider Electric inverters. Now as the required power to achieve is 5 kilowatts, here we can choose an inverter with 5 kilowatts. So this one is good. And here its operating voltage ranges from 100 volts to 540 volts, and its input maximum voltage is 550 volts. And also it has the technology of the multi-maximum power point tracking modules. So each MPPT module of it will carry a power of about the half of the power, which is 2500 watts. And for this we estimate that we will have two strings as we learned it before, and this is what exactly appears here. So this is the number of panels that will be inserted series, and this is the number of strings that we have, or the number of parallel rows. So we will have 2 strings, 1 string for each MPPT. This is because we have here 2 MPPT. But now we need to select the number of panels that will be in series. So as each module or each MPPT has a power of 2500 watts, but each module power is about 280 watts. So when we divide 2500 over 280 watts, here let's do that on the calculator. 2500 over 280, so it gives us 8.9, which is approximately 9 panels in each series branch. And here you can notice that this is what the program suggests. So the program suggests us to have 9 panels for each string. So our design now is a good one with no problems. But now you can notice that we have this box on the right. So at this box there may be some messages that appears if we made the wrong design. For example, if we increase the number of panels, let's increase it to P12 for example, and let's select this one again. So we will have a message that says that the inverter power is slightly undersized. This is because the number of panels for each string is 12, which will give an input power that is larger than 2050 watts, while each MPPT of the inverter has a power of 2500 watts, so the inverter is undersized. Now suppose that we increase this number again to P20 for example. We have a serious warning here that says that the array open circuit voltage is greater than the inverter absolute maximum input voltage. This is because the maximum input voltage of the inverter is about 550 watts. But the open circuit voltage of each series branch is about the number of panels, which is 20 times the open circuit voltage, which is 42. So when we multiply 20 by 42, it will give us about 860 volts. So 860 volts is a very larger input voltage that is larger than the input maximum voltage of the inverter, and for this reason this message appears to us here. Now let's make it back to P9 only, and here we have no messages, so our design is right now. And here the area of the design, as you see, is 18 meters square. So this is the suggested area for the design that we have made to get an output power of 5 kilowatts from this project. Now we can press on OK. And after that we can run the simulation. And then press on OK. And yes, here we need to save. Now we can open the report to see the summary of our design. So this is our report. You can see that those are some information about it. Here our design is at Poland, the country is Germany. This is the latitude, the longitude, and the altitude on the sea level, and the time zone. And this is the day at which we have made the design. And then when going down, we will see the tilt angle that we made the design at it. And after that, some information about the arrays. So we have used a pulley array, and we have used 9 modules in series and 2 parallel strings, each string on 1 PPT of the inverter, and the power of the module is 280 watts. And the nominal power output is about 5 kilowatt, and the array operating voltage is about 245. And then when going down, we will find that those are some data about the inverter. Here it's from Schneider Electric. Its output power is 5 kilowatts, and it has 2 maximum power point tracking. Each of them will be loaded with 50% of the load. Now those are some information about the losses of the array. As we learned it before, the array has some losses, the thermal losses, the wiring losses, and this is the percentage of losses of each of them. Now when going to the second page, we will find that this is the power analysis. Here this purple power on each of those columns is the losses in the array or the PV array, and this green one is the losses in the inverter, and this brown one is the produced useful energy. So we can see that we have the maximum output power or the P value of the power at the summer months. Now when going down, we will find that this is the energy table at each month. So at January, for example, we will have the array energy of about 199.8, and the energy that reaches the grid is about 191. So the difference between them here is about 9 watt, which is the losses. So the array produces an energy, but there are some losses in the inverter and the panels, as we said, but it's a smaller losses as we learned it before. Now when going to the third page, we will find that this is the diagram of the losses. We will find that this is the produced energy. Firstly, it's about 5,500 watt, but the reached energy at the lost after the losses is about 4,900 watts. So we will have a photovoltaic losses of about 2.2% and losses due to the temperature of 4.3%, and the inverter losses during the operation is about 3.4%, and so on until reaching the output energy that will be injected to the grid. So this is the energy injected to the grid. So that's about this tutorial at which we have learned some details about the full design of the full project and how can we enter its details and receive its output. Thank you for watching and see you next tutorial. Hello and welcome everyone. On the previous tutorials we have learned how to make the on-grid solar system design on the PVSYST software, on the preliminary design and on the project design. And now this is the time to discuss the standalone or the off-grid solar system design on our program. And for that we will press on project design, then instead of grid connected we will press on standalone, and now this is the time to choose the place that we need to work on. So for example, suppose now we need to work on Milano at Italy. For that we will press on search and then press on new, and now choose the site. And for example here we will search for Milano. That's good, this is Milano, and then OK. Good job, the site has been added, and now we can save it and press save with the name you need. So we can name it, or we can rename it to P Milano OFFGRID. Then we press save, and yes. Now the first thing as we use is to enter the orientation, and you can notice that the default value of the program is the winter, so we need to get the optimum results at the winter. This is because we are related to some loads that we need to feed. So we must make our design at the worst case or at the months that have the worst solar irradiation, as our loads must work well at those months. So we need to get a larger number of solar panels and a larger capacity of the batteries to store the required energy that will feed our loads. So if we made a well design on the winter months, it will be easy for the design to cope with the summer months. This is because at the summer the solar irradiation will be larger, and we have made the design at the worst case. Now we can show the optimization. Then we can change the angle, the tilt angle here, until getting the optimum value. And here we have a tilt angle of about 53 degrees and the azimuth of 0. Now press OK. That's good. And after that we have the user needs. So we press on user needs. And at this point it asks you to enter the number of devices and the type of the device and the power of each device, and also the number of hours in the day that the device will work for. So the first device that the program asks for is the lamps. Suppose for example we have 10 lamps, and the power of each one of them is 20 watts. Then it will work for 10 hours in the day. And for the TV, suppose we have one TV and its power is about, for example, 200 watts, and it will work for 6 hours in the day. Now for the domestic appliances, suppose we have one and its power is about, for example, 30 watts. And for the fridge, we have only one fridge and its power is about 130 watts. So it asks us for the kilowatt per hour, not the watt per hour. And for this, its watt hour per day will be about 1,300. So its kilowatt hour will be about 1.3 kilowatt hour per day. That's good. Also, if we have a washing machine, so we have one washing machine, and its power is about, for example, 700 watts, and it will work for 2 hours in the day, and press OK. That's good. Now the next step we need to work on is the hourly distribution. So it asks us again for the number of hours for each device that we have entered. So we have entered some lamps, a TV, a domestic appliances, a fridge, a dishwasher. So we need to fill those tabs also. Here for the lamps, it was working for 10 hours. Let's go back and make it to P 10 hours. Let's increase those to P 10 hours. That's good. Here 10 hours. And for the TV it was 6 hours. So let's go back for the TV and make it to P 6 hours. Now for the domestic appliances, it was working for 8 hours. So let's select 8 hours here. Then we need them to be 8, 7, and finally 8 hours. And the last thing is the dishwasher, so it works for 2 hours in the day, and those 2 hours are selected now. After that, we will press on OK. That's good. Here the second step has been done. Now let's go to the system. Now we are ready to enter the data of the batteries. Here it asks us for the pass voltage, so its default value is 48 volts. We can set it at this value, at the suggested value, and also the suggested capacity or the total capacity of the batteries to be 816 ampere hour. And now it asks us to enter the type of the battery we need. It's ampere hour according to its voltage or capacity or manufacturer, so we can select capacity. And then let's choose a battery which have, for example, 180 ampere hour. Here it tells us we will have 2 batteries in series and 5 batteries in parallel, or 5 branches in parallel. So when we multiply 5 by 2, it will be 10 batteries. Here it tells us the battery pack voltage is 51 volt and the global capacity is about 900 ampere hour. Then the DOD factor is 80%, and this is the total weight of all of the batteries, and this is the number of cycles and so on. So those are some features of the batteries. Now after selecting the batteries, we need to select the PV array or the solar panels. So we will select it from this part here. So we can select a panel that has a power, for example, of 250 watts. Here let's go down until 250. So that's good. Let's select the 250 with a pulley type. So we can select this one. Here it tells us that the open circuit voltage of that panel is 42.4 volts. And its maximum power point voltage is 25.9 volts. And after that, we need to select the charger controller. So it tells us if we need to select it to be a maximum power point tracking converter or a DC-DC converter. So we will select the maximum power point tracking. And here it asks us if we need to choose a universal controller or we need to select a controller ourselves. So we will use the universal controller. So when we use the universal controller, all the parameters required for the charger will be adjusted according to the other system parameters. For example, if we have a pulse voltage of 48 volts, so the program will choose automatically a pulse voltage of the charger controller to be 48 volts, and also it will choose a current range that we need for the charger to be suitable for the rating current that our system works on, and so on. And now after finishing, let's open the backup. Here it asks us if we need to use a backup generator or not. So the backup generator is used for the sensitive loads. Suppose you need to supply some loads in the hospital, so the critical loads needs a backup generator or a backup system to supply the loads in case of the main source has been shut down for any reason. Now we will not use a backup generator. Here let's open the scheme. This is the scheme or the layout of the standalone or the off-grid system. Here those are the PV array, and then we have a bypass diode that allows the current to move in one direction and doesn't move in the other direction. So this is not to make any damage for the system for any reverse or back current. And then we have the regulator or the charger controller, and this regulator or the charger controller will feed the batteries. And also we have the backup generator. This is in case we are using a backup generator, it will be on in case if we have a failure for any reason in our system. So when the generator is on, the switch is on and the switch of the batteries is off. So in case all the batteries switch is off, so the generator will sense that, then its switch will be on to feed our load. So those are our loads, and this is the direction of the current. And you can see this is the fuse for a protection as well as rated in the off-grid tutorials. Also we can save our project to save the changes, not to lose it. And after that we need to run the simulation to see the output result of the program. Then we can close it, and after that we will open the report to see the summary or the results. Now let's zoom in. Here it tells us our project is done in Milano, country Italy. This is the latitude and the longitude. Now when going down, it tells us that this is the total angle which we have to choose, 54. That will give us the optimum results at the winter, and the azimuth is 0. Now when going down, we will find that we have used a PV array of the pulley type. Then we use 2 modules in series and 13 strings or 13 branches in parallel. So 13 branches times 2 in each branch equals 26 modules. and its total nominal power is about 6.5 kilowatt. Then the area that we need to spread those modules into it is 42.2 meters squared. So this is the total area that we need for our project. And finally, it tells us about the losses that we have illustrated before in the on-grid design. And when going down, we will find that those are some informations about the batteries. Here the battery is 180 ampere hour and its voltage is about 26 volts. So we can say that it's approximately 24, so 24 times 2, as we have two batteries in series, will give us the pulse voltage that we have seen to be 48 volts. Now the total ampere hour is about 900. And for the controller, those are some informations. Its technology as the maximum power point tracking. Now let's go to the second page. Here, those are the loads that we have used. The TV, the domestic appliance, the fridge. And this is the hourly profile of the use of the loads during the day. Now let's go to the third page. Here, this is the energy performance of our system. This flow energy is the energy that is stored in the batteries when the batteries is full, and those purple ones for the losses in the PV array, and those for the losses in the batteries. And then when going down, we will find that this is the energy profile during the year. Here, this is the megawatt hour generated for each month, and finally, this is the total for the year. And now for the last page, we have the losses in the system. So you can note that we have a very larger losses than the on-grid system, and for this reason on our manual design we doesn't take the losses into account, so it was small. But here you can find that we have a large losses starting from the solar irradiation itself. Then on the array we have some losses, and then the losses in the batteries and the charger controller. So that's about the off-grid solar system design and the PV software. Hope that's clear right now. Thank you for watching and see you next tutorials.